Good morning. My name is Kevin Crothers, and I am the STEM teacher at Mass Academy. And I appreciate you coming and volunteering and being present for these presentations. The Assistive Technology STEM project that we're going to be presenting today provides Mass Academy students an opportunity to work with members of our community to identify and address needs. An assistive technology is any type of device that increases participation, achievement, or independence for any individual. Mission Empower defines an assistive device as being anything from a low-tech device, like a magnifying glass, to a high-tech device like a computerized communication system. Mass Academy students work with our community partners to engineer solutions that are small, low-tech, and easy to iterate. In a regular design cycle, teams of 3 to 4 students are matched with a project that typically takes 3 to 3.5 months from receiving the request to developing a deliverable device. Consistent work and the iterative design process are essential for successful delivery. However, this has not been a normal design cycle. Students have been working online for the majority of this project. Collaborating over Zoom, remotely printing out prototypes and testing, and challenges in obtaining client feedback have been stumbling blocks during this particular term. Students have been able to show their grit, resolve, and perseverance in their desire to deliver a product worthy of the clients that they are working with. Students see the importance of providing a working deliverable product and are willing to meet with their clients over the summer when restrictions in mobility have been eased. Each session will have 4 presentations. After each presentation, there will be an opportunity to ask questions.
Okay.
So I am asking that you remain muted to try and keep down on some of those background noises if you have them. But then if the panelists have an opportunity to ask questions, questions may be asked by hitting the QA button at the bottom of the Zoom screen and typing it in. And so I will see those questions from the attendees, and participants can also use the chat button to ask those questions. If you have a similar question that has already been asked, you can upvote that question. In the email for the panelists that I have recruited, and I appreciate you volunteering, I have forwarded a link to a Google form to help you provide feedback to the presenters. And I ask you about process, the product, and the presentation. And if you would like, I will also put the link in the chat room to all panelists and attendees, so you can end up providing that feedback as well. I appreciate you and I thank you for attending. My students are absolutely eager to receive your expert feedback and your guidance. So the first presentation that will occur is Julia Toyesh and Jacqueline A. And their project is titled Music Again, an adaptive device for playing instruments independently. So Julia Toyesh and Jackie, go ahead and take it away.
Wait, could you enable screen sharing?
Okay. Okay, go ahead.
There we go.
I'm Julia.
I'm Toyesh.
And I'm Jackie.
And this is our project Music Again, and our device is a piano pedal pressing device. So for a problem statement, spinal cord injuries often result in limited motor function for patients. And so patients often have difficulty doing some daily tasks, which include a number of things, including playing music. And so their limited motor function can range all the way from paralysis of the legs to almost full body paralysis. And the goal of this project is to design a device which can help them produce music easily, which could benefit them.
So there are three main competitors for our device. First, the Jambox, which is a hands-free breath control device similar to a harmonica. So the user blows into the mouthpiece and this produces music. And then the mobile music glove, which is a glove that sends vibrations to the user's hands, and this helps them play the piano. They also ran some studies on this glove and found that when users wore the glove for extended periods of time, they began to regain some sensations in their hands and fingers. So it was also useful for that. And then there's the Clarion, which is a program that uses eye movement detection to play musical notes. So the user basically looks at different objects on the screen and this translates into musical notes. So the initial requirements for our prototype were that it helps someone make music individually, can be used by patients with spinal cord injuries, which would mean that they have a limited range of motion. It should be durable, simple to learn how to use, doesn't cause significant physical strain for the user, costs less than $50, doesn't change the sound the instrument makes or decrease the quality of music, should be easy to adapt to, and comfortable for the user. It shouldn't require access to multiple outside resources and shouldn't have too many wires for hardware. It should be aesthetic and visually pleasing and usable by users with a variety of spinal cord injuries because these can range in severity. And it should have adjustable settings and be detachable and portable.
So our first design, since it was a very broad topic, we decided to come up with multiple ideas that we could try to make. And so our three ideas were a guitar finger extension, which would allow people to play the guitar with a smaller motion of their fingers. Our second design was a trombone slide, which would involve a touchpad and allow players to move a trombone slide while only sliding a touchpad, which would also allow for a smaller movement of joints. And the last one is the one that we went with, and it was a device to push down piano pedals to aid with playing the piano. Our designs for the models for our CDR were just CAD models to try and get a sense of what we could possibly make. And so we came up with two designs for the guitar finger extension, but we decided not to go with this because the first one had very limited freedom and the second one didn't have much reach. Then the second thing that we came up with was the trombone slide mover. And here we came up with a hold, which would hold a piston along with being connected to the trombone to be able to extend the slide. And our third model here would be the casing, which would hold 3 pistons to push down piano pedals.
And so one of the ways that we decided on the piano pedal was we did a stress analysis in CAD. And the stress analysis just, you apply a force and then the computer simulates what would happen if a certain area of the design were to remain stationary and then the force were to be applied. And you can see that these are like the results of the stress analysis for all of them. And for the piano pedal piston, we found that it was less susceptible to the forces. And the least amount of stress to the most amount of stress was the first design, and then the trombone one, and then the piano pedal, and then the second design for the finger piston. And the maximum displacement was the trombone slide, the finger pick, and then the piano pedal, and then the second design for the finger pick. And also when doing the design study, one of the trombone pieces was actually unsolvable because there was too large of a displacement. So that's one of the reasons why we didn't choose the trombone slide.
So after making the CAD models, we decided that the piano pedal pressing device would be the best choice to move forward because it had the most straightforward objective, and we felt it would be applicable to a wider range of individuals. And so we also decided that the ideal way to push down the pedals would be to use a motor rather than a piston, because with the motor, the code would be easily implementable with the Arduinos, and it would be more carefully controlled. So we also decided to switch the input method to buttons rather than a breath controlled sensors because of our time and materials. So this would be a possible extension to make it breath controlled.
And then this is the first design for the piano pedal piston. And it's piston based, and there's only the base of it, so there are no pistons, nothing else. And then the second design has the pistons in it, but it doesn't have anything else, and it isn't actually functional. And then the third design, we changed it from pistons to gears, and we also added plates that would push down the piano pedals. But as you can see, it isn't fully implemented, and there are no things that connect the plates to the actual base. But we also added a connector that ensured that the piano pedal pusher would be secure when attached on the base of the piano. And then for our final design, we implemented a motor, and we had attachments for the motor so that the motor wouldn't move from its place. And we also had a vertical gear assembly that connected to the pedals, and then the pedals, or the plates for the pedals, would go up and down and then press the piano pedals down. But we don't have any electrical components because this is still entirely in CAD, so we would have to add electrical components for it to actually work. And then our method was we would 3D print the CAD files with a durable material, assemble the mechanism as in the CAD assembly, attach the model to the piano above the pedals, attach 3 motors, 1 to each gear of the CAD parts, connect the motors to the breadboard and an Arduino, connect the 3 buttons to the breadboard and Arduino, and then write the code to associate each button with a corresponding motor. But we haven't done these steps because right now the file is only in CAD.
So after creating the device, we went back and analyzed whether or not it met the initial requirements. So for producing music and allowing someone to produce music individually, we would assume that this is yes, but since we didn't get to physically test it on a piano, we can't exactly confirm it, but based on the CAD test, this should work. It will be usable by patients with spinal cord injuries. Based on the testing, it should be durable, simple to learn how to use, yes. It should not cause physical strain for the user. It probably won't end up costing less than $50 just because of the additional electrical components and access to 3D printing, but this wasn't a very top priority. And it shouldn't change the sound of the music. We would expect that it would be easy to adapt to. And we also expect that it will be comfortable. Again, it does require some outside resources, so it didn't exactly meet that requirement. And it does have some wires required for hardware, but it's not so many wires that it would interrupt with the user playing the device. So we felt that it still met that requirement. It's not exactly aesthetic, but again, that wasn't a top priority. it should be usable by various users. It does not have adjustable settings, but it is detachable and portable.
And then here's a video demonstration of how we would put together the device and how it would work. As you can see right now, these buttons. That's
Julie, I don't
how-
know if we can hear you.
Oh, wait. I'm not muted. Oh,
I think it was just glitching,
oh, okay.
but that's okay. We can just keep going.
And so, yeah, so yeah, so each of the motors would connect to one of the piano pedal plates, which would also connect to like a specific button. And then we would just program the Arduino to have the motor be activated when one button is pressed. And that's how it would work. And though we didn't manage to make a physical model, we still wanted to share our work with the community at large. So we made an Instructables. We also made a YouTube channel that explains how to make the piano pedal pusher. And it also has a link to our GrabCAD community, or our GrabCAD link, which has the piano pedal pusher STL files and also the actual SolidWorks files. And so because it's connected to both YouTube and GrabCAD, anybody could take these files and build off of it and improve it and make it better. And anybody in the world could use our project.
So our next steps would be first taking the model from a CAD file and 3D printing it with a sturdy material, and then using circuits and motors to be able to properly assemble the device and test it out on actual piano. And could you hear me now? Oh, yes. An additional step is to add sensors to the Arduino to make sure that the motors don't cause damage to the mechanism or the piano. So for our takeaways, it's always good to have multiple ideas and open mind when designing a prototype. And so when we were starting off with our designs, some of our first ideas like the guitar pick and the trombone, we feel it wouldn't have worked out as well. So we think it was helpful to come up with this piano idea. And it was also helpful to keep thinking about ways to move the pedals down because pistons would not have been as effective as using motors. And also a similar idea, multiple plans could have been made in case of unexpected limiting factors, such as the whole quarantine situation. And we felt that we made a good amount of progress, but we could have made alternative plans and come up with a much better final product ahead of time, potentially.
And then that is our project. Any questions?
Okay, so you can ask questions. Panelists can unmute themselves, or if you'd like to type it in to the chat room or even the Q&A, I'll read them off.
Looks like Annika. Are you raising your hand, Annika?
Oh yeah, but so
No
my
question.
no, I do have a question. Well, my question was just for when you were saying how I know you weren't able to get a lot of user input done for because of COVID, but how were you planning on if say the circumstances were different? What were you doing in order to actually get user input? Like, what was your plan for testing for these models that you developed? How would you-
So I believe we were just going to print these out and use a piano that one of us had and just kind of see how it would produce the music and how it would sound, and then potentially try to meet up with a client and have them use it and see if they enjoyed it, if they had any feedback. So that would have been pretty useful.
So if you have a question, you can use the question button. If you have in your panelists, you can end up asking a question by raising your hand, and I'll acknowledge it. Scott Justo.
Hi, very interesting project, guys. I didn't get a clear perspective on the buttons. Would those be, so people would push the buttons with their hand, and how would that affect their playing of music on the piano?
Yeah, so basically, the idea is that you would have 3 buttons put near the keyboard. Oh, my microphone just fails sometimes. So you would have 3 buttons put near the keyboard. So as they're playing the piano, they would push it once, and then the pedal that's associated with it would be pushed down, and then they would press it again to move it back up. And so sometimes, like if your left hand has like nothing to play at the moment, you could quickly press the button and then have your right hand continue on.
So we have a question from Ulm. What was the #1 feature you would like to have seen added?
It would have been nice if we could have added the Arduinos to the CAD model, because right now it's just on CAD, but if we'd added the Arduinos, we would be able to have it actually work.
A question from Charlie Trong. What is the size of the product?
I think that the base is 40 centimeters. And that was just like somewhat arbitrary, but also somewhat based on a piano that I have at home.
Okay. There is a question from the attendees. Ajay, would you like to speak up?
I got a question.
Okay, go ahead.
I really like the fact that you've explored different designs, and you outlined your requirements at the beginning and you evaluated them at the end. That was really cool. Did you ever think of modifying this design to actually play the not the pedals, but the what do you call the finger thingies?
Yeah, so I think that was initially like what we were thinking. We wanted to find a way to help the user actually play the keys, but this just seemed like a bit complicated. So we figured that first we'd focus on the pedals and try to get a prototype working for that. And then possibly in the future or for future students doing this project, it could be applied to the actual keys.
Yeah, and I like the fact that you use the gear, because the pedals are going to require a lot more force than the keys.
Yeah.
And for the keys, I wouldn't get too wrapped up in 3D printing. You could probably reduce the cost by maybe just using common elements that you find around the house, or wood, or
Yeah.
great project. Thanks.
Thank you.
Okay, we have one question from Mr. Thurul Malai. Let's see, where did I put? You can unmute yourself if you'd like.
I believe that viewers can't unmute.
Okay, so if you'd like to type your question into the chat, we can answer that question shortly. Gina Betty has a question. Are you juniors or seniors? And if seniors, how will you hand the project off to the next class?
So currently, we're going to be transitioning into the senior class, and potentially we may work on this project over the summer and try to get it working. Otherwise, we could try and see if any groups next year are interested in this project. We'd talk with them and pass it on to them to work on their own STEM 2 project.
Okay. All right. Well, thank you very much. I appreciate the presentation. Great job. Up next is engineering an assistive cup for an individual with Parkinson's disease, done by Will, Clarice, and Liv. And while they're getting ready, if you could end up any of the attendees or the panelists typing in your questions into the chat. I'm clarifying that process right now, and then I'll ask those questions from the chat. All right, hopefully you guys are ready? All right.
All right. Good morning, everybody. My name is Will.
I'm Liv.
And I'm Clarice, and we engineered an assistive cup for an individual with Parkinson's disease. So the individual has progressive Parkinson's disease, which is a neurological disorder that debilitates movement over time. Currently, we have difficulty using a cup to drink liquids and have no use of their arms or hands. So therefore, the cup they're currently using is being controlled by a caretaker who prefers to dispense liquids through tipping. You can see the cup on the left is what they're currently using. The narrow straw makes it difficult to clean. The abnormal shape is uncomfortable. And on top of that, it requires the drinker to have sipping capabilities, which the individual does not have. And most of the cups that are currently on the market are designed with cheap plastics and are difficult to clean. So the project at hand is to develop a cup that uses a tipping capability and is also endurable so that it can be used for a long time.
So listed here are the level 1 requirements for this project, but there are a few notable ones I'd like to highlight. First is number 1, that the device can facilitate easy liquid regulation. This is really the requirement that sets this cup different from what's on the market right now. It's designed to assist a third party in feeding the individual, specifically one that cannot regulate water on their own and cannot hold a regular cup. So then is number 3 regarding cleaning. This one's our client's biggest complaint when it comes to current designs, that even if they were helpful in terms of water regulation, that they were often complex and difficult to clean. And then is also number 8 that says that liquid should be visible. And our client specifically noted this to be a good part of solutions that do work right now. So we attempted to also implement this into our design as well.
So when we had our preliminary design and our CDR, we came up with 4 main proof of concepts that all have similar base but different kinds of regulation. So the first one is a pitcher design where the base is extended and narrowed to make a straw. The second one is a modified basic cup, which is a lot more like the cups currently on the market, as you can see by the conventional straw shape. The third one is a sliding cup, which would use a sliding mechanism to open and close a plunger that regulates intake of liquid at the bottom compartment. And the fourth one is a squeezable straw, where the straw at the end is made out of a flexible material that the client could use to squeeze and regulate liquid. After making proofs of concepts and into preliminary testing, we decided to move forward and improve on the first design because not only was it the most mechanically simple, but met the most requirements and was also the most reliable while also using the tipping mechanism.
So for an overview of our build process, as Clarice said, we started looking at the first 2 that were shown on that after doing some talk with our client and getting their feedback. From there, we built the proof of concepts for these 2 models and we started testing these. We just did a basic test that tested water regulation and cleaning and just showed which one was going to be easier. We then moved forward with that design and we wanted to test different characteristics of it. So we tested the straw shape, straw angle, and the bore size, and we tested most of these for both water regulation and cleaning. Only one of the tests was conducted for just water regulation, and we wanted these to be easily comparable, so we rated them on the same quantitative scale throughout all of the tests for all of the prototypes. And then we would take what we decided was the feature we wanted to move forward with and implement it into the next test. For example, when we conducted the straw angle test, we had 2 different designs, and we after deciding which straw angle we want to move forward with, we implemented that angle into all of the tests for the bore size. So our first design study, we looked at the straw shape. As you can see, these were our 3 different designs that were tested for both the water regulation and how easy they were to clean. The ones that showed us the best results was the far right, which we call our linear design. This had the highest ratings, and it didn't have any any specific drawbacks that were specific to this one and not the other 2. The minimal curvature really helped with it being easy to clean. And although it did have the fastest flow rate, we were told that this would be the easiest to regulate still. A little overview of how we went about our testing. We actually did all 3 of our design studies virtually over Zoom. We didn't have actual access to our prototypes until this week when we picked them up. So we had Dr. C print out all of our models, and then we would meet with him over Zoom and conduct our tests. So we didn't get to see and perform the tests ourselves.
So as Liv previously mentioned, our second design study was a focus on straw angle to see if that would impact the flow rate in any ways. We tested using water in 2 main designs, the first one curving up with the shape of the straw, and the second one being more linearized like the traditional straw shape. So using the same scales before, we found that the steep angle design, which is the photo farthest to the right, performed the best. Not only did it have the highest rating from our virtual tester, but was also able to slow down the water output and allow a more controlled flow rate.
So for the third and final design study was a little less clear cut than the first 2, as we studied the bore size and how it affected the pourability and ease of cleaning for the user. And they found that the smaller bore diameters created a more controllable and slower stream of water. However, this was a cost of some ease of cleaning, as the smaller bore we found was a little more difficult to clean reliably and feel like you were getting a good job of cleaning all the small pieces, versus the larger bore sizes, which the largest bore size we tested was 12 millimeters, was significantly easier to clean because it was much more open and you could get in there with tools a lot more reliably. However, because it was so large, it didn't do as good of a job as the smaller ones at creating a consistent and slower flow, making it more rapid and harder to control. So after kind of weighing these against our criteria, we decided to move forward with the smaller 6 millimeter bore because the flow rate of the cup directly affects the individual's safety when trying to drink. So we decided to try and optimize for that. And for the final design, it implements all of the findings from our first design studies. So the straight straw, the linear angle, the smaller bore size. And this version of the cup was printed with a translucent PETG 3D printing filament and an attachment for a screw-on cap, which was also printed with the final prototype. So the original intent from early on in the project was to coat the entire final prototype with an epoxy coating to seal holes in the filament and make it food safe to drink out of. However, due to the recent circumstances, we have been unable to access the Mass Academy building and the proper lab safety equipment to coat the cup. So when we do have the ability to seal our design, we'll need to adjust the dimensions that we see printed here to account for the extra layer of substance that the coating will add to it. And as for the requirements for the final prototype, it meets most of our initial requirements, aside from the translucent filament, because we wanted it to be more see-through than it currently is. Right now, while the filament that we use to print it is less opaque than the standard filament, it still only really works when there's proper lighting and darker liquids. With water, it can be quite difficult to see through. And here we will have a short video demonstration of the pouring the cup once it loads.
We might end up having to skip this slide just because of the, oh,
There it is.
Okay, so one of the primary requirements was to be able to hold 16 fluid ounces. So you can see that when pouring it into the cup, it fits quite comfortably, going to about the halfway mark. And after the liquid is poured in, you can take the cap and screw it on securely. I used both hands to make sure that it was on completely. And then afterwards, the base is comfortable enough to be secured and held comfortably with one hand. And here's just a demonstration of the tipping mechanism. The further you tip, the more liquid comes out and the faster it comes out, which allows for a versatile and controllable liquid outpour.
So some of the future work that we're looking to do, as Will already discussed, our top priority is sealing our current device with an epoxy coating. This is because since we're working with liquids and water, we don't want any possibility of any water getting in. It will also allow for the device to be dishwasher safe. So although it is food safe, it's going to be more likely to not last as long without the coating, and also it won't be able to be used in a dishwasher until it is coated. Another thing Will kind of already mentioned was the fact that we are looking to reprint our current model and see what we can do to allow it to actually be transparent, whether this is looking into different filaments or just trying to make it a little bit thinner, like the walls of it a little bit thinner so they can be seen. That's something that we want to discuss and weigh options on so that you are able to see the liquid pouring out. We've also been considering and looking into adding a handle. The reason this wasn't just done and put on is because we also want to test the user comfort and see if it actually does make it easier to use or if it doesn't. And then another thing that was on our requirements that we didn't end up having time to do and also would have been really difficult to do without having physical access to our prototypes was adding volume measurements onto the cup so you could see kind of just a brief bit of like fluid ounces on it and how many it could hold and how many were being used each time. So that is the end of our presentation. I'd like to thank you all for watching and ask if there's any questions now.
So the first question is from Gina Betty. A soft silicone or rubber mouthpiece could be added to the spout. And this piece might be able to help control flow to prevent choking. Is that a possibility?
So that's not something that we've looked into at all. So I don't want to fully speak on it and because I don't know much about it. But the one thing is that the way that our device is used, it's not being fully drinking out of like a normal straw where you suck out of it. There's kind of like a two-person help. So somebody else is pouring the cup. So I don't know if that would necessarily be needed, but also it's not something that we've looked into. So I don't want to fully speak and say, oh, we definitely don't need it, or that would definitely help.
Robert Belota asks, what type of handle are you considering?
So when it comes to the handle and user handling, in some preliminary sketches that we were doing when we were first brainstorming, we were looking at sort of finger grooves or some kind of shape to the actual base of the cup to allow the caretaker to more easily hold it and tip it and pour it as the drinker needs. So when we're talking handle, we're looking in general handling, not just normal like handles you'd see on like a beer mug.
Jennifer Baker asks, what is the estimated cost of this cup?
Although we don't have exact numbers, the filament, since most of it is 3D printed and the filament is not expensive, we've estimated that the majority of the cup is just in general very cheap. We don't know exactly how much resin we would use, so we can't give you an exact number, but we've been able to estimate that it would definitely cost under $25 and most likely under $10, which was one of our requirements that we were able to say that we met.
Home asks, thoughts of making the spout or mouthpiece detachable and interchangeable in order to assist with the cleaning and different user needs?
Yeah, that's actually a really great suggestion, and we really appreciate it, especially because the cup also needs to be able to account for thicker, more viscous liquids. It's definitely something we want to do in a further extension. So if given more time, we'd want to make more detachable straw parts that could be taken, not only for the ease of cleaning, but also for the adaptability to more liquids.
Andrew Yang asks, how long does it take for a user to drink all of the water in the cup? Will the weight of the product make it more tiring if it's being used for a long time?
So
that's not something that that's also not something that we've looked into. A main reason we didn't is because we know that individuals who do have Parkinson's and dysphagia most likely will not just drink the entire cup at once. So it's not something that we feel comfortable performing a test on, and that would be more something that we would look into after sending it into our client and getting their feedback on it and seeing what they have to say.
Jane asks, what exactly made you pick this design over some of the other preliminary designs?
So with the other preliminary designs, there was a key problem with each of them. One of them involved the use of two hands, which was one of our requirements was one-handed use because the caretaker found that they often need to use their other hand for some other task while they were feeding this individual. So one of them was knocked off the list that way. One of them, which was the slider design 3 on the presentation, we tried to proof of concept it, and we found that having a slider mechanism inside of a cup was a little complicated, and especially when you're trying to eat things through it and clean it efficiently, it was just becoming to be too much of a hassle. And then comparing the one that we went with and the one that was very similar to the original cup, we did a quick preliminary, like before design study 0, as you could call it, with some proof of concept models, and found that the one that we went with would have been a bit better.
One question from the audience. How do you plan to coat the spout, as this part is hard to reach compared to the rest of the design?
So that's also a really good question. We could use a small brush that could fit inside the hole to coat it that way. There's also always the option of making a detachable straw so that we could just dip it into the resin. And given the cup model, which right now is just one entire entity, we could always just move it around, rotate it to ensure that the resin is in it completely.
Okay. Any last questions from either the panelists? Scott?
Yeah, very interesting, guys. I wondered about the straw design you have is more of a funnel rather than the just the individual straw, and I'm just wondering what the attributes of the funnel versus the straight straw are, the differences between the two.
So there are definitely pros and cons to each. A main pro of just a kind of your more regular straw was that it would be more versatile. So those who experience Parkinson's and dysphagia in different levels would have access to use it, and you would be able to suck through it to drink it. But we did go with the design we chose because based off of our testing, if you're looking at just water regulation, it was much easier to regulate with the design we picked, and also it was much easier to tip and had a less likely chance to spill out the top, because for the more regular straw, you have to tip it a lot more to pour it in. Another thing is that, I'm sorry, I am blanking on what I was gonna say, but we did have to kind of outweigh whether we want it to be more client specific or if we wanted it to be more versatile, because we knew ours would help our specific client more, but it would really limit access to who else was able to use it. And we decided for right now to make it as client specific as we can to try and help our client and this one person. And then if we could do everything we could to make it versatile or make that an extension.
Okay, 2 questions from Gina. First question was comfort while in the mouth a consideration?
That was definitely a consideration, but something that we could not test moving forward, especially during the past few months. Because as much as we couldn't code it, we couldn't drink from it and be confident that it was safe. So in these early stages of iterating, we decided to focus more on the pourability and cleaning because it's something that we could focus on at this time.
Okay, and then the last question from Gina. Were different shapes considered for the mouth part of the straw?
Yes, different shapes were considered for the mouth parts of the straw. If you looked at our preliminary designs, we wanted to use different shapes for the straw and its attachment to the base, and also for the diameter and the angle of the straw. Like Will mentioned, we could only test the water regulation and the cleanability of it for the first half because of quarantine. And moving forward, we thought that our design, at least the current one, was the best of the ones we could come up with. And in addition to that, once we received the actual prototype, we were able to do some preliminary testing using more viscous fluids. And the current shape of the straw does allow for more types of fluids to go through the cup smoothly. And obviously moving forward, we would need to work closely with the client to make sure that it's a shape and a material that they're comfortable with.
I know, Mr. Stabile, it looks like you have a question.
Yeah.
Yeah, so my mind just gets going when I see these designs. Did you ever think of splitting it down the middle so you could break the cup apart in halves to facilitate cleaning? And
That,
also,
oh, sorry. You can continue and then we'll answer.
that would also facilitate, you could, instead of getting wrapped up with 3D printing, which you could still do, you could just plastic injection mold it if you had it up in halves.
I know that some of our we showed you our main 4 preliminary designs. We did have a few sets of designs before that were just sketches. Some of those did include 2-sided designs. I don't know if we were looking at them for the same reasons as you explained when we looked at them. It was more so that you could have kind of like a pour side and then a side that you could drink from, which as you can see, we did implement that because you don't pour and drink from the same piece, but we didn't keep the complete 2-sided separation part. And from your what you were saying about like 3D printing versus the molding, although for some people it's definitely a lot easier to deal with the molding, since we do have access to 3D printers and we are like lucky enough to have that, we found that it's definitely a lot easier for us to use 3D printing because we can design it, and once we have the design in our like software, we can change it however we want. As you can see from like the group before, you can even do some testing in the software before you print it out. So for us, it allows us to work with it more hands-on and not have to continuously say, oh, we want to make this one super slight change, which we didn't realize was going to be there until it was already made.
Great. And one last thing, did you think of having a pivot axis coming out the sides so that it could rest on a mount and just so somebody with Parkinson's could just maybe just push it to drink from?
That's definitely not something that we looked at and we considered, but it is a really good suggestion that we will think about when we move forward.
Thank you.
Thank you.
All right, so we're going to end up having the next group, which is Ryan, Darshan, and Maxi, and they end up have their title of their project is a plate warmer. I would like to also remind all of our panelists and attendees that there is a feedback form that I have put the link into the chat. If you'd like to click on that link to provide specific feedback for the presenters, that would be great. All right.
Hi, I'm Maxi.
I'm Ryan.
I'm Darshan.
And our project is the plate warmer. Okay, so this is our poster that we're going to present.
Maxi, I can't see it. Okay, I can see it now. We're good.
Okay. So as we said, we're doing the plate warmer project, and our client is from Seven Hills, and our client is a person with dysphagia, which means that they have trouble swallowing. And the problem that we're trying to address is that when our client is eating, they take extra time to finish eating their meals such that hot food becomes cold. So we have to create a device that will allow their food to keep warm for the entire duration while they're eating. So here is a table of our level 1 requirements. We had many more requirements than this, but this is just the most important ones. And we color coded it so that green was for if our prototype did meet the criteria, yellow was if it maybe did, and then red is for if it didn't. And then you can see here the progression that we'll cover later on with our test.
So during our critical design review,
I just wanted to highlight a few of the requirements real quick. So the most important ones were that it needs to heat the food for the entire duration of while the client's eating, and specifically they mentioned that it should be for 1 hour. And they also specifically said that they do not want a device that's plugged in the wall with an electrical cord. And because the person is eating from it, we also need to make sure that it's food safe.
So during critical design review, we had 3 possible designs. The first one was a plate with heating coils beneath the surface. These would be powered most likely through a power outlet, and it would be used to heat the surface of the plate by using heating coils. The second design was a plate with hot water beneath the surface, which would create convection currents under the surface, which would heat the surface of the plate. And our third design was a plate with an insulative surface, which would initially be heated before the food is placed on top, and it would stay warm and keep heating the food over time. And so during our critical design review, we had a conversation with our client at Seven Hills, and we received some information and decided to move forward with design 2, which was using hot water beneath the surface to heat it up.
Okay, so in order to create our chosen design, which is design 2, we constructed it out of 3 main parts. The first part, we had a silicone thermal pad that we attached to an aluminum disc. And what the thermal pad does is that it distributes heat evenly, and then the aluminum disc is conductive because it's metal, so it helps conduct the heat from the hot water to the food that's on top of it. And then we attach the aluminum disc and the thermal pad to the top of the plastic plate that contains the hot water. And the plate is plastic so that you can hold the plate without it being hot. And then we still have the conductive surface on top so that the heat can get from the water to the food on top. And that will be shown more in a video that we have later.
So in order to kind of test and iterate this product, we sort of started from the ground up. And so first we wanted to do a control test in order to test to see how fast the food would typically cool down without any sort of outside heating. So in order to do this, we tested in a regular bowl that people would typically use, and we heated the applesauce up, and we used applesauce because it would mimic the pureed food that our client would typically eat. And so we heated it up and tested the rate of cooling over an hour, since the client wanted to be able to eat their food for an hour and it's still being hot. And so when moving into our first tests, we started off with like the plastic base that we intended to put the water in. And we wanted to test to make sure that the water itself would stay hot over the hour that the food would need to be heated for. And so we did a cover test. And so what we did in this test is we tested how fast the water will cool down when it was uncovered and then when it was covered by the aluminum disc. So we have a graph next to down kind of in the bottom center, and you can kind of see that the red line is the temperature of the water that was covered by the aluminum disc, and the blue line is the temperature of water that was uncovered. And so you can see that the water that was covered stayed warm for a longer period of time. And to prove this, we did several calculations that involved calculating the Newton's law of cooling, K constant, And so Darshan will talk about that a little bit later, but that's just kind of like how we proved mathematically that our design kept food hotter for longer. And so after this, we decided to do a drop test. And in this test, we just kind of wanted to make sure that because when you're transferring food, it's it can typically, accidents can happen. So we wanted to make sure that both parts of our plate, both the base and the lid attachment, would not like be damaged if it was dropped. And so in order to do this, we took the both the plastic base and the aluminum top, and we dropped them from two main heights. So first we dropped it from 1 meter, and then we dropped it from 2 meters. And so after each drop, we just kind of recorded whether it was damaged, dented, scratched. And so after about 20 drops for each of the parts, we concluded that no major damage was sustained during this. And so it would be safe and it would be durable if the client had or the caretaker had dropped it. And so finally, we wanted to we wanted to be able to provide to our client instructions for using this plate. And so in order to do this, we wanted to know what was the ideal temperature that the client would need to heat the water to in order to keep the food warm for the hour. Because that is a major part of our plate, we need to know how hot the water needs to be in order to be safe, but also to work to their needs. So to do this, we tested initial water temperatures of about 50 degrees Celsius, 68.3 degrees Celsius, and 85 degrees Celsius. So what we did in this test is we heated the water to each of these initial temperatures, put it in the base of the plate, and then we put applesauce on top of the lid, and we measured the temperature of the applesauce over an hour. And so the yellow line that you see is the initial temperature of 85 degrees Celsius. The red line is about 68.3 degrees Celsius, and the blue line is 50 degrees Celsius. So as you can see, the temperature of the food using the 85 degrees Celsius water started out a lot hotter, but it did almost end up in the same place as the 68.3 degree water. And so for these reasons, we decided that a temperature of around 68.3 degrees or about 155 degrees Fahrenheit was ideal for heating the food, both for safety purposes, because it is not boiling, so the hotter it gets, the more risk there is with burning yourself, but also it would be able to keep the food warm for up to an hour. So now we kind of just have like a video to show of the demonstration of the product. To eat because it would start to be heated.
So for our conclusions and future work, we concluded that the aluminum disc cover did improve the heat retention of the water beneath the plate, and so we decided to continue forward with the design with the aluminum disc. We also found that a water temperature of about 68.3 degrees Celsius led to the slowest rate of cooling, measured by Newton's law of cooling coefficient, which is basically a number that tells you how slowly an object cools down. So lower numbers are better in this case. And so we had our lowest number of about 0.018 at this temperature. And so we decided And so then for future work, we're planning on adding a 3D printed handle, which would go between the deep dish plate and the aluminum disc, which would make it easier to pick up and hold. And so we currently have the 3D model for this ready, as shown in the picture. Additionally, we made instructables for how to build this device on the Instructables website, which you can view by scanning the QR code at the top right corner.
So thank you for listening to our presentation, and we are opening up for questions at this time if you guys have any.
Okay, great. So the first question from Garima is, how do you ensure that the water doesn't leak or spill while the client is moving the plate?
Yeah, so currently one of our future extensions is that we would like to implement like a Velcro attachment to both the handles and the base of the plate, so that the lid is secured on top of it, but also is not able to move around and create any openings while the client is eating.
Okay. Asks, is it possible to make the plate and the base in one piece that is filled through an opening?
So yeah, Max, you can go for this one.
Yeah, that's another one of our feature extensions that we are thinking of. We are thinking of potentially having an opening that's like the opening of a bottle that will have a cap that you can screw off to fill with water or remove water, and then you can screw the cap back on.
Okay. Scott asks, what kind of feedback have you gotten from your client on the design?
So for our initial 3 designs, we talked to our client. They were concerned about the design with the heating coils because they didn't want it to be powered by electricity, so we chose not to go with that design. They're also concerned about the third design of insulated material because it could cause risk of burn. But for the second design, they seemed to think that it would be a good design, so that's why we ended up going with that one.
Toyesh asks, how does the retention or heat retention compare to other devices like insulated bottles?
We have not looked into this yet, but that's definitely one of our future design studies that we'd like to do, is to compare it to other existing like insulated bottles, like you said.
Okay. Clarice asks, how does the current prototype prevent burns while removing the plate?
Okay, so to finish as a next step of this project, we were planning on putting in this handle, and the lid top here will go on top of it, and then you will hold it from the handle here. And since it's made of plastic, then you wouldn't be burning yourself.
Okay.
Yeah, so currently that is one of our concerns, because currently we can only advise our client not to touch the aluminum disc until it's cooled down enough to safely touch. But hopefully with these handles, you'll be able to remove it while it's still hot and not be able to risk any burns.
Okay. A quick question here. Is the device dishwasher safe?
Currently not dishwasher safe because the temperature in dishwashers is generally too high for the heat that the plastic area of the plate can handle. So I'd say no for that.
And then a question from Kim. I noticed that the lid of the plate is extremely flat. It does not have a raised lip like a traditional plate. Is this an intentional design choice, or is this something you are looking to change in the future?
This is something that we're looking to change in the future, because we do recognize that it is difficult, especially if you have like pureed or almost more liquid food, that it is difficult to be able to scoop it up with a spoon without pushing it off the plate if it's flat like this. So we are looking into like different methods, like with our handle attachment, we would like to create more of like a curved up so that it's easier for the client to scoop and eat the food.
Okay, and last question. Rather than water as a heat source, have you considered the kind of microwavable substance used in body warming devices that retain heat and can be sealed, i.e. heating pads for sore backs?
Yes, we initially, as part of our process of initial brainstorming, we were thinking of many different ways that we could provide heat, which also included sealed package containers. Like we also were considering like hand warmers, for example, which was kind of similar to what you're mentioning. But we decided that water would be like the easiest, probably the easiest, cheapest, and most commonly available material that we could use.
Okay. So I'm going to ask that the group continue to answer questions during the chat. There's a question from Julia and a question from Neil, but I'd like to have the next group get ready and begin their presentation. The next group is called A Fresh Scoop, an adaptive device for dining with hand tremors by Anika, Nina, and Aki.
Hello, everyone. Thank you so much for coming today. It means a lot that you're here to see our designs that we've been working on. So my name is Anika.
My name is Aki.
I'm Nina.
And this is our anti-tremor spoon. Oh, okay. So our problem that we were given was that many people who suffer from hand or elbow tremors, they experience difficulties while eating food because as the tremors are occurring, the shaking of the spoon knocks food out of the utensils. Though there are numerous spoons that are actually on the market, they're often too expensive. And so some existing spoons require too much maintenance while others are too heavy for others to use. So our target audience is anyone who's suffering from tremors. It doesn't matter if they're light tremors or heavy tremors. And these individuals can either be independent or dependent. When we say independent, that means they could be living on their own, or basically that they can eat their food by themselves despite the occurrence of tremors. And individuals who are dependent means that they have a caretaker who would help them out with eating. So that could be someone, a family member, or maybe they're at a certain place where a caretaker is provided for them. So while doing some market research, we found some competitors. The main one is Liftware. This is very popular amongst many people, and it significantly reduces tremors because it creates a shaking motion through that main body that you see on this is the leftmost prototype here. And it's that shaking from the actual body of the spoon counteracts the tremors. And though there are numerous electronic parts, it can actually be extremely high cost. It costs up to $200, I believe. And it's very high maintenance because if it falls, it will break really easily. And if it runs underwater or is exposed to any moisture, it will stop working. The second device that we found was a swivel spoon. Now this is cheap, and the way that it works is that as the user, as their tremors occur, the spoon actually swings slightly to stabilize. However, it doesn't hold a lot of food, and it's not as effective as the walls of the bowl of the spoon are very shallow. The third model is actually the weighted spoon. Now this looks like a normal spoon, and it actually has a lot more weight in the handle of the spoon to kind of counteract the tremors. However, it requires the user to hold a lot of weight, which can be very difficult for a lot of people, especially if they have reduced motor skills. And we also saw that it isn't as effective as, say, the Liftware spoon is.
Okay, so in terms of requirements, we have 4 level 1 requirements. We wanted it to hold at least half a tablespoon of food, and we wanted it to keep 90% of the contents in the bowl of the spoon when an average tremor is occurring. And in terms of how big it is, we wanted it to fit into an average bag, and we also needed it to follow health codes and safety protocols. In terms of level 2 requirements, we wanted the spoon to cost $25 or less. We want it to be affordable for most people and for more people to have access to the spoon. We also needed it to be easy to grip for those with reduced motor skills because many of the people who are suffering from tremors also suffer from reduced motor skills. We wanted it to be dishwasher safe, durable, include instructions on how to use it. We also wanted the material to be able to last a year, and we needed the user to lift 0.25 kilograms to their face. And for the third level requirements, we wanted the bowl to fit comfortably in someone's mouth. We wanted the spoon to look no different from an average spoon, so someone can feel normal while using it. We wanted the spoon also to be usable by both left-handed and right-handed people, so you didn't have to be specific-handed to use it. And we also wanted it to be both usable by independent and dependent users.
So after deciding on our requirements and looking at some of the competitors, we started like drawing some preliminary designs just on some ideas that we had. So our first one was the lipped spoon. Excusing the bad drawing, it's essentially just a normal spoon with a lip over the bowl that would, like as the spoon shakes, the spoon would hit the lip and fall back inside, preventing most of the food from flying out. And our next idea was a rotating spoon similar to the swivel spoon. As the handle would rotate with a person's tremor, the spoon bowl would remain stabilized. And our last idea was a little bit higher tech compared to the other ones. It was the shuttered spoon, where essentially there was a button that would open and close a shutter. And as the person was carrying the food to their face, the shutter would be closed. So in transfer, the food would not be flying out, and then they could push the button to open it once they got to their mouth. But we quickly decided against this because people who have low motor skills, this would be really difficult for them to use.
So here, as you can see, we have our CDR design. So basically what this is that it's the design that we first designed with our 3D modeling software. So basically while this was working, we saw that we had created a rotating handle where the handle basically, it rotates with the tremors, but the actual stem of the spoon, which is shown here on the left, it doesn't move, it's stable. So we found that the lipped spoon that we had originally thought that we would do, it would make it uncomfortable for many people to eat. And that the button that we also had previously thought we would do, actually, the users wouldn't have the motor skills to actually hold down a button for an extended period of time and then release it in order to eat. So we had to scrap the lipped spoon as well as the motor, as well as the button, and we decided to go with our rotating spoon. So this rotating spoon has no electric parts since we wanted to make sure that it can be dishwasher safe and easy to maintain. And we also wanted to find a way for it to reduce the hand and elbow tremors, which is done by the actual swinging of the spoon itself. It accommodates for a wide range of motor skills, whether this is someone who has just started having hand tremors. So that means that they actually, that their tremors are light, that they're not that drastic, or for people who have, say, progressed due to aging or due to just the process of tremors becoming worse. Their tremors are stronger, they're more unpredictable, they're more drastic, and it still accommodates for that. So we added some weight at the edge here to at the end of the spoon to make it more stable so that while it's swinging, the actual head of the spoon would remain stable. So this is the actual handle of the spoon that we had found. Now this handle, it is bigger and it's a thicker grip so that it's easier to hold for people who have those reduced motor skills, because it's often hard for people with reduced motor skills to hold small things. So we wanted to make it bigger so that it's easier for them to hold. And so, as I said before, we wanted to make it so that it's easy for people who are dependent or need someone to help them while eating, or independent. So as you can see here, there's the right side, the right prototype that we have here. This is the top part of our handle, and it actually has a bottom part which is identical to it. It's just that the pegs on the top part fit perfectly with the holes in the bottom part. But basically it's a smooth exterior casing, which is for independent people so that they're able to eat on their own with a large grip. There's also on the left side a dependent handle, which has a slot for a caretaker to basically put their finger in and guide the handle to the user's mouth. So this just makes it so that the person who is eating actually, even if they're dependent on someone, they're still a part of the process. So they don't feel as if they're completely dependent on someone. But it's also some slot that actually works. We've actually had people from Seven Hills Foundation who work in the dining staff who have been able to say that this design is actually something that really works for a lot of people. Now, these two parts are interchangeable, so someone can buy both parts and say in the beginning, if they're completely independent, they can have both parts be completely smooth, no slot, and say as time goes on, they need to become more dependent on someone. They can interchange that with the actual dependent handle and not have to buy anything extra. The halves fit well together, but they give enough space for the actual spoon or the stem of the spoon to move. So that way, while the handle is moving with the actual tremors, the stem of the spoon can be stable and swing lightly and make sure that no food falls out.
Okay, so when we started building the spoon, we printed out what we had in CDR, and we found that the bowl of the spoon wasn't attached properly, as you can see in these photos. The first one broke, and the second two, they have half of the bowl of the spoon like hanging off of that neck. And so that was our first, one of our first changes after this. Our first change was that we realized that the CDR prototype only held half a teaspoon of liquid, which meant that we needed to triple the volume of it. And so that was our first change. We made the bowl bigger. Then after changing the bowl, we realized that it was too deep to comfortably fit in someone's mouth. So that was our next change. And so after that, we corrected both the depth of the bowl and the attachment of the neck. And then we also realized that the swinging could have been a little bit smoother. So we decreased the diameter of the cylinders at the top. We also realized during this process that the grip was sufficient for these tests. It was thick enough to be gripped comfortably, and the caretaker hole was also wide enough that someone could comfortably fit their fingers in.
So after that, we attached the bowl of the spoon better, and then we also noticed that the stem might be a little bit too long to be used comfortably. A user might have to raise their arm much higher above their head to get the bowl of the spoon into their mouth. So to counteract that, we decided to shorten the stem as shown in the bottom prototype, but that came with its own issues. The shorter stem made the spoon less effective in swinging and keeping it stable because there's less weight on the bottom. So to counteract the shorter stem, we decided to add little holes on the bowl of the spoon so that we could add small weights like metal bearings that would add more stabilization to the spoon while it's swinging. So this is our, the orange one there is the final product that I just showed you before with the short stem, and there's also holes on the edge of the bowl, which you can see better on the black one. And so after we interviewed caretakers of those who experienced tremors on a daily basis, they suggested that it might be a good idea to rotate the bowl of the spoon 90 degrees, which is the black model that you see here. And so that way the user wouldn't have to turn their hand while they are bringing the food to their mouth. They can simply bring their arm without rotating it in a different plane. And unfortunately, this didn't work as effectively as we thought. The uneven distribution of the spoon weight and the bowl was made the food like fall out much quicker.
So after taking everything into consideration, we finally decided upon a final prototype. And this was the spoon that had the long neck. We know that we have created the spoon with a shorter neck as well as the 90-degree spoon. And while those still had some incompetencies and weren't able to do the function as well as the main, the long neck spoon was able to. So we decided to make the long neck spoon the final prototype because it's more stable as well, and it actually held the most food during the duration or the simulation of actual tremors. So as said before, it has an interchangeable grip, so it can be made to be dependent or independent. And it has a big bowl that can still fit into someone's mouth, but it holds enough food and it's deep enough so that the actual food doesn't fall out of the bowl of the spoon. It's low cost of around $3 since we're only using mainly filament, which is actually, when you actually see for each prototype, becomes pretty cheap compared to, especially compared to the Liftway spoon, which was like hundreds of dollars. It's low maintenance and low tech. So it's easy to disassemble and you can put it in the dishwasher or wash it yourself by hand. It can be exposed to water and it's fairly durable as well. So our final prototype, basically what we had is, in order to actually test the spoon and to make sure that it's actually working, we had to simulate our own tremors, as you can see here on the left. So basically what it is that we had in the beginning, as mentioned before by the other groups, due to COVID, we had Dr. C print out our prototypes and then we had him test them and then we looked at it through a Zoom call. But after talking with some staff at Seven Hills, they said that tremors mainly occur either in the vertical plane or in the horizontal plane. So we simulated the two types of tremors that we had seen, and we did them with varying degrees of strength to actually see if it would hold food. And as you saw in the left on the video, that it holds food by keeping the stem will swing, but the actual bowl will remain stable, as you can see here. So no food falls out. And then on the left, we have the bowl, which is actually something that we developed pretty late into the process because we saw when talking to some of the staff from Seven Hills, they were saying how while scooping, the actual bowl of the spoon may swing back. So with the help of another STEM group, we were actually able to develop a plate which has a raised platform, as you can see on one half of the bowl. So that directs the food to the lower platform and actually makes it easier to scoop. It also has very high walls, which is something that we liked because while scooping, the actual bowl of the spoon will not swing back. So we didn't develop that plate. It was actually help from another STEM group, as I mentioned, who was creating their own plate, and they were kind enough to modify it for us. And then we were able to use it for our project so that it can be a system. So we could have this plate along with the spoon. So now when we look at the requirements that we had, which we had brainstormed in the beginning of the process, when we first got our problem, we made some requirements on what we wanted the basic spoon to have. So this is how our final prototype matches up with our requirements. Just to highlight a few, it keeps most of the contents of the bowl in the bowl during a tremor, which is something that we have done. It's portable and can fit in the average bag. And this is, we can disassemble it and you can have 3 parts. You can just put in a quick bag. It follows, it's cheap. It costs less than $25 and it's easy for those to grip with reduced motor skills. It is, in terms of dishwasher safe, we are currently looking at applying a resin. Of course, due to COVID, we weren't able to get that resin and actually have it placed, but we are looking to apply a resin on the actual spoons so that it will make the spoons dishwasher safe and easier to just pop in the dishwasher and clean. And for lasting a year, the actual filament, it can corrode over time, so it may weaken, or if it's dropped from an extremely forcefully, it will break, the joints will break, which is something we're looking into, to finding a stronger filament or finding a way to strengthen those joints. So these are our second list of requirements. Again, just going off of anything that highlights. The bowl fits comfortably into an average mouth. And it's one of our requirements that we did have was that it would look no different than an average spoon, but unfortunately we weren't able to fulfill that. But that was because we were prioritizing actually a functioning spoon versus the appearance of the spoon. We realized that the spoon must be longer and it must have that weight in order to actually make sure that the spoon is stable and that while swinging, the food will actually fall out. Now, this is something that we're currently working on. As you saw, we are trying to shorten the stem, but of course there are weight issues which we still have to figure out.
So in the future, we found that the final prototype was effective, but the stem was too long to be comfortably used and like eaten from. And so the longer stem means that someone would have to raise their arm higher to get the bowl of the spoon to be level with their mouth. And so we want to play with the length of the stem more in the next few weeks, just to make sure that we can get that perfect balance of stability and comfort when eating. And we also want to look more into adding weight to the bottom of the stem. We played with that a little before in our previous prototypes, but we didn't really find an effective way to add the weight into the spoon with seamlessly and have enough weight to substantially change the stability of the spoon. And in terms of the next 3 months, we also want to play with making the spoon dishwasher safe and more heat resistance so that it'll be even easier to clean, because we know with some reduced motor skills, cleanability is definitely an issue for a lot of people. And we also want to continue working with adding more weights. And another thing is we want to play with the grip of the spoon, because we didn't really touch that since we were more focused on the tremors of the spoon. But eventually we want to alter the shape of the grip so that if it is slick, we want it to have a good shape, maybe add some rubber so that there's less slipping likely to happen. And we also want to improve the ease of scooping, because that was also something we found during testing, was that it may be able to hold, the spoon may be able to hold food within the bowl, but there was an issue of getting a lot of food into the bowl initially.
So overall, some of the lessons we learned from the project was that communication is important, especially when we're working remotely like this. It's important to let everyone know what's going on with the project, since it is a group effort. We also learned the importance of testing and getting feedback on prototype every single iteration of every single design. It's good to test and get feedback so you know what to change next time. That goes along with the documenting work. So each iteration, just so you know what works, what didn't, in case somebody else wants to try the experiment as well. We found that it was easiest to focus on one problem at a time in each prototype. That way we weren't biting off more than we could chew, so to speak. For each iteration, we tried to fix one thing that we didn't like about the previous one, and that really worked for us. And overall, we just learned the process of designing and engineering a product. So now I think we'll be answering questions.
Okay, wonderful. Thank you. So the first question comes from Joy. Is this product food safe? If not, how would you go about making it food safe if you continued working on this project?
So the models were printed with PETG filament, which is food safe, but so far it's not dishwasher safe yet, which we are looking to improve upon in the future.
Okay. The next question comes from Scott. Are there any design options that might make rotating the spoon lowest curve of the stem near the spoon rather than the spoon bowl itself make any difference, especially in shortening the stem?
Sorry, I was trying to edit that question and it leapt out before it was right. So what I was really wondering is, or you answered the question I was typing. I'm curious, the rotating of the spoon bowl 90 degrees would seem to be very valuable. Are there other ways you might try and do that could be successful? I know the first effort you made was not successful, but any ideas about how that might be accomplished?
Right. We were thinking about changing the location of the bowl of the spoon in relation to the joint, just so we can improve upon the balance of the model, because right now it was too heavy on one side. So we think if we play around with the location of the connection, it might improve that. Another thing we thought about was that if we did rotate the bowl of the spoon 90 degrees, one way or the other, that would make it exclusively right-handed or left-handed, which we might be able to do for like a specific client based on their needs. But as of right now, we don't have a specific client, so we tried to keep it a little bit more general. But in the future, if we do get a person with custom needs, we can certainly change it based on their requirements.
Okay, so next question is from Kim. If you are still intending to add weights to the spoon, are you still thinking metal bearings? Would these be put in the mouth, or if so, would they pose a choking hazard?
So we added the holes on the very back end of the bowl, so it's unlikely that they would ever reach someone's mouth. And even if they did, we're planning on securing them very well with some sort of like food safe glue or something that can kind of keep them in place. So we definitely don't want people choking.
Right, and I think as Aki was saying, we're still planning on using metal bearings. So what happens is we're gonna maybe look into adding more metal bearings into our actual spoon. One thing that we had previously thought of was during the actual 3D printing process to pause halfway and to have some actual metal bearings put into the spoon and then continue the actual 3D printing process and finish it off so that they would be actually in the spoon itself to add more weight. We were also thinking of adding more than just one metal bearing into those holes. And another thing that we were thinking of is adding bigger metal bearings, so ones that have more mass. So we're definitely playing around with the metal bearings to see if it'll actually be a viable option in order to add more weight into the spoon while swinging.
Okay, go ahead, Joe.
So I'm kind of thinking, when you have that elbow, did you think of bringing the spoon up to the axis of rotation and then use the elbow to hang weights from, or maybe an elastic band to the table?
I'm afraid I'm a little confused.
So you come out of your handle and then you curve down and then you come up slightly. How about you come out of the handle, curve down, and come all the way back up. So the spoon is in line with the axis of rotation, but you still have the inertia of the long curve to dampen your motion. And then even you could use the curve of that curve to hook a weight onto, or an elastic band. Just a thought.
Yeah, we definitely haven't thought about that, but that's a great idea. We'll certainly look into it. Thank you.
Just a thought. Thank you.
Okay, so as we head into the next session, I'd like to share with you the lineup. You are more than welcome to stay. I know some people are coming in, coming out. I want to appreciate and extend my appreciation to all those who've attended and participated. I'll remind you again that we have an online Google form for your feedback if you'd like to share that. And I can give that to you shortly. Actually, that link is in the comments. But right now, what you see on session 2, which is 10:30 to 12, the first up will be Liftware Adaptation Redux of Noe, Emmeline, and Harsh. The second presentation will be the Wall Reacher project by Maria, Shane, and Avika. Third will be the Stop Alice by Neil, Shri, and Hazelin. And then the last one will be the Adjust-A-Cup, which is Anvi, Will, and Shri as well. I have also provided the link to the Google form here on the screen as also a QR code if you'd like to scan that with your mobile phone. And I will also put the feedback form link in the comments or in the chat room. But I want to appreciate and thank everyone who's been here. And we're going to end up starting on time. So if the first group, Noe, Emmeline, and Harsh, would like to begin, that would be great. And I will stop sharing my screen.
All right. Hello, everybody. My name is Noe.
I'm Harsh.
I'm Emmeline. And we did the Liftware adaptation device, which was actually a revision of a device that was done by a different group last year, just for a particular client who wanted some more adaptations. So the aim of this project was to engineer and deliver an adaptive device to allow our client who has tremors to eat independently. She currently uses a Liftware spoon, so we are not looking to replace the Liftware spoon, but rather add an adaptation to it to make eating a little bit easier for her. Although one was designed last year, she still had some needs that were not met, and she had a couple more requests for us.
So for a little bit of background on this, a tremor is a non-intentional rhythmic movement of a body part, usually stemming at a joint. So approximately 7 million people in the US actually suffer from some kind of tremor. Our client suffers specifically from elbow tremors, and she uses the liftware spoon in order to eat independently. This adaptation will be highly personalized as it's for her and her only. We require interaction with the caregiver in order to optimize the product. So a bit more on the liftware spoon. It costs $195, which is very expensive, which is why our client does not want to have to switch to a different product. And it prevents food spillage when a tremor arises by using a gyroscope, which moves this spoon in the opposite direction of the handle when the handle is moved in an abrupt way.
So the specific problem that our client is facing is that when she's gripping the handle, as shown in the image to the right of a liftware spoon, she's holding it in such a way that she's holding onto the gyro. This is preventing the liftware spoon from functioning, because how a liftware spoon normally works is it counteracts any tremor movements, but by holding the gyro, it basically turns into a regular spoon. And this makes transporting food from the spoon to the mouth really frustrating and embarrassing for somebody who has tremors. So our goal is to find some way to prevent her from holding this handle, holding the gyro and making the handle better.
So here are the requirements that we had. Some of them were given to us from our client, and some of them we came up with ourselves based on what we thought would be most useful in the device. So they're ranked based on level. So level 1 requirements we absolutely had to meet, whereas a level 2 or level 3 would be less important, but still a goal of ours. And they're also divided based on the type of requirement. So functionality, which is the actual purpose of it, the user, which is something that would benefit the user, physical, and cost. So we only had one cost goal, which was to stay under $20, which we did meet.
So our initial designs, we had 3. As Evelyn stated previously, we needed one of our prototypes to be non-3D printed. So our first design was an extendable handle using overlapping pipe pieces. So there would be no need to 3D print, and this could also be easily carried around because it could be extended out and then compressed back in. This would be harder to clean because of the amount of layers, and for the same reason, it could also be structurally weak because of all the moving parts. This would also most likely be the least comfortable of the handles that we've come up with, because it ends up in kind of a cone shape, because each overlapping piece of pipe is smaller. So this could be uncomfortable for our user. Our second design was a cylinder that simply went around the handle of the spoon and came with finger slots for our client. Now, this would allow for a steady and comfortable grip, and it would ensure that the fingers do not touch the gyro of the spoon. This would, however, require 3D printing and possibly not be dishwasher safe or food safe. So we had to make sure we were using the right materials, and it could also be hard to clean. Now, our third design was to clasp a ball around the spoon's gyro in order to completely block it off from the user's hands. This would protect the gyro, and it would also extend the handle and be easier to clean since we wanted to make it foldable. Due to the same reason that it was foldable, it would also be easy to transport. This would, however, require 3D printing, and also, again, we have to make sure it was food safe.
So back to the requirements, we evaluated each of those 3 designs based on the requirements. As you can see, the only one that actually did meet all of our requirements was the extendable handle, because it was not 3D printed. However, they all did meet the same number of level 1 requirements, so which was the most important. And so the clamp around the gyro and the finger gripping handle, the benefit of them being 3D printed was the fact that we could combine them, but again, they were 3D printed.
So after initial designs, we came up with a hybrid of design 2 and 3. We originally wanted to test these as different designs, but we were unable to. So we decided to instead combine them into one. So we have a handle that extends from the base of the liftware handle, and it also has a ball clasp going around the gyro in order to prevent the user from touching it. And because the liftware spoon was too expensive and we were unable to acquire one or acquire measurements for it, we instead found some other way to get the handle to go around a spoon. So the slot in the middle allows for flexibility within the plastic, and this allows it so it can be tightened with screws on the side, so that even if we don't know the measurements exactly of a liftware spoon, this handle will still work for it.
So design studies, the purpose of testing was obviously to determine the functionality of our device. Because we did not have an actual test subject who did have tremors, we simulated them to the best of our ability. And also, of course, ensure that our requirements were met for left and right-handed users. As for variables, our independent variables would be the hand used and the prototype used, which was done into different test sessions. Because we only had one prototype printed, that was the only prototype that was used, obviously, for testing. Dependent variables, obviously the mass lost from the spring, because that, the spoon, not the spring, because that was obviously the goal, was to lose as minimal food. Constants, the device that was used in each trial, in each session. The test subject remained the same because they had the same ability to simulate a tremor. And also the mass that was held in the spoon during each trial.
So the materials that were used during testing were rice, uncooked rice, our liftware adaptation device, and then our CAD provisional liftware spoon. Now, the reason we had to use a CAD provisional liftware spoon is, as stated before, that we couldn't get our hands on an actual liftware spoon. So the main difference between this spoon and the liftware spoon are that this has no gyro. So this is technically just a normal spoon that we modeled to the dimensions of, as close as we could to the dimensions of the liftware spoon. So how we tested was pretty much, we would take rice, 5 grams of rice every time, and put it into the provisional spoon. One thing we did do to the provisional spoon is make it a bit deeper of a bowl in the spoon so that it would try and make up a bit for the lack of a gyro. Then we would simulate tremors while making sure that we had a sturdy grip and that the handle was comfortable. And so we would then measure the mass of rice that fell out of the spoon and record. Now, one of the important things that we noticed in our first test was that our initial design was way too big. So what we did is we reduced the size by 30%, and it then worked fine with our provisional spoon.
Here we have our device. Now what it is you can see the finger holes here, the clamp to clamp around the spoon, and this is how you would hold it, with your fingers on the bottom and then thumb around the side and just holding tight. Because our client does not have grip problems, they have tremors, which means this is what happens with their hands. Here is our modeled spoon. Here's an example of rice that we used for testing. Now this is what would represent the gyro portion of the liftware spoon. This is about the same size, and the important part with this is that it is capable of fitting inside of this contraption and then being held tightly without moving. Now, as you can see, even with tremors, the rice is falling out because there is no gyro here, which is something that we still need to test. So our next step with this device is to test it with an actual spoon and a gyro and see if we have any adjustments to make, as it is quite possible that this is not the exact dimensions of the actual liftware spoon.
So this is our data table from the provisional spoon. We plan on making another data table just like this using the actual liftware spoon. And so as you can see here, we found that a total average of 31% of the rice fell from the spoon, even though it was a deeper dish. Yeah, deeper dish or spoon. So we found that it was satisfactory. The comfort and grip on the spoon was satisfactory, and that it did hold the spoon correctly, and that it would also not come into contact with the actual gyro, which is the main problem that the client was having. One thing that we would like to test, however, in the future was possibly to compare the two data tables, one with the provisional spoon and one with the actual liftware product, because it could give us some more information as well on what works better, a gyro or a deeper spoon.
So in conclusion, although we did not test properly with a liftware spoon, the handle was able to successfully allow the usage of the spoon without compromising the abilities. The finger holes in the grip did allow better gripping for this for the handle and allow it to be held more easily. Testing obviously was not done with a liftware spoon because we could not obtain one. So we used the deeper spoon obviously to compensate for that. So we didn't actually test the device that we were supposed to adapt.
So then some future extensions we would like to do is to test the same prototype but with an actual liftware spoon. And this will allow us to compare this data, new data, to the data we already took to see how our actual provisional liftware spoon would compare to a real liftware spoon. We'd also like to get real measurements of a liftware spoon so that we can remake our CAD file to fit exactly like with a liftware spoon, because normally right now it's just a flexible piece of plastic that can go around any handle about that size. We'd also like to coat the prototype in resin, because this could make it both food safe and would also make it sturdier and less fragile.
So the main takeaways we got from this project were that meeting outside of our class hours was very important. Things take a lot more time than you realize, and so it was really important to get those done. Definitely working to each other's strengths. We all have our strong suits, so in order to complete this project on time, it was definitely important that we all work to the best of our abilities. Obviously, communication, such that everybody is on the same page, is very important. And then definitely getting started from the PDR phase into actually designing in CAD and writing the documents up was one of the hardest steps that we had. For more information on the product, please visit our Instructables. We have nice detailed instructions on how it was made, how it works, and more pictures, more images. So thank you. Are there any questions?
Yes, we have several. So first question is, did you anticipate any other problems with adapting your current design to the liftware spoon?
I don't exactly understand what is meant by that.
Ryan, do you want to clarify?
Yeah, so I know you were talking about how there might be size issues. So I was wondering if you think there might be any other problems that you're considering right now.
Okay. Okay. So something we definitely have to pay attention to is we have to make sure the spoon obviously stays inside the contraption, and we also have to make sure, because we didn't have the actual gyro there with us, so we would like to make sure that the prototype doesn't come into contact with the gyro, because that is that's the most important part. Because without the gyro, it's just a normal spoon. So that would probably be the other issue that we'd have to make sure was clear.
Okay.
Also the curvature of the spoon itself, because we just base it off of photos mainly, but the curvature of the gyros and other part of it might be different than what we were able to recreate with our CAD prototype. So we possibly might need to change it based on that.
Okay. Next question comes from Toyesh. Does the extended handle cause issues with the moving spoon to moving the spoon to the mouth?
Okay, that is a good question. Now, it should not, because it extends the, as we said before, we had a prototype that was way too big. That one might have, because it was very big. But once we reduced the size, it should not, because it stays far enough back from the actual spoon part, but it's still short enough that it's not like you're reaching your arm completely out in order to get food into your mouth.
Yeah, and although there are finger grips in the handle, the benefit of having such a long handle is user has the freedom of how, like where they want to hold it without touching the gyro.
Okay. Elman asks, did you contact the manufacturer of the liftware spoon to see if they would give you a free model?
We did not. That's actually a very good idea. We did not think of that.
And also before while we were still like in school physically, we had someone who gave us a liftware spoon for a brief period of time, so we were able to see it and look how it functioned. But after that, we could not get it back from him. So that's why we decided to instead go with this idea, because we didn't have enough time or resources.
Okay. Does the user need to constantly be applying pressure to make the clamp stay attached to the spoon, or can it be attached semi-permanently?
So the adaptation does get attached with screws to ensure that it is clamped on sufficiently.
Right, so on the left and right side of the handle, there are screws which allow it to be tightened as much as needed.
Okay, Hima asks, are there any additional tests that you would want to run when you can meet with your client? Do you plan on continuing to iterate the device based on how it works specifically for your client?
Yes, because as we were saying, this is a highly personalized product. So for me, at least, especially with the finger holes, I don't know if there are maybe a certain size that she would prefer, as well as just the size of the product. If if we could shorten the handle or things like that. So I think there are small things that could definitely change once we meet with our client. However, I don't know if we are actually allowed to meet with our client. We actually have to go through a caregiver. So that makes that a bit more complicated, but there are some things that we would like to change.
And while we were able to meet with the caregiver of our client before this situation, we did get feedback on the design, but we weren't able to get feedback on our final prototype. So that would also be something to look into.
So I'm going to ask the group to continuing answering the questions that are in the chat room, and we will end up going to the next group, which is the Wall Reacher Project. Maria, Shane, and Avika. Their Wall Reacher project comes from Easter Seals. And Maria, Avika, and Shane, are you guys ready?
Yeah.
All right.
Hi, I'm Maria.
I'm Advika.
I'm Shane, and we had the Wall Reacher project. So basically a quick overview of the problem we were trying to solve. The problem is that individuals who have movement constraints from the waist down often find it very difficult to reach items which are high on the wall. So that makes it difficult to adjust or take down or put up items like frames or clocks or things like that, which may need to be adjusted for whatever reason. So for example, clocks, twice every year for daylight savings time, they need to be adjusted. And so people, for example, people in wheelchairs cannot reach these heights, so they cannot make these adjustments. And so our goal was to engineer a device which would allow people with these movement constraints to successfully take items off of the wall and put items back on the wall safely. And this would mainly be for people who have movement disabilities in the lower half of their body, which make it difficult for them to reach high in the air. And so the previous slide was just a table representation of all of our requirements. And this is kind of a summary of that. So the first one is our device should be able to remove an object from a wall. It should be usable by people with movement constraints from the waist down. It should be able to deal with multiple types of objects, so clocks, picture frames, etc. It should be able to reach high enough, so desired heights. It should be safe, and it should also be reliable.
So for the very first design that we came up with, this is a 2-part latch system. So basically what this means is that it'll have 2 parts. One is the latch, which is something that would attach to the back of the object. So the back of like the clock or the picture frame or whatever it is that you're trying to take down. And the second part would be the shaft. So basically this would lock into the latch part. And so the pros of this is that it would be very secure in the sense that it's clicked into the latch. The shaft is locked into the latch. So it definitely would be easier to maneuver the object around and it won't fall off. You won't have trouble with the object being unstable. However, on the con side, it is a 2-part device instead of 1 part. And also since the latch has to be attached to the back of the object, you would have to do this once first for every single object that you ever plan to take down or to put up. So you would only have to do it 1 time to put the latch on the back. However, you would have to do it for every single thing that you ever plan on taking down or putting up. So the second design, this is one that we first brainstormed initially before meeting with our client. So we sort of came up with this before we had a clear idea of what exactly the engineering goal of our design was. So for this design, it's designed sort of in a way that would be less, it would be less stress on like the wrist because we weren't exactly sure what the actual the project was back then. But basically this is a 1-part system in which you have the shaft and the head is a suction. So the suction would essentially just stick to the surface of whatever object it is that you're trying to remove. So if it was a clock, it would basically just stick to the surface of the clock or stick to the surface of the picture frame or whatever it is. And the pros for this is that it's 1 part. So it's easy to like store away and it's easy to use. However, the con side is that since it's only a suction, we figured it'd be very unstable and very difficult to be able to maybe stick to different types of surfaces. And no matter how strong the suction is, it is only a suction, so it's not necessarily very secure. So it won't really stick well to an object, making it easy to maneuver. So we figured that this probably wasn't the most secure option. And then the last option, this is most similar to the way existing reachers are right now. However, the way existing reachers work is that a lot of them are usually catered to moving horizontal objects, for example, things off of like tables and stuff like that. So we were planning on finding one that caters more to grabbing objects vertically, like against the wall. And then in addition to that, adding a wedge on the edge of the head. So basically on one side of the head. If you picture the head as like a claw with 2 sides, the wedge would be on one side, and the purpose of it would be to slide underneath the clock or the picture or whatever the object is, and it would slide under to prop the object off the wall slightly before grabbing onto the object to make it easier to take off. And in addition to this, we thought of maybe adding a spoke to it because after discussing with our client, we realized that was sort of one of the requests was to maybe have something that could be easy to make it take off like fire alarms off of walls or off of the ceiling and things like that. So one of our initial ideas was maybe having a spoke that could assist in doing that. So the pros for this would be that it's 1 part. However, it is definitely more secure than the suction cup idea. However, not necessarily as secure as the latch idea.
So moving from PDR to CDR, in this phase, we had to create concept models for our ideas. So our concept model for design 1 was we switched from kind of like a shaft to sort of like scissors. So essentially you would stick the shaft into the latch and then you would expand and essentially that would grab onto the sides and that would be very secure. And then you'd be able to take the object off the wall. The pros and cons to this are very similar to the way they were in the PDR. However, there was an added complication where this would be a little bit more difficult to use potentially, and also a little bit more complicated to actually build. So we decided to not go with design 2 going forward because of the fact that, like Advika said, it was just not very practical and the suction would just not be strong enough likely to continue. So for design 3, we moved on with this, and this was this is a picture of the concept model we came up with. So we used an existing reacher that we already had at home, and essentially took a piece of cardboard and put it onto one of the sides just to make sort of a concept model. And then it turned out that this made it much easier to take objects off of a wall, because that wedge was able to slide behind the object before it was able to clamp, and then you could take it off very easily. Now there still were obviously some flaws with this because of the fact that this is just a concept model. However, we dealt with these in the next steps.
So now we had to actually make our final product. So first we had to consider both of the designs, design 1 and 3. So the scissor design versus the wedge design. And after we reviewed the materials and we reviewed the feasibility of each design, we decided to go with design 3, which was the wedge, because we considered it more practical and easier to use on the user. So now that we picked a design, we had to find the materials we were going to use. So on the side, you can see this reacher, and this is an existing reacher that we bought, and it operates with a button. So when you press a button and you squeeze the handle, you can let go of the handle and the reacher head remains closed. This was ideal because our client did mention wanting a button operated reacher. And then we got an aluminum sheet to act as a wedge, which would be flexible enough and while also being durable. So then when the parts actually came, we were hesitant about the suction cups of the reacher that it came with, but when it actually did come in, we realized that it was thick plastic and durable, so they were not like normal flimsy suction cups, so we use that. We also considered ordering fabric to cover the aluminum sheet that would act as a wedge, but when we tested this out, the metal sheet became too thick and wouldn't slide under the frames. So now we had to actually assemble it. So going from CDR, our concept model, to now our final product, we had to add this wooden wedge, because when you attach the metal sheet just to the reacher, taking off the suction cup and screwing it in, it becomes too much of a wide angle from the vertical. We found that to be a 38-degree angle, but after testing different angles, we found we cut a wedge that was at a 12-degree angle from the vertical, and this is just enough for it to be able to slide under the frame without getting caught on the wall, while also being able to prop the frame off. So first you just had to drill the hole into the aluminum sheet, make the wedge, and then screw it all together and test for final functionality. So this is just a picture of the final assembly and all of its parts. So the reacher is 32 inches in length, which we thought would be sufficient enough and could reach high enough up the wall. And that's just like close-up pictures of the final prototype and what it ended up looking like. And here's just a video demonstration. This is putting an object on the wall, a heavy frame. We did have to flip over and have the metal sheet on top because we found when putting objects on the wall, it tended more to just get in the way, but by flipping it over, it didn't cause any problems. So it worked that way. And then this is taking a clock off of a wall.
And then this is just the final requirements for our prototype or our final design. And so everything, all of our level 1 requirements were met. The only maybe was hanging multiple objects, different types onto the wall. And that was just because of different backings. Like certain backings, like if you just have a hole at the back and you have to match the hole with the nail, that caused some complications and would require a redesign. And our design currently cannot take off fire alarms, but that would be a future extension in a different design.
So for the final prototype, so in order to use it, there is a red button at the bottom where the grip is. So in order to open and close the head or the claw of the reacher, as you could call it, you would basically just squeeze the like lever at the bottom. And then there's a red button to, once you grab onto the object, if you press the red button, it'll lock that head in place so that it is holding on to the object very stably, and you won't have to keep on grasping the lever. So you won't have to constantly squeeze it. You can just sort of click the red button and then it'll lock it to also have a secure grip on the object. And then also you would press the red button again to remove your grip on the object. So this would be more for taking or putting objects onto the wall. Once you put it onto the wall, to release the grip of the head from the object, you would just press the red button again. So sort of as Maria was highlighting in the demonstration, in order to put an object on the wall, you would have to have the metal wedge on the top of the object, so on the surface of it, not underneath, because if it is underneath the object, then it would, as Maria was saying, it would probably get in the way of the object when trying to put it on the wall. However, to take objects off of the wall, you would want to definitely use the wedge underneath, because that's sort of its purpose, is to prop it off the wall prior to grasping it and removing it from the wall. So there's just that slight usability use, is when you're putting an object on, it's wedge in front, and when you're taking an object off, it's the wedge underneath. So for future work, so the first thing would probably be the ability to replace fire alarms from the ceiling. And this is because this was one of sort of like the requests that we had from our client initially. However, the problem was that we realized as we were making our model that in order to account for this, we would have to sort of thoroughly change our design and almost make it like a completely new thing, as that that requirement wouldn't exactly fit what we had designed. So the other thing would be to strengthen the grip on larger objects, because as of now, the Reacher does work very well on a very diverse range of objects. However, we did notice that as the objects got heavier and heavier, it did get less and less stable when grabbing onto. And so the last thing, slightly less important, but would definitely be to make it foldable and easily compacted to be stored. As of right now, it's just sort of one long reacher, which can be stored almost maybe like a broom. It's not that difficult, but definitely being able to fold it up and put it away in a smaller space could definitely be useful. So some of the lessons learned. So it was kind of difficult doing this project online, obviously, because we could not all be together to work on something. It was more just one person who had all the parts. However, we realized that as long as we kept communicating and sort of making sure that everything was going well with the design and sort of keeping each other up to date with exactly what we were doing, then we realized that that was sort of a really key thing that helped us move forward with this project, even though we could not all construct it together. And the second thing would definitely be consistent productivity. So basically making sure that every single week, every single time we met, we had our goals for each meeting. We had our goals for sort of the entire project, for when we had to do what, and just making sure things got done efficiently. So any questions?
Yes, thank you. So there are a couple of questions from Catherine. Can the length be extended?
It currently cannot be, but that would be a future extension, going along with making it compactable.
Okay.
And that also has to do with the type of reacher that you use, since we bought a pre-existing one.
All right, and then she goes on to say, I'm not sure any of these have the dexterity for me to be able to turn a calendar page. What do you think? Is it possible to modify the object or modify your device for individuals with a range of dexterity?
So we haven't thought of something like turning a calendar page like with the actual reacher, though perhaps like depending on how the calendar is placed, what you could do is like take the calendar down and then flip the page and then put it back up with this type of design. But I feel like flipping a calendar page with the reacher itself would be quite difficult with
Yeah.
the current design.
We did focus more on like frames and clocks and things like that, because with every different object that you try this reacher on, you have different challenges depending on the backing, depending on the size and shape. So along with like our future extensions, we want to just try to make different heads for the reacher, and it would be able to be used on a wider range of objects.
Okay. Julia asks, how would weight or balance of the overall product affect the usability?
So the actual product as of right now isn't heavy, if that's what you're asking. So basically, like as the object gets heavier, it sort of, as I was saying, like makes it more difficult to use, but like still, it just makes it like a little less stable, obviously, with like heavier objects. But the actual reacher itself isn't heavy. I'm not sure if that answers the question.
You would have to, especially with the heavier objects, like Advika said, if you remember in the first video, it was a wide, heavy frame, and it was like wide. So if you don't hold it with two hands and like maintain your steady grip, it can get top heavy.
Okay, thank you. Liv asks, do you see specific objects that your device would struggle hanging other than fire alarms?
So I feel like, definitely certain backings can make it quite difficult. So like a classic backing that you would say hang something on the wall would just be you put the picture frame up and then you kind of slide down until it kind of locks into place. However, certain backings on certain types of clocks or things like that, you actually have to like find the hole where the nail is supposed to be inserted into the back of the item. And that is, those types of backings make it slightly more difficult because if you're working from far away with a reacher, it might make it a little bit more difficult. However, it's not necessarily outside of the range of what the reacher can accomplish.
Sort of just adding on to what Shane said, like objects like that with the hole where you have to sort of aim it, that's not exactly something that like the reacher wouldn't be limited to like being able to hang those up. It's more if the object itself is difficult to hang up, then like those obviously you'd have to perfectly aim it. However, the reacher would be able to get it up there. It would just probably make it more difficult because of the fact that you can't see the hole. So not really as much to do with the device, but more to do with like the fact that the object is difficult to hang on its own anyway.
So Catherine also continues with the idea about the fire alarm. As a wheelchair user, are you sure the fire alarm issue was putting on or off? I bet the spike was just to reach the center button to test, and I have never been able to do that. A spike would be useful for reaching number pads, alarms, etc. Could you speak more to how an individual might be able to reach a fire alarm and change a battery on a fire alarm and so forth?
So when we had initially put the spoke, it was going to be, so the spoke would be, or sorry, let me start over. There would be a second device almost that you would attach around the fire alarm. And then you'd have like a ring where the spoke would like go into. And if it was one like the twisting fire alarms, you could put the spoke in, twist it along, and then the fire alarm would just like sit on the spoke. And you could take it down that way and put it back up like that.
So if I'm not exactly sure if you're asking about this, but if the issue is just like say pushing a button that's high up in the air, like you said, number pads or something like that, or the center button on a fire alarm, then definitely the spoke would be very helpful. We didn't quite think of it that way, but that's definitely something we would consider doing to the design.
I think also the aluminum wedge could potentially work in if you wanted to press things and things like that. But yeah, like Shane said, a spike would definitely be helpful.
So question from Noe, do you think it will be important for your client to try different prototypes or just one? I know that it can be user preference, but what you may like may be different to them.
So I'm pretty sure our project was kind of meant to be more of a general thing for many different types of people. So it's not necessarily as personalized. However, definitely getting user feedback is something that we would really like to do, because that is something we have not done yet with our object. So.
So then I'm going to ask your group to address some of the additional questions in the chat room while the next group begins. And we have the Stop Alice group, which is Neil, Shri, and Hazelin.
Hi, I'm Hazelin.
I'm Neil.
And I'm Shri, and today we are going to be presenting Stop Alice, a better barricade for users with limited mobility. All right, so the problem statement: in today's world, active shooters are unfortunately a common problem, and it is important that all individuals be prepared for an active shooter situation. For many individuals who use wheelchairs, it can be difficult for them to barricade themselves into a room when needed. So the goal of this project is to design a device to help these individuals who use wheelchairs or have reduced arm strength quickly barricade a door to hinder the entry of an active shooter or any unwanted individual.
So before we began the project, it was important that we took a look at current competitors on the market to understand how best our product would fit into where other things have been covered. So what we found is that many current emergency door lock devices on the market are aimed towards schools and would only help lock one specific type of door. While these products could be useful for school administration who could buy one type of product to service the entire school, these products are often not viable for personal use because of how specified they are to a certain type of door. In addition, many commercialized devices do not abide by fire codes and additionally adhere either very high or very low on or around the door, meaning that if a user didn't have full mobility, they could be trapped inside the room if they were unable to access the device. Adding on to that, while door barricades for personal use do exist, oftentimes these take a good amount of time to set up and are more of an additional precaution to be put in place in addition to locking the door, rather than a quick solution to a problem. In a situation where someone needs to secure a door quickly, they're likely not going to have those 5 or 10 minutes to go through the setup that many of these devices require. It's imperative that our emergency door lock functions quickly and is relatively intuitive to use when every second counts. Finally, one concern brought up in the initial phase was the requirement for a device without any permanent installation or alteration made to the surrounding door or wall. Some apartments do not allow those who live there to make alterations to the floor or doors there. But in addition, we also wanted our device to enable the people who use it rather than require them to rely on an outside source for installation.
So moving on to the requirements, our level 1 requirements and top priorities were, of course, having the device be accessible to users with limited mobility. We wanted the device to be activated as quickly as possible and as intuitively as possible, as during the situation in which our device would be used, every second counts. We also wanted our device to work on both inwards and outwards opening doors. If possible, we also wanted to create a device which did not require the user to constantly apply a force, because this would enable the user to evacuate the area and get to safety if possible. Finally, we wanted the device to be both portable and usable with one hand. So our current prototype is both of these. It works best when stored by a specific door, and it does not require any permanent installation. Both methods of use for our final prototype can be performed using only one hand. But one requirement we did not meet was the ability to make the device more compact. We do hope to implement this feature in the future.
Our first device was the standard wedge. The picture we're about to show is just a very early concept of design. It is not our final prototype. So the concept for this device was originally proposed by our client. The extended handle makes the device accessible to users with limited mobility. And we also wanted a way to secure the door shut and have the user be as far away as possible.
I was not.
We had in mind that the user would be able to support the device with force from the wheelchair, therefore allowing them to keep a safe far distance from the door and then evacuate the area and move safely away.
Okay, so when building this device officially, as you'll see in a bit, we attached a 3D printed wedge to a PVC pipe, and the handle was part of a second iteration of the device and was designed in CAD and 3D printed.
The takeaways from this first design, we found that this device was quick and easy to implement and set up. An addition that we wanted to make was to adapt the device to serve for both inward and outward opening doors, as currently it only protected towards inward opening doors. Additionally, we wanted to create different attachments for the bottom of the wedge so that they could adhere better to different types of flooring. We ended up using Dyson, which has a very high coefficient of friction and adds a lot of grip against hardwood floors. So that was one of the attachments that we were able to make. And we also wanted to make a handle for better ease of use.
So our second design was the over-the-door barricade. When creating this design, we wanted to make a design that would work for both inwards and outwards opening doors because a device that functions for all types of doors is extremely important. Its security for outwards opening doors, however, depends on the length of the attachment in the middle. We chose to have it secured to the doorknob or door handle because this is a central location on the door that would be accessible even to users with limited mobility who might not be able to reach the very top or very bottom of the door. This prototype is also quick, easy, and intuitive to use.
So in order to build this device, we tied a 550 nylon paracord around a 1-inch PVC pipe. And so the knots that we used were a clove hitch around the PVC and an overhand loop to accommodate the doorknob.
So what we were able to take away from this device was that the strength of the attachment in the middle was a top priority. For our initial design study, we used string, but we decided to switch that to paracord for the final product in order to maximize security and strength. Additionally, the length of the rod of the device was also important because we needed the prototype to be able to extend across the entire width of the door frame.
Our third preliminary design was the reverse wedge. In creating this device, we wondered whether we could provide additional support to the door by moving the wedge farther away from the door and flipping the design of the standard wedge.
So after the second iteration of the standard wedge, the handle could also function as an attachment that would secure to the door. So the device was the same as the standard wedge, but it was implemented in a reverse orientation so that there was a different distribution of force across the device.
So this device required the user to be right next to the door for a long period of time when setting it up. The device was also difficult to set up and was not able to withstand as much force as the standard wedge. As a result, we decided that the standard wedge was a better approach to the wedge idea rather than reversing it.
Our final design was a combination of the standard wedge and over-the-door barricade and can be used in both ways. Dyson on the bottom of the wedge means that it grips to the floor and can withstand over 90 pounds of force to the door standing on its own. Due to the current situation, we were not able to test over 90 pounds of force for fear of damaging doors or materials.
So the materials that were used to create this final device were a 1-inch diameter PVC pipe, 550 nylon paracord, an adjustable joint fitting for the PVC pipe, Dyson, and PET filament. Additional tools that were used to create this device were a 3D printer, sandpaper, super glue, a saw, scissors, and also synthetic grease.
All right, so here's a quick overview of the build process. So the first step is to 3D print the necessary materials, which in this case are just 2 units of the handle side, a wedge, and a rotating handle assembly piece. So to prepare the materials, we cut a 5-foot segment of PVC with a saw, and we used a jigsaw since it was on hand, but a hacksaw should suffice. Also, we cut an additional 4-inch segment for the handle, and a 2-foot segment of paracord, which we heated the ends with a flame to seal. You don't use super glue for this bit because that can cause a highly exothermic reaction, which can actually cause the paracord to combust. Believe me, we found out the hard way. Finally, cut a sheet of Dyson traced exactly around the wedge. So now we assemble the device by first assembling the handle as shown here, and then assembling the body of the device. Finally, we fastened a paracord loop around the device as explained prior, and if you're interested in building one, you can just access this document on instructables.com. Just look for Stop Alice and it should come up. All right. So we have a short video now that would show the use of the device.
So for the wedge on a stick, you'd want to grab the device from the area that it was being stored. And then you would hold on to the handle of the device as you approach the door of the room that you wish to barricade. And then once the bottom of the wedge is near the bottom of the door, you would insert the wedge in between the gap. And then you, by using the handle, you'd want to push it in as far as possible to secure the device into place. And then once secure, you would be able to move away from the device and protect yourself.
So our device also has the function of the over-the-door barricade, as you'll see in a second. To use the device as the over-the-door barricade, first you'll want to grab the device from the area that it is being stored in. Then you'll want to secure the open paracord loop around the door handle. The device should hang so that both sides of the PVC pipe are covering the door, and if necessary, you'll need to adjust the device. And then once secure, you can also move away from the device and protect yourself. So the first design study we completed was a time test. We were testing to see how long it would take to set up each device. One of our main requirements, as stated before, is that the device must be able to set up in under a minute. In a time of need, it's important to protect yourself as quickly as possible, and we wanted to see which device was the most efficient. We were able to conclude that the standard wedge consistently took the least amount of time to set up, therefore making it the most efficient device.
The second design study that we completed was a collapse test. We were testing to see how long each device could last against a large amount of force before the device moved or the door opened. Through this test, we were able to conclude that the standard wedge with Dyson was able to last the longest amount of time. This device was able to keep the door secured shut during the test, and it was able to last for over a minute, which is much longer than all of the other devices lasted.
Wow.
So the third design study that we completed was a materials test. We tested the standard wedge design with and without Dyson. During this experiment, we used an airport suitcase weight scale to measure the amount of force the device was able to withstand. And on hardwood floors, the device functioned better with Dyson and withstood more force, actually over 90 pounds. At that point, the entire door was prone to break before our device gave way. This is partially due to the fact that the stronger the force applied to the door by a would-be intruder, the greater the normal force and hence frictional force keeping the wedge in place. Furthermore, as the Dyson compresses, this force increases exponentially. In essence, the harder the intruder tries to get in, the harder the wedge works to keep him or her out.
To conclude, this device is functional. This device was able to withstand a large amount of force for a long period of time. And based on the design studies, the standard wedge works better on hardwood floors as the Dyson provides a lot of grip against the hardwood material. This device works on both inwards and outwards opening doors, doors that are raised a certain height above the ground, and any door with a doorknob or a longer handle. Our device is quick to use, relatively lightweight, and combines 3 different functions to allow the user to choose which method they would like to use to barricade the door. They could set up the standard wedge with the wedge in between the gap between the door and the floor, the over-the-door barricade by securing the paracord around the doorknob, or the reverse wedge by having the wedge away from the door and the handle against the door. But based on our design studies, we feel that the standard wedge with Dyson is the recommended way to use it.
So as for what we want to do with our device in the future, there are many more steps that we want to take towards improving our device. There's a lot of materials that we may not have had access to during this time that we would like to test. For example, the material the rod is made out of is something that we would definitely like to vary. We're using a PVC pipe right now, but we'd also like to try using aluminum. This metal is both strong and lightweight. Hopefully we would be able to test different materials for the rod and come to a decision on which is best to use roughly 3 weeks after we're able to work on the device in person. We'd also like to create multiple wedge attachments, each geared towards a specific floor material. Because the current Dyson works very well on hardwood floors and cement, but we want to look into designing some sort of material with spikes that can grip to the carpet to attach to the bottom of the wedge, or even just design a wedge with spikes that can grip to the carpet. These different attachments might take a little longer to develop, but we could likely complete them within a month.
Also, since Dyson functions a lot better when it's clean, we'd like to create an additional attachment to our device that would make it easier to clean the Dyson. When the Dyson is used on cement especially, it is prone to pick up a lot of dust that inhibits its function, and that is something that we discovered while testing. Again, this work could also be completed probably within a month. And a few final cosmetic and functional changes that we'd like to make to the devices are adding a metal tip to the wedge to more effectively deal with the amount of force placed on it by an intruder trying to open the door and creating a more secure way to attach the paracord. We've tested out a few 3D printed attachments to serve this function while also making the position of the paracord vary based on the user's door measurements. But also we want to look into possibly having a groove in the PVC pipe so that the paracord can sit there comfortably. Likely these small changes could probably be completed in 3 weeks at the most. And then we have the resources from our research and links to our competitors right there.
So I just want to thank you all. We just want to thank you all for your time. And when we started this project, our biggest question was, will it work? And it does. So right now, our biggest question has become, how can it work better? So what questions do you guys have about our work? Or maybe you guys have some answers. Please feel free to leave a thought in the comments or ask any questions in the Q&A. We're happy to answer.
Okay, so I think the first question that Catherine brings up, which would help make it better, is were you aware that doorknobs are less common than levers in accessible housing? Would the cord slip down the lever handle? I pull cords on doors to help close them, but cords often slip down for levers.
So that's a really great point and a really good thing to bring up. Because of the current situation, we haven't been able to actually test our devices a lot outside of our homes. So that is definitely something that we'll want to look into in the future, and possibly changing that attachment to better accommodate doors that use a lever as a handle instead of paracord, maybe something else that can attach to the lever. Thanks for bringing that up.
Hema asks, how heavy is the device? Would it be able to be moved and placed efficiently by an individual who may have upper limb mobility issues? How did you test it if you could be placed in under a minute? Wouldn't this vary based on the individual and their mobility?
So that's a great question. Neil, do you think you can respond to the stuff about the weight of the device? I know you did some research into that originally.
Sure. So with the materials that we had access to, we actually chose PVC partially because of how lightweight it is compared to, say, steel or aluminum, which might be stronger, but will also have an increased weight. So that's definitely something we considered.
And one of our future extensions is definitely going to be testing those different materials for the center piece of the part. And also, I know you mentioned how we tested like the time to set up. Our device was originally aimed mainly towards wheelchair users. So while we were doing the setup test, Neil sat in a rolling chair to kind of simulate that as best we could given the current situation and like the level in relation to the door. We didn't really have access to a lot of other ways to test that during this time.
But in the future,
go ahead.
We'd be more than open to reaching out to anybody who'd be willing to test the device and collecting data to further better it.
Balhan asked the question, how would you deal with the attachments if the user has multiple doors over different types of floors?
That's another good question. So our device was originally designed to be something that was kind of kept towards like one individual door with like the added ability that you could move it to a different door and store it there if that's what you wanted to do. So some way that I guess a user could help with that is to have multiple devices and just leave each one at a door with its certain attachment, or just have the variety of attachments and move where it is stored based on where they want to keep the device.
And since the wedges are 3D printed, it is pretty simple to make multiple of these wedges and then have different materials on the bottom of them to accommodate for different types of flooring.
Okay, so this will be the last question. Before then I'll ask all of you as a group to respond to the other questions that you weren't able to respond to. This comes from Julia. How does changing the length of the handle affect the effectiveness of your product? Would shortening or lengthening the handle affect the results greatly?
So that's another great question. Because of the functionality of the over-the-door barricade part of our product, it is essential that the device is long enough to fully cover the door frame because we need it to extend from one area of the door frame to the other to block the door from opening when it is in use. So it is essential that our device is long enough so that when it is hanging, it covers the entire door frame. As such, our device will not function if the length is too short.
Okay, so I'll ask your group to respond to the rest of the questions in the chat. We're going to end up moving to the last group in this session, the Adjust-A-Cup project by Anvi, Will, H, and Shri. Thank you very much.
Thank you. Thank you.
Thank you.
Hi, I'm Anvi.
I am Shri.
I'm Will.
And we had Adjust-A-Cup, which is engineering an adjustable cup that is suited for individuals with Parkinson's disease. So when we first started this project, we were designing a cup for an individual who has Parkinson's. So our client has tremors and they can't, so which makes it difficult for them to handle a cup. And they also have limited sucking ability, which makes it difficult for them to suck liquid out of the cup. So in our specific case for our client has lost their hand mobility completely. So their caretaker is at this point fully taking care of all of their drinking needs. So when we first started our project, we decided that our product would be only focused for our specific client. But after talking to our client's caretaker, we realized that there are several people with Parkinson's who aren't getting these resources that they need. And so we are deciding that our cup is designed for both individuals with Parkinson's who can take care of themselves currently and for those who need to depend on their caretaker.
So now we'll discuss some requirements. So the first is that there's a small bore for sucking and pouring. This is so that both the client can suck out of it and the caretaker can pour it. And this is basically a straw. Next, this is that it's easily and efficiently delivers water to the mouth. We didn't want any other aspects of our project to cloud this very important requirement. And then the next is that it's spill proof. So many individuals facing Parkinson's have hand tremors randomly, and we needed to make sure that the handle that we put in place could get through any hand tremors without spilling too much water. And then finally is that there's a controllable flow of water to prevent aspiration, which is when water goes down the breathing tube, and this could cause choking. Next, we have level 2 and level 3 requirements. An important one in level 2 is that it has to be easy to clean. And this was a major drawback of many competitors that we saw because they had weird designs and shapes that would be hard to clean. So this was something that we had to consider in making our designs. And then in level 3, we put cost effective, which is many patients or many families going through Parkinson's face this challenge. So our client's caretaker told us that it wouldn't matter too much the cost because families would be willing to afford it.
Okay, so these are some of our designs for the PDR, which is the preliminary design reviews. And our first design is on the left, which uses a curvy shape bottle. And though it has some dechargeable parts, some of it might be difficult to clean. And like the middle, if like every time you need to dump something into it, you need to open it, it's not really easy to use. Next, we have the squeezable bottle. And the problem with this is that it's difficult for flow control because it's difficult to assess the pressure you need to apply for the water to flow out. And lastly, we have the sippy cup kind of design at the right. And some of its problem might be straw cleaning. And also, we don't want to design our prototype to look a lot like a children's cup because we want to use it for adults. For the CDR design, so our CDR design basically has the handle in the middle, and cup shape pretty much doesn't change, but we do want to look into ways of control mechanism. This one uses a button to control the water flow. And this one has like the same basic concept, also the straw on the side and the handle in the middle, but we have a slider to control the water flow for this design. Okay, so proof of concept is for ideas of proving how our concepts in the CDR work. So in the top left, we used a simple straw attached to like a kind of bottle, and the water will be able to flow out the straw when the water level is higher than the straw opening. And we decided that, well, we should also try this for a bendy straw, because bendy straw can also serve as a way of controlling the water flow, because you can just adjust the height of the straw to be higher or lower than the height of the water in the cup to control the water to see whether or not it will flow out. So this is our proof of concept for testing whether or not the handle in the middle would work. And what we find is that it is really easy to get a hold of the cup, and it's really difficult to lose grip of the cup or let the cup fall out of the hands. And after meeting with our client, he thinks that this design would be suitable because it allows him or her to get a strong grip of the cup and feed the client. Okay, so going into our CAD designs, we decided to use 3D printing to construct our models. And it will basically be the shape we want it to be, because as you can see from the previous slides, that we want the handle in the middle design. And this is not really doable without the use of 3D printing. So making the handles feasible to construct is pretty much one of our main ideas or main reasons as to why we want to use SolidWorks to construct our prototype. And we have two different prototypes. One will be one will have like a hole that allows a detachable and bendable straw attached to it, and the other will have a slider as a control mechanism. I just want to add that like some of its dimension is that it's about 8 centimeters in width and 10 centimeters in height. And I'll leave it to Shri and Avi to talk about the functionalities.
Yeah, so thank you, Will, for taking us through the design process. So this is our first CAD design prototype. As you can see, there's a little bit of a hole right here, which is where we were intending to add the bendable straw. So the straw that we were planning on using is a metal straw, and you can bend it at any angle and at any part of the straw, which we thought would be pretty beneficial for our client and for anyone that needs a caretaker, because it can allow them to go through any angles that they may face, because typically when you have Parkinson's, it's kind of unpredictable to figure out what angle you're going to need to drink water at. So we thought that would be a good to have. So we also have a handle going through the middle, and that's mainly to prevent hand tremors for those that are currently using it for themselves. And also it makes it easier for caretakers to hold as well. In addition, we needed to ensure that it was spill proof. So we have a metal bar going through the top in order to ensure that the lid isn't completely open. In addition, as our main concern, we wanted to make sure that we were preventing aspiration as much as we can, which you will see through the design studies.
So our second prototype was very similar to the first, except this one attached a straw at the end that was printed out. And so the straw was designed above the top of the cup to prevent spillage. And also the handle goes through the middle like before. We attached a slider, but that was not done through CAD. We attached that mechanically outside of the straw, as we'll see in the next slide. And that also prevents aspiration.
So these are the final prototypes that we ended up having for today. On the left, you'll see prototype number 1, which was the first CAD design, and we actually referred to this one as the bendy straw cup. So one thing that we had to kind of encounter because of the whole pandemic going on is that we could not get the straw that we wanted in time. So we just used a household straw, but as you can see, there's still a bent joint over here. So we mainly tested with the angles to see how it would work in function.
And then on the right is the second cup. And we went through a few iterations of how to make the slider, but we couldn't get it inside the cup because the cup was actually printed a bit smaller than what we had originally designed. So instead, for our prototype today, we put it on the outside. So our first design study was to see if water was deliverable by both the client and the caretaker, which was one of our requirements discussed at the beginning. So we recorded in different positions how long it takes water to reach the mouth while the cup is held above the mouth at a constant height. Yeah, so the results of this design study showed that the water ended up traveling the fastest with the slider cup, except for when the individual was lying down, which is mainly because of the design of the straw. So overall, we concluded that the optimal cup for this particular design study was the slider cup. And this was a big deal because it ensured that our cup would work for 2 different target audiences. And then next, we needed to make sure that the cup was spill proof, even through tremors like we discussed at the beginning. And so for this, we test the cup's ability to maintain water at different angles. And we saw how much liquid spilled out of the cup at different angles. Yeah, so what we found from this test is that the slider cup spilled the least amount of water for any angle, which we could kind of predict it because you could kind of change how much we were getting out. So it prevented spilling the most. So our next design study is maybe the one that we were most concerned about. So we needed to check the flow of water because again, aspiration is a really big deal and we need to prevent choking as much as we can. So in this, we had our 2 different prototypes and our 2 different prototypes had different flow control mechanisms. So we ended up using 2 different experiments that would allow us to compare which one had the better flow rate. And I'll let Shri go on. So as you can see here, we have the, we recorded how much water came out and we also recorded the flow rate. And because of the 2 different procedures, we can't really conclude which one is better, even though we have data for it. But in the future, we hope to run some statistical analyses to see which one would be better. Yep. And we also wanted to include a 4th design study that we did. So this was actually one of our level 2 requirements, but we thought it was really prominent because when we initially met with our client, we saw that the current cup they were using, which is a kitty cup, it ended up growing a lot of mold because of the design of it, and it was really difficult to clean. So because of that, we wanted to make sure that our cup is very easy to clean, and we would have been able to better do that with a translucent cup, but we have some data for the opaque cup that we had. So because of the data that we found that the bendy straw cup was actually easier to clean. And one thing that might add to that was the shape of the straw was a little bit hard to clean in the slider cup because it was curved. And also the cup was a little bit small. So that's definitely something that we hope to fix in future iterations. So overall, our engineering matrix showed that the slider cup was the better cup for our particular client and for our target audience. So both of our cups met the requirement for having a small bore tube for sucking, which is basically a straw. And we also had methods for making it easily deliverable, easily delivering water to the mouth for both caretaker to client interaction and for simple client to client interaction. And we also ensured that it was spill proof, but we definitely think there are more iterations of testing to do in regards to this concern because we cannot ensure that it is 100% spill proof as we would have wanted it to be. And in regards to the flow of water, we can see that the first cup it can control the flow of water and it had a lower flow rate than the second cup did. So we see that that one has a stronger flow of water control.
Okay, so for the easy to feeder for feeder to hold, we believe that we satisfy this criteria because of the handle, and and this also satisfy the second criteria, extensive space between the handle and cup. And it's also easy for the user to hold because the user could, even though we designed this specifically for a caretaker, it's also easy for the user to hold on to the cup and grab onto it. It's pretty durable based on the material we made it in, but we can't not definitely say that because we didn't really have a design study to test that. And lastly, it's not see-through, and I feel like this would definitely be better if it's transparent or translucent.
And then going into some more requirements, it's pretty cost effective considering that we 3D printed it and then just used household materials for the other aspects of it. It can be angled for easy drinking, as we found through our design studies. The long handles was not applicable since we put it through the middle of the cup, and that can be changed depending on the size of the cup. And then we did not have measurements on the outside or make it writable.
So now we have a demonstration of our final prototype, and hopefully the sound. Okay. So through this, we test different aspects of when the slider is completely open, half open, and closed. And as you can see, it gets smaller over time. The completely closed doesn't completely stop the water, but that's definitely something that we look forward to fixing in future iterations. So we have a lot of work that we would like to do in the future to make sure that our deliverable product not only satisfies the needs of our client, but satisfies the needs of individuals with Parkinson's worldwide. So the first thing that we want to do is to somehow incorporate the stainless steel bendable straw that we wanted to use for the bendy straw cup. And we think that it might also help with flow control on the slider cup because the current straw that we have is a little bit more difficult to work with, and it might make for easier cleaning if we had the bendable straw in place. And we also want to work on editing the slider because, as Shri mentioned in the demonstration, the slider does not cause, there's no setting of the slider that can make it completely stop outputting water. So we might want to work on adding more settings or making sure that we can just find a way to get less leakage. And as for our long-term goals, we might want to find a way to maximize the volume inside the cup because currently it cannot hold that much. So we might want to do that by just increasing the size of our CAD file, which would also help us with making it easier to clean and making it easier to hold. In addition, we want to make it accommodating to all different types of users. So this means that we would add customized flow controls so that it would be able to be used by patient-to-patient interactions, client-to-client interactions, caretaker-to-client interactions, and maybe even for hand tremors in general, not just for those with Parkinson's. And then we decided that because of the two prototypes that we tested, that the slider was a bit more optimal, but that's definitely not the final case, and we have a lot more work to do. But for the slider model today, one of the important things that we have to work on is find out what type of slider to use. So because the cup was quite small, it was hard to put a slider inside. So we just put a rotational one on the outside, and that's definitely something to discuss. And also whether it would be more effective to have the slider inside the cup or outside. And then another one is, the second one kind of discusses level 3 requirements, making the cup translucent, adding measurements, and making it writable. And then finally, we want to design the slider on CAD instead of making it mechanically because we think it can be more precise and it can help access the handle and things like that.
Okay, so for lessons learned, one of the most important part of this project is collaboration, because in these uncertain times, which is like the coronavirus outbreak, our group was able to work over Zoom calls and stuff to together create first few iterations for our project successfully.
We also wanted to highlight that we learned a lot about communication through this project. Not only communicating with each other, but with our teacher to, especially in this time, like Will said, we needed to get our prototypes, figure out our CAD designs. So we wanted to thank our teacher for being so accommodating of all of that. And we also wanted to thank our client's caretaker for meeting with us so much, for teaching us about communication, and for all of their guidance. And then finally, we also learned about new perspectives that caretakers face, whether it be with just individuals going through Parkinson's or any other circumstances like that. We learned that it wasn't only the person going through that, but also the caretakers and the families that have a lot of responsibilities. And with that, we thank you for listening to our presentation, and we're now open for any questions.
Thank you. Thank you so much. Scott has a question. How complicated will the slider be to build, and how confident are you that it will be leak proof?
We think that if built correctly, and especially if designed on CAD and SolidWorks, I think it can be very effective, not only to control flow, but also completely close off water. But I think we'll need to run more design studies with this versus the steel straw that we get, just to see which one would be more effective. But I think it is definitely possible.
So Ohm has a suggestion. Would a camera aperture type of system work for the slider?
Yeah, so that's actually, that's something we looked into during our CDR requirements or CDR designs. We wanted to do something using eye control. So like when when you blink, maybe the slider opens. That's something we looked into. We just didn't think it would be possible with the time that we were given. So that's definitely a very interesting idea, and we'd love to look into that. Yeah.
So Maxi had asked a question. What inspired you to come up with the specific shape you ended up choosing for your final prototype, specifically the feature of having the hole in the middle of the cup?
Yeah, so I can answer that one. So what we actually wanted to do initially was we wanted to have a handle, but we were just planning on extruding it out further. But what we saw is once we met with our client, he actually gave us the cup that they were currently using. And the problem was that no matter how far you put the handle away, it's going to be uncomfortable for drinking. So we were trying to make it to best prevent hand tremors, which when you're wrapping your hand through the middle of the cup, no matter how much your hand shakes, it's really hard for you to completely lose grasp of it. And also for caretakers, it's a little bit easier to pour because there's a lot of different angles that you can kind of adjust it to.
Okay. Ashita has a question. Would the straw in the bendy straw cup be replaced with every use, or would the final product include a reusable straw?
Okay. To answer that question, we were initially thinking about using a stainless steel reusable straw that can bend throughout. And this will help the client adjust while trying to feed the water into the client's mouth. And it would not be replaced every time because we feel like that wouldn't be environment friendly, and it would not be good for the overall prototype.
And in regards to whether it's detachable or not, that's something that we need to do more testing on. It might make it easier to clean if it is detachable, but it might make it harder for the user to keep all of the ingredients, like the parts of the product together. So we would have to do more testing on that and see how that ends up working out.
Okay. Will B asks a question. Do you think that the size of the slider at the end of the straw would be a problem for the person drinking?
Yeah, definitely. It has to be, you have to like be able to reach it from the handle, which definitely depends on like hand size, which is individual, or which is like just particular to the client themselves. But yeah, the slider definitely has a lot of iterations to go through, whether it be where it's located or, as you said, the size of it. That's definitely something that we have to look into.
Yeah, I agree with that. And I feel like for our specific prototype, the thing is that our caretaker is feeding the client. So it wouldn't matter as much because they could just adjust it with one hand and hold it with the other. But to fit the general audience where we need to accommodate all kinds of users, the slider at the opening of the straw might not be the most suitable because it might be hard to drink from and hard to adjust.
Okay. There are some other questions on the chat, but I one just came up that I think would be important for you to address, since you addressed it in the body of your presentation. How would this cup, and this is from Clarice, how would this cup be cleaned between drinks?
Okay.
Yeah.
So basically, okay, wait, go for it.
Okay. So between drinks, I think the way we tested it was simply rinsing it using soap and water. We didn't run any dishwasher tests, but that's definitely something we can do in the future. And as I said, it was a bit difficult just because it was the cup is kind of small, but we can look at that.
Yeah, and in addition, if we make the straw detachable, that would also help with cleaning. So again, there's a lot of iterations that we have to make, but yeah.
Okay, so last comment from Gina Betty comes as a comment from your last question. The size of the prototype for testing ideas does not matter. It is, quote, the reduction to practice when it gets reduced to meet user needs. So that's a comment that I think is important for you guys to consider. It's okay to test a smaller prototype, but if you need to reduce your deliverable product to meet the user needs, then that becomes important. All right. I want to thank all of the presenters today and all of the panelists and attendees. I would like to remind that the last group to try and address some of the questions that have been unanswered in the chat file, the chat room. And we're going to end up breaking between 12 and 1 o'clock for lunch. And you are all welcome to come back at 1 o'clock for the third and the fourth session. So thank you so much for attending. I appreciate the feedback and all of the questions, and I will see you back at 1 o'clock. Thank you very much.
Should we stay and answer questions, Dr. C?
Yeah.
Okay. Yeah, I didn't know if it was okay. Yeah, we'll do it.
Yeah, if you'd like, if you take the last couple of minutes to answer questions, you can do that. But I think most of the questions have been answered. So just go through the whole list and address those.
Yeah, I can do Alex's unless you're looking at it.
Okay, I'm just doing Vinny's right now.
Okay. Do we have any more?
I'm just doing Jackie's right now.
I think we'll answer Jackie's.
Oh, did anyone answer Ishida's?
Oh,
Not
no.
yet.
I don't. Would we use the same material? Would it just be PETG?
I think
I'll just type up the response. I think I have an idea.
Okay. anymore. Okay, I think that's all. Okay, all right, awesome. All right. Bye, Dr. C. Thank you. Bye, Dr. C. Thank you.
Thank you, Dr. C.
Okay. Matt, you're up first.
Yes, yeah. Sorry, I think I was muted.
With Jeff and Hema.
Yeah, I don't know if they're on right now.
Pragya, your group is next. So I would get prepared and ready to go. Okay, good afternoon. Thank you for coming to the 2020 STEM 2 Assistive Technology Fair. My name is Kevin Crothers, and I appreciate you volunteering to come and listen to the presentations. The Assistive Technology STEM project provides Mass Academy students an opportunity to work with members of our community to identify and address needs. An assistive technology is any type of device that increases participation, achievement, or independence for any individual. Mission Empower defines an assistive device as being anything from a low-tech device like a magnifying glass to a high-tech device like a computerized communication system. Mass Academy students work with our community partners to engineer solutions that are small, low-tech, and easy to iterate. And in a regular design cycle, teams of 3 to 4 students are matched with a project that typically takes 3 to 3.5 months from receiving the request to developing a deliverable device. Consistent work and the iterative design process are essential for successful delivery. However, clearly this has not been a normal design cycle. Students have been working online for the majority of this project, collaborating over Zoom, remotely printing out prototypes and testing, and challenges in obtaining client feedback have been stumbling blocks during this term. Students have been able to show their grit, resolve, and perseverance in their desire to deliver a product worthy of the clients they are working with. Students see the importance of providing a working deliverable product and are willing to meet with their clients over the summer when restrictions in mobility have been eased. Each session, and this is session number 3, will have 4 presentations. After each presentation, there will be an opportunity to ask questions. I ask that each participant keep themselves mute, so audio in the background does not interrupt the presentation. Questions may be asked by hitting the Q&A button at the bottom of the Zoom screen or writing in their question in the chat box, and I will ask those questions after the presentation. If you have a similar question that has already been asked, you may upvote that question. I have in the chat posted a link to the live YouTube feed. So this is being recorded. And then I'm also providing a link to the feedback form that is on Google. So if you would be willing to provide feedback for our presenters, that would be awesome. I'm asking you to provide feedback concerning the process that they've gone through, the ultimate product that they've designed, and in the process of delivering, and the overall presentation. So I want to thank you all for attending. I hope you enjoy the presentations. My students are absolutely eager to receive your expert feedback and your guidance. And so I wanted to just remind all of you that questions can be asked in the chat box or in the Q&A. So if without any further comments or suggestions, our first presenter, let me share my screen with you. Our first presenter project will be called Go Fetch, an adaptive device for companion dogs by Jeff, Him, and Matt. Our second will be a wireless bathroom button from Pragya, Matt, Isaac, and Marzouk. A third will be a Clean Start, an adaptive device to increase independence and personal hygiene by Danish, Shreya, and Jackie. And then our last presentation for this session is called Paint a Little Picture for Me, which is Bauhan, Alex, and Ashita. And at the bottom of this slide, I have the link for the feedback survey, or if you would like to scan the QR code that is on the screen right now, you will be able to link that to on your mobile phone. All right. So Jeff, Hima, and Matt, you're up.
All right. Hi, everyone. I'm Matt.
I'm Hima.
And I'm Jeffrey, and this is our project Go Fetch, a tennis ball launcher adapted for individuals with limited mobility.
The problem that we're addressing with our device is a request that we got from a client from Seven Hills who has upper limb mobility limitations and is unable to play fetch with his canine companion. Devices that are currently on the market that offer a hands-free Go Fetch device are unaffordable and they haven't been adapted for those with limited mobility. To address this problem, we've engineered a device that can be independently used by people with mobility limitations and can play fetch with their dogs. The minimum viable product for our device is that it has to be able to launch the ball at least 15 feet, and it should be easily activated and independently used by the individual. Our target audience is anyone who has a canine companion and has upper limb limitations, but this device was specifically developed for a client at Seven Hills.
So based off of the problem that we had at hand, we created some fundamental requirements for our project, and there were 3 levels. So level 1 are the requirements from our minimum viable product, which are must-have requirements. So we wanted our device to launch a ball at least 15 feet, be easily activated and independently used. And from our minimum viable product, we also added the requirement of safety because we found this super important to keep our client safe and also his companion safe as well. Our level 2 requirements included the device being easily reloadable, transportable, and manageable, as well as durable and cost efficient. And our level 3 requirements, which are some nice to haves, would have the device launch a ball at multiple angles, be easy to repair if needed, and then be aesthetically pleasing, produce less sound, and be compact and lightweight. So based off of those requirements, we created a few preliminary designs in our preliminary design review. So the first was a wheel ball launcher, which displays almost like a small pipe that curves at the bottom, and it has 2 wheels that rotate, and they kind of poke into the pipe, and a tennis ball going through the pipe would hit the 2 wheels, and the wheels would push or propel the tennis ball outside. The next was a spring ball launcher, in which our client would be able to pull back a spring-loaded mechanism and launch a tennis ball or ball outside. And the last was a frisbee launcher, which worked very similarly to the ball launcher, the wheel ball launcher, in the sense that there would be 2 wheels propelling some toy outside of it. In this case, it would be a frisbee. So after our preliminary design review, we talked with our client and got a lot of feedback about what he wanted to see in the device and also things that would best fit his needs. And so based off of that, we refined some of our designs and kept other ones. So the main design that we looked to go forward with was the wheel ball launcher, and we branched it off into 2 different kinds. So in the middle of this table, there's a single wheel ball launcher powered by a motor and 1 wheel. And so this design is similar to the one we had before, where it's just a pipe in which a tennis ball could be placed, and it would roll down and then hit a wheel, but this time it would be a singular wheel, and it would launch the ball out. There were some pros and cons to this design. Having 1 wheel made it easy to set up with the motor, since it's only spinning in one direction. However, it would put some spin on the ball and may cause some abnormalities when launching. So then we considered a 2-wheel ball launcher, which is similar to the one we had before in the sense that it used 2 wheels on the side of the device. As you can see, it may be a little bit hard to see, but there are 2 wheels on the side, and when the ball is put down, the motor will spin the wheels in the same direction or in opposite directions, and it will launch the ball forward with almost no spin. And the last one was a spring-loaded tennis ball launcher. However, this design became obsolete because we found that using a spring-loaded mechanism would be hard for our client who may have some difficulties pulling back a very heavy spring.
So what you see here is what we were looking to aim to get for our final product. So it's a side view of the device shooting a tennis ball out of the launcher at some launch angle, which we said was about 40 degrees. The circuit we used a 12 volt, 23 amp battery connected to a VexPro 775 Pro motor, which you'll see in a second, connected to a switch, which would make easy access for the user to turn on and off the motor. We chose the VEX 775 Pro motor due to its torque and RPM ratings. It's capable of launching balls in short distances, similar to the objective of our project. And I'm a member of the robotics team at my school. So in the FRC robotics competitions, this motor is commonly used to manipulate game pieces, which is where the inspiration came. For connecting the pieces, we used chain and sprocket along with polycord pulleys, which were printed from my 3D printer along with polycord to power the wheels. And we connected the base of the device along with the PVC tube using screws. We attached the battery holders, motor, and switch using wires, soldering iron, and solder. The final prototype is shown on the screen here. It launches the ball 15 feet. It is easy to activate using a simple switch, and once mounted onto the wheelchair, it can be independently used. We tested for average distance the ball is launched in one of our design studies. We also tested for an average reload time, an average activation time, and the average height of the ball 1 foot after it had been launched. This is the raw data we got from our design studies. For the average launch distance, it bounced first after 22 feet and about 2.4 inches on average, and it came to a rest about 47 feet away from the launcher. We said that this passed the requirements because it launched at least 15 feet. The reload time was about 0.82 seconds, which we thought was relatively fast, so we considered this a pass. The activation time was 1.68 seconds on average, so we also considered this a pass. For our launch safety, we took videos of the ball as it came out of the launcher 1 foot after the launch, except these videos were unclear, so to figure out how high it was above the ground, we used some physics to obtain a theoretical height.
So this data analysis reiterates a bit of the data that Jeff was talking about before. So again, the average distance traveled in the air before the ball actually touched the ground was about 22 feet in some inches, which again passed our level 1 requirement of launching 15 feet. And again, he was talking about using physics to determine the theoretical height of the ball about 1 foot after the launch. And that came out to be 0.8 feet, which is about like 10 inches. And we deem this a bit unsafe because we want to keep our client and his dog safe. And if the ball launches only about 10 inches, it has a possibility of hitting his dog, and we don't want that to happen. So in the future, we hope to find a better launch angle for the ball or have it launch a little bit higher. That way it keeps him and his dog safe. And again, just to reiterate, the average reload time was about 0.8 seconds on average, and the activation time was 1.68 seconds. And if it's unclear, the difference between the reload time and activation time, the reload time is just how long it takes to put the ball back into the device and have it launch. The activation time is how long it gets the flywheels to start spinning and the device to actually start functioning fully. And so we also found that after a few consecutive uses of the launcher by putting the ball in, the ball distance will decrease over time as the battery loses power.
Here we have a compiled list of our requirements, including our level 1, level 2, and level 3 requirements. And after testing, we went back and we saw if our our final prototype had met these requirements or not. In terms of functionality, our device proved to launch the toy at least 15 feet, and it did launch the tennis ball, which is a pet toy. In terms of being easily activated, the time it took for activation was relatively low, so we had that as a yes. But again, for easily activated and independently used and easily manageable, we would have to test with our client to make sure that given his mobility, he's able to maneuver the device and get it to work successfully. In terms of cost efficient and aesthetically pleasing, our device right now is not very cost efficient, but with further iterations of the device, we can continue to choose different materials that can make it more cost efficient. And then with aesthetically pleasing, because there are some wires and chains exposed, which is also a safety concern, with covering those and maybe changing the appearance of the device a little bit, we could get that to a yes. Right now, with produces minimal sound, when the device is run, the motor is making a bit of a whirring sound, which is kind of loud. And then once the ball is launched, there's a pop sound that occurs. In terms of compact and lightweight, the device is pretty lightweight and it feels around under 10 pounds, but because it is a pretty wide PVC pipe, it isn't very compact. In terms of safety, which was a level 1 requirement that we didn't meet completely, there are exposed wiring and chains, which was a safety concern. And also, as Matt stated, because the launch height after it's been launched is relatively low, we don't want it to hit the canine during the fetch process. So that's something that we'd have to change by adjusting the launch angle when it's mounted on a wheelchair.
So this is a video of us using the device. So as you can see, the device was activated by a switch, and then the ball was dropped by the top of the tube, and it came out the end.
So overall, the device came out better than expected, and I will be brutally honest that it did come out a lot better than we expected, given the time constraints we had, especially being only online for the past month and a half. We were in a little bit of a rush to get a lot of the materials that we needed and iterate a bunch of different designs for this. And so it ended up being a long build process, but we did get a complete product in the end. So in the beginning, we started with some smaller batteries and wires for the device. However, the wires were a little bit too thin and couldn't carry the current without burning up. So instead, we upgraded to D-cell batteries and thicker wires, and the thicker wires were able to handle the current needed for the motor. However, the D-cell batteries that we ended up using, rather than the small batteries, were a lot heavier and also didn't produce enough current to run the motor at full speed. So finally, we got a 12-volt Duracell battery that is lighter than the D-cell batteries and was able to produce a consistent current that could run the motor. And so that was the final battery and set of wires that we used for the device. And so based off of this, we did have several future expansions we wanted. So like Hima was saying, we did not fully meet our level 1 safety requirement. So we did have some wires and some chains exposed. And so we hope in the future that we're able to cover that up and give it to our client and test that way. And then we also hope to satisfy other requirements as well.
As Matt said, a priority in future extensions would be addressing the safety issues that we brought up. In addition to that, we can also make aesthetical and functional improvements, such as hiding the wire. In terms of functionality, adding a larger activation button instead of a switch that's positioned higher up on the device, closer to where the ball would enter the device, would make it easier for a client to use. Another nice to have functional improvement that we can add is having adjustable launch angles, because as you change the launch angle, the distance the ball travels will also change, which can be a good characteristic to have in our device based on where our client and his companion are playing fetch. Some lessons that we learned throughout this process is the importance of iterating prototypes, and not only based on the requirements that we've had and the device is not meeting, but also based on our client's needs. In addition to that, we found that communication between us as teammates was key, because just being in remote locations and not being able to meet every day at school, communicating about the documents that we were getting done, the research that we're doing, and how testing and building was going was really important. Here is a QR code and the website that you can go to see our instructables that describe our build process, the usability, and a video of the device being used in addition to the materials and the tools that were used. We can stay on this slide for a little bit if you want to get that.
The next slide is just questions. So I guess at this time, while we leave the instructables up, we'll ask if there are any questions that you guys have for us or any suggestions as well.
Sure. There are several questions. The first one would be from me, and I wanted to hear a little bit about how your product compares to some of your competitors.
So a lot.
I'll let you go, Hima, sorry.
All right, I was just going to say that a lot of the competitors on the market, they can obviously successfully launch the ball well. The only issue is those devices have not been adapted for someone with mobility limitations, and they're relatively small. So if they were placed, they would be in an area where the user would not be able to like replace the ball, and that would be something that you'd have to train your dog to do.
And what I was going to say was that we also found that a lot of the devices on the market are relatively expensive in the like $200 range. And that's why one of our requirements that we wanted to have was have our device be cost efficient, so that our device would be easy to access for other people who would want a device like this. And also the devices on the market too didn't use regulation size tennis balls. A lot of the devices use smaller tennis balls that were manufactured by that company. And they were meant for usually smaller dogs rather than a larger dog. And we know that our client's dog would most likely use a regulation tennis ball, which is a lot bigger. And that also kind of goes along with safety. Using smaller tennis balls can be a choking hazard to larger dogs. And that's why we also kept that in mind.
Okay, so I think that would end up addressing Om's question of, here's the question I'll state to you. Any thought of using a lighter plastic ball toy to reduce the need for hefty motors and maybe the possibility of lithium, I guess, LiPo batteries?
Yeah, I definitely think that like using a lighter ball would be something we'd look to in the future, especially to reduce the motor costs, because using a pretty hefty motor did require a larger power source, and it was also a little bit more expensive. So in the future, we'd look into that. Right now, a regulation tennis ball is what we were aiming to use, just because it's easier to get our hands on, and it's also safer for the client's dog as well. But when we are able to test the device with our client and his dog as well, we can see if we could use any smaller tennis balls or even a lighter ball as well, like a wiffle ball to use.
Okay. Catherine Morse ends up asking, looks like fun, but not sure if it is easy to take on and off. Do you envision taking off each time? Adding width to the wheelchair is problematic since many wheelchairs barely fit through internal doors as it is.
Yeah, that was something that we definitely considered as well. So originally, we had planned having the device mounted to the side of the wheelchair, but we had gotten some advice for people who had clients with wheelchairs that they barely fit through the door, as you had mentioned. And so our client had also talked about putting the device between his legs on almost like a base plate where his feet rest on the wheelchair. And so we were hoping that in the future, we'd be able to add a base plate where it could rest between his feet. And that way he could hold it between his legs, and it would be easier for him to place a tennis ball in as well. That was a great question.
Emmeline asks, does this work with other toys such as balls of different materials? Would this affect the launch distance?
We haven't tried using other toys yet, but that is something that we could look into trying in the future.
Alec asks, do you think this would be possible to make the device more compact to increase portability?
Yeah, so the PVC that we ended up using for the device is actually, I'll rephrase that. You're able to take it apart. So if Jeff goes back in the presentation to the device, the device uses, yeah, there we go. Oh, yeah, so it uses PVC. So originally in the launch video, the small corner piece right before the motor attaches to both PVCs that jet out one end and then above. And you can take those two pieces off and disassemble it. So it's a little bit more compact. But I will say that the PVC is pretty thick. So that's as compact as it'll get. But being able to take it apart was one thing we considered so that our client didn't have to carry around a large device.
Okay. And Rachel Johnson asks, I'm curious about the reload times. They are very low. Does this include the time to get the ball from the dog's mouth up to the device and then activate it? The video made this seem to require a lot of mobility, bending over to adjust the switch. Do you foresee this setup working for your specific client as well as others who may have mobility limitations?
In regards,
So in the future, we're looking to move the switch so it's higher up on the device by adding a little bit more wire length, and that way it'll be easier to access. So in terms of the switch, I think we can definitely change that because right now it is a little bit hard to use. And then in regards to the ball, we just tested from the ball being in the lap of the user into the actual device. So we did not test it with a dog giving the ball to the user.
Alexander ends up asking, do you foresee any durability or swelling issues with the compliant wheels as the rubber is rather pliable?
So far, we haven't had any issues. Over time, that may change and we could see some swelling happen. But at this point in time, I don't think so. We chose a specific compliant wheel that is a little bit less compressible than some of the other options. So over time, it should hold up fairly well.
Okay, so I'm going to ask your group to continue answering the questions in the chat room because there are a couple of other questions I'd like you to address. So I'm going to end up asking the next group, which is Bragia, Matt, Isaac, and Marzouk, which they're doing the project called the Wireless Bathroom Button, to get started. Thank you very much.
Hey everybody, my name is Marzouk Iqbal.
I'm Isaac Lau.
I'm Pragya Narahari.
And I'm Matt Sawyer. And this is our STEM 2 project on a wireless bathroom button. So the motivation behind this project is that millions of people do need assistance in environments like Seven Hills. And while they do need assistance, balancing that with the independence of each client, something that is trying to be maintained. Therefore, constant caretaker can be intrusive. And since there are many types of disabilities, it's difficult to find a solution that fits all of these disabilities. And so far, the competitors that we have are expensive and have solutions that are not fit for as many different disabilities.
So the goal of this project is to design a wireless button that can send signals to a caretaker's phone. And this will allow a client to feel more independent while also allowing for assistance when they need to. So we have some requirements for level 1, level 2, and level 3. Level 1 requirements are things that the device must have. So it must be wireless, easy to use, and durable. For level 2, these are things that would be nice that it should have. So it should be inexpensive and lightweight. And level 3 requirements are things that it would be nice to have. So it would be nice to be visually appealing, multifunctional, and to have light levels. So for our first design in the PDR, we had the button on the person. And in this case, the button would be with the client at all times so that when they need to use the bathroom, they can press the button. and this would send a signal to the caretaker's phone. Some pros is that it can be lightweight and the device is cheap. However, it is not customizable and it's harder to have multiple signals. Our second design is the button on the bathroom. And in this case, the button would be mounted on the bathroom door. So some pros is that the client doesn't need to worry about carrying the device and it's more permanent. However, it's harder to implement and it would be harder to maintain. Our third design is an automatic sensor. And in this case, the client would wear a band, which would send constant signals to the bathroom sensor. And whenever the client gets close, a signal would be sent to the caretaker. Some pros is that it would be fully autonomous and it can be smaller since there's no buttons. However, this is much more complicated and harder to maintain.
In terms of our CDR designs, we had two main designs. Our first design was our D-pad or 3D printed plush shape design. In this design, we see that the client can press down on either one of the four sides, and each of these buttons on each of the four sides would entail a different option of help or request for help. Again, this design would be ideally with the person or with the client. In terms of our second design, we had a linear design where the buttons were in a line, and we designed it such that the buttons would be able to move up and down through the hole. When the large button would be pushed down, an extended rod would be pushed out to a much more smaller button for additional options. Again, with this design, the design would be on the person. So in terms of determining what type of design we wanted to go forward with, as Isaac talked about earlier, in terms of the button on person, the button on bathroom, and the sensor design, we decided to make a decision matrix using the different categories that you can see on here. And using decision matrix, we decided that the button on the person would be the best design. You could see it had the highest score.
So moving from the CDR to the ADR, we already knew how we were going to approach the problem, but we were not sure the exact model that would make it easiest for the client to use. We decided to go with the approach that we were going to make the button on the wheelchair. For both designs, we would be using this configuration as shown to connect the buttons to the Raspberry Pi. The button was attached to one side of the breadboard with the resistor and two wires coming out connecting directly to the Raspberry Pi. This was the basic model for the buttons, and the next two designs shown will be using this configuration, but will have additional add-ons. As Marzouk mentioned before, this is the plus sign design. The plus sign was 3D printed and is 4 inches by 4 inches. Although not visible in the picture, under each of the points of the plus sign, there is a small cardboard extension that comes down from each of the points so that it can press the button. Since both the length and width of this model are 4 inches, an extra extension would needed to be added to the sides of the arms of the chair because the device would not be able to fit otherwise. Once those were set, the 3D model was placed on top and now the button could be pressed on either side. The reason we didn't go ahead with this model was because not only did the device stick up high from the arm handle, but it also protrudes outwards as well, which may have limited some of the room the user will have while sitting in the wheelchair. The model we decided to move forward with is the 3D model where the buttons were placed in the straight line. As shown here, the buttons are placed in a straight line and also have an extension in order to make the buttons easier to press. The 3D printed extensions are attached to the base of the cardboard using cardboard rods to hold it up. Another layer of cardboard is added around the model in order to keep everything in place. There's also a pouch attached to the arm of the chair which holds the Raspberry Pi. We decided to use this model as our final prototype because we found the buttons were easiest to press on this model, and even though it does extend upwards like the other model, it doesn't extend outwards like the plus sign model. However, moving forward with this product, we would focus on aesthetically pleasing elements so that the parts are each durable and look nicer. When the user presses a button, a notification, like shown in the picture, is sent to the nurse or caretaker's phone. As of right now, we are using Pushbullet, which is an app that's free and helps us send notifications from the Raspberry Pi, but is only compatible with Android devices. Hopefully in the future, we can find a software that is both free and compatible with Apple devices. There are 3 statistical tests we ran to test this prototype. We ran a test on response time, force, and range. After several tests of each button, notifications were sent from the Pi to the phone almost instantly. All notifications for each button were received within 1 second of the button being pushed. This removed the need for a time-based experiment because the speed of the notification devolved the experiment to simply a test of how fast the timekeeper could start and stop the timer. This increased human error between trials dramatically. The next test we ran was a force test. For the force test, as shown in the picture, we used quarters which we stacked on the button to find the force needed in grams to push the button down. We ran 5 trials for each of the 4 buttons, and based on our test, we found an overall 1.72 newtons of force is needed to press down on the buttons. The next test we ran was a range test. This test was run to see how far away the button can be from the device that the notification was being sent to and still work. Since when testing this device, I pressed the button from where I was and the notification was sent to where Matt was, who was miles away, we knew the range wasn't going to permit any messages from going through or even slow down the process. This also means the Raspberry Pi and the phone aren't required to be on the same Wi-Fi and can still work perfectly together. So there should be no problem for the notification to reach the nurse or caretaker quickly.
So our final prototype consists of a Raspberry Pi with 4 miniature breadboards attached via the pins on the Pi and wires. These breadboards house a small button and a resistor. Each button sends a distinct notification to Pushbullet, which is tracked in the code. For this prototype, the images were printed and taped onto the buttons instead of a more permanent solution. The Raspberry Pi hangs off the chair in a pouch that is out of the way of the user. All coding was done in Python with the built-in Raspberry Pi IDE. The GPIO library was used to track button presses, although GPIO 0 was also tested. GPIO stands for General Purpose Input-Output, which refers to the pins on the Pi. These libraries help track the state of each attached button and can give instructions to the Pi once a button is pressed. The code that pushed a notification to Pushbullet will be completely invisible to the user and may only be edited by attaching the Raspberry Pi to a PC monitor with a keyboard and mouse. Currently, the Pi only gets power directly from an outlet, although battery packs that serve as a standalone rechargeable power source are commercially available. The code to wait for button presses is currently being manually executed using the whole monitor, keyboard, mouse setup, and that is so we can debug it just by running and rerunning the code without having to unplug the Pi every time. It is possible to get the code to run as soon as the Pi is connected to power so that it will be constantly waiting for a button push as soon as it is turned on. Here are our requirements, along with whether or not the current prototype can meet the need. Some just to comment on. The device isn't really easy to fix because the entire casing would have to be disassembled to repair a button, and any code issues would have to be debugged with the external setup. The automatic alerts were geared more toward our sensor designs, which we decided not to go forward with. And although there isn't a light for wireless connectivity, some battery packs offer light levels to show how much power is left.
So in terms of future work, as Pragya mentioned earlier, the app that is being used right now only works on Android devices. So making this cross software and making it compatible with Apple products is one possible future extension. In addition, the app that does have the same function that works for Apple products requires a monthly payment. So being able to make that free would be an extension. In terms of this device being wireless, since it does fit the definition of being wireless, but we want to extend that definition to where there would not be connection to a laptop or an outlet in order for this device to function. And if there is a way that we can make this device more compact by reducing the amount of wires, that is something that we hopefully want to implement in the future. And making this device more compact would also allow for this device to be more wearable or movable. And that is something that would be ideal for clients in Seven Hills.
So some things that we learned during this process is that it takes a long time to narrow down a solution as seen with our PDR and our CDR models. And there's also a lot of components that we didn't consider at first glance, such as the Raspberry Pi, the Arduino buttons, and the resistors. And we also learned how to work together on a physical object, even when we're separated in this crisis. And we also learned how to divide up our work based on our different strengths. Thank
So we
you
will
for
now
listening.
take Oh, yeah, go ahead.
Oh, thank you for listening. We'll ask any questions now, or answer any questions now.
Okay, good. Thank you. And so I'd like to encourage both the panelists and the attendees that to type into the chat window any questions that you might have. So from Catherine Morse, how much power does the device need? Many power wheelchairs have USB ports and in the armrest. I am charging my phone right now.
So some of the battery packs we looked at actually can also charge phones. So I don't have the exact number on how much power our device needs, but assuming it can use the same battery pack, that may be something we look into where we do use that built-in thing on the wheelchair to power this device.
Okay. From Balhan, how did you decide on the button size?
So we decided on the button size mainly from our preference because the original buttons, the Arduino buttons, were very small. So we decided we wanted to make it at least very big so that, as like Matt showed before, that there could be a picture on it so that the user could differentiate between the different buttons if they say forget what each of them mean. So we wanted it to be big enough so that the user could see and press it easily, but we also didn't want it to be too big that it takes up too much space.
We also based this design on the width of the wheelchair arm, which is around 2 inches, which is around the size of our button.
Okay. There's a couple of questions concerning, is there a way to mention that the press of a button was accidental? How could you make sure that the button can't be pressed accidentally?
As of right now, oh, sorry.
Go ahead.
Okay. As of right now, we don't have a process to say if the button was pressed accidentally, but in the future, that could be something that we could implement.
In addition to that, in my research, I found that keyboards typically take between 0.5 and 1 Newton to push down, like the keys on a keyboard. So our button being 1.7, we think offers an acceptable kind of balance between not being super easy to push down by accident, but you can push it down easily when you need to.
Okay. Roy asked the question, how long did it take to send the signal miles? And following on questions, how many miles per second per minute?
We weren't able to run an exact test for how many miles per minute, and like how many miles per second, sorry. But when we sent, as we said before, that it takes almost instantly for the notification to be sent, that was also across miles. That wasn't like when the device was right next to the buttons. So it's sent almost instantly. And as we said before, it becomes, to track the time of that, there's a lot of human error that can go in because it comes with like the time that the timekeeper is pressing the button.
Adding on to that, if the range is within miles, I don't think it would be a problem in an environment like Seven Hills, where caretakers are usually no more than a couple 100 feet away from each of the clients.
Okay. One question from William H. Is there a way where you don't have to take apart the whole design to fix a small issue with, for example, the Raspberry Pi? Also, how susceptible is the device to water because it is related to the bathroom?
So right now, as like most of the parts are 3D printed, we have most of the things are very tucked away so that the user, if like a minor water spill happened, nothing major would happen. But if there was like a major water spill, then something if there was any wires exposed. But right now we don't have many wires exposed in order for there to be too much damage if like a small water spill was to happen.
And then last question before then I'll ask you to address them in the chat room. Roy asks, how were the requirements attained?
So for the requirements, since we had like our project was more like a general project to address this need, we decided to look at competitors' products on the market and see what they didn't have. And we decided to make those as requirements for things that we thought were necessary. Like one example was cost efficient. Many buttons like this on the market right now are very expensive. So we wanted to make sure ours was pretty cheap.
Also, adding on to that, unfortunately, we didn't really have a client to go off on, so we had to develop requirements again based on competitors. Otherwise, we would have made requirements that are much more specific to a specific client, but for that reason, we had to make them a little bit more general, as you saw the requirements earlier.
Okay. All right, so then I will ask your group to go through the comments and address some of the questions that were not able to be answered during this time, while the next group, Danish, Shreya, and Jackie, gets set up and begins.
So hi everyone, my name is Shreya.
I'm Danish.
I'm Jackie.
And we're doing a clean start. So our motivation behind a clean start was basically that there's an individual, a male, with traumatic brain injury. And with this, he has left-sided paralysis. He currently resides in Seven Hills in Holden, and the client would like to be more independent, especially with personal hygiene. Particularly, the client wants to be able to perform tasks associated with showering without staff assistance. So just some background, paralysis is the loss of muscle function in your body. It happens when something goes wrong with the messages between your brain and muscles. Paralysis can be partial or complete, and in this case scenario, the client has partial paralysis.
So just to briefly cover some requirements that we were given from a small blurb from our client. I'll cover the level 1 requirements, which are our main ones that we're trying to cover that need to be completed. So our MVP is our client is able to shower using one hand and able to effectively clean every part of their body, as well as making sure that the product is electrically safe for both the client and the technology itself, making sure that we don't blow a circuit and the client isn't injured in the process, and making sure that the client is comfortable while they're showering, so they don't need an aid, because that was one of the main reasons why this project was a thing. And lastly, our last level 1 requirement was it can last through many uses. What's the point of making a product that can only be showered with once or twice? So we want to make sure that it can last for as long as it can before needing to be replaced.
So in our preliminary design stage, we had 3 different designs, and this is just the list of the designs in a short, brief statement about them. And at the bottom, you can see there's a design 3.5, and we added that because in all of our designs, we're planning on adding an electric soap dispenser, and this would be required for all the designs since the client wouldn't be able to squeeze a shampoo bottle. So our first design was a part of a wall that's made out of brushes from CAD, as you can see in the drawing, though that's going to just be the back wall of the shower, and it's going to have brushes lined up for the client to be able to use, and they are going to be motorized. And the pros is that it's going to clean all areas of the body at once without the client having to use his hands or any other part of his body. But the cons are that it might hurt the client, as you can see, if any part of his body were to get stuck on the brushes, or if they were supposed to, or if the motors were to face any technical difficulties, it would hurt the client. And it'd also be difficult to transport because that's like entire section of the wall. So for our second design, we had a shower handle, and you can see in the drawing that the brush is going to be under the shower head on top of the handle. And basically this is the client only needs to use one hand to activate this, and it cleans all areas, and he can control whichever area he wants to clean, as well as the motorized brush would be able to clean sufficiently. But the bad thing about this one is that he still needs to use one of his hands, but he can use his right arm, so it should be fine.
This is in comparison to our other two designs where the client did not need to use their hands for either product.
And our last design is our weakest one, and it's a wetsuit with brushes aligned on the inside. And although it gets every part of the body, if there were to be any motor malfunctions or if the technology had some difficulties, it would be really painful for the client. Additionally, it's really hard to put a wetsuit on and even harder to get it off when it's wet, and the client would need assistance.
So our next stage CDR, there were a couple things that we narrowed down on. One, we immediately ruled out design number 3 due to our feedback from our peers and our teachers. It's very difficult to put on and off a wetsuit, and the brushes would be static, so they would not actually move, making it not a very effective clean. And we also got rid of our soap dispenser 3.5 because that requires a little more technology, and we wouldn't want to make the product unsafe just by including that. So we said, okay, if the design needs it, we'll include it, but if not, then it's not necessary. So we moved on to creating a computer-aided design of each design. So this is our first model. As you can see, once again, the shower head is above the brush, making it a little difficult to clean and brush at the same time. So some brief analysis of it. This cost was on the lower side for our designs, totaling it around 50 to 80 bucks, depending. And it's pretty easy to manufacture, at least compared to Model 2. It meets all our requirements, and it's, like I said, fairly cheap. But it's difficult to brush since the brush is underneath the shower head, and the shower head may block some areas when the user is trying to brush. And our Model 2, this is a lot more complicated than Design 1, as you can see. It's a whole partition of the wall with designated brushes to brush the user. A big pro of this, right off the bat, is the user doesn't have to really use their hands to brush, to actually clean themselves. It can all be done by a machine. But by looking at the cost, it was almost 2 or 3 times the price of the previous, of Model 1. And it's very complicated. It can be very dangerous if something malfunctions, and it does not clean small areas. This design was mostly for the back and maybe head area, so it does not really clean everything.
So as a general overlook in our build process, throughout the process from CDR to ADR, feedback was heavily weighted. After carefully analyzing the pros and cons of each of our final designs, as well as considering all given feedback from both our peers and our teachers, our team finally decided that it would be best to pursue Model 1, which, if we remember back, is the shower handle with a brush attached to it. This design was chosen because it's not only satisfactory of the requirements, but its pros heavily outweigh its cons. With this, the next step was to produce various prototypes before finally narrowing down to our final product. So this was our first prototype, which was the full shower head and the handle. As you can see, it has a motorized brush and a soap dispenser. The reason we ruled this out was because, as Danish mentioned before, it's a bit hard for the user to reach certain parts with the brush while it's under the shower head. At the same time, it's not very versatile because in case the user wants to use other bathrooms or shower heads, they wouldn't be able to use the same prototype. So this is our second prototype, which was the shower handle attachment. It's kind of a next step from prototype 1, and it's just a 3D printed brush designed to be attached to the shower handle itself. So as you can see, to the left is our CAD design, and onto the right is our 3D printed part. The reason we ruled this prototype out was because its printed brushes were made out of plastic, which would ultimately cause discomfort for the user. And at the same time, because it was made of plastic and it had supports in between due to 3D printing, it broke very easily when you tried to remove the supports from the brushes itself. This was our third prototype, which was essentially a hybrid of prototypes 1 and 2, and it's a shower head attachment. So we felt as though this was our most promising prototype since it allows for the device to be attached onto the head of the shower handle. So with this, we wanted to look more into prototype 3. So our initial approach to prototype 3 was to 3D print it. As seen in the picture, the printed bristles were made out of plastic, and similar to our experiences with prototype 2, it broke very easily. Additionally, supports between the bristles, again, could not be removed easily, and as mentioned before with prototype 2, the plastic would cause discomfort for the user. So we decided to have an alteration of prototype 3 itself. So based on the qualitative data, rather than directly producing the prototype through 3D printing, we decided that 3D printing a mold would be a better approach. The product could then be produced by filling out the mold using a liquid silicone or rubber. And in this case, not only would it be more comfortable for the user, but the mold would also be reusable. In this case, if the product was lost or broken over the years, the client could simply refill it using a liquid silicone.
So we printed out this mold using Dr. C's 3D printer, and fortunately we were able to get our hands on a rubber it was on the short A hardness scale. It was a 71, which is kind of around an eraser, so it's soft enough to brush. So we tried it out, but unfortunately, even though we used an easy release liquid to try to get the mold get the rubber out of the mold after it dried, unfortunately, due to a large amount of surface area in contact with the rubber and the mold, it was very difficult to get out, and a lot of the bristles ended up getting stuck. Although this looks like a big failure, we ended up looking on the positive side. There's the bristles that we did have. There was 2 standing, that they were they were solid and they were flexible and felt good on skin, which meant that we can definitely work with this material, but we have to figure out a different solution for the mold. But like I said, we're looking at on the positives of this, and looking to the future, we'll definitely be able to manipulate this and come up with a better solution than the PLA mold.
So this is a theoretical video demonstration of our prototype. Keep in mind that it is theoretical. As mentioned, we don't have a working prototype, so instead we're just going to take this styrofoam cup and latch it on to a shower head with tape. In reality, we would have our prototype, which would be made out of liquid silicone attached with Velcro. And we're just going to use this as a video demonstration to see water flow through the holes we made, which represent the bristles of the brush. So as you can see, the water does flow through, so theoretically, with more testing, our prototype should also work. As mentioned, we don't have a working.
So now some theoretical stress tests. We ended up running our design through a couple different simulations in CAD just to see how it would react to different forces. So for example, we may have forces, if it's dropped, this is just in case it's dropped, just a small little animation. As you can see, the bristles are reacting kind of like a hairbrush as you push in. So the bristles react pretty well with each other. We tested it for a couple different forces, pointing in the z-axis up and down. This is in the z-axis down. We pointed the x and y, and all of the stress tests we found were the force overall was pretty evenly distributed across the prototype itself, and so we thought it was a good green light to continue moving forward with this prototype.
So in conclusion, our third prototype, or the shower head with the attachment, seems to be the most promising as it integrates all the qualities of the other 2 prototypes and corrects their flaws and proficiently meets the requirements, all level 1 requirements. But unfortunately, the current mold and silicone alliance did not work out as planned, and therefore we would have to use different materials and lubricants in the future, and we would have to experiment with that to get the best ones. But so far, theoretically testing on CAD has proven that the final product should be able to withstand the high level high stress levels and the various water pressures, so that's good. And finally, since the deliverable product was not ready due to the various constraints at this time, we decided as a group that it would be essential to continue working on this project over the summer in order to satisfy the client. And also, it is critical to follow a schedule in order to do this in a timely manner so the client doesn't have to wait too long.
So branching off what Jackie was talking about with the schedule, we decided to split up our future extension, not only for the broad future, but strictly a 3-week and a 3-month plan. So in regards to our 3-week plan, we want to test various lubricants and liquid silicones and rubbers in order to, 1, efficiently remove the silicone from the mold, and 2, in order for the prototype to be flexible enough for the client's comfort, but simultaneously durable in order to prevent easy tearing. We also want to continue with test design and data collection. So as Danish mentioned before with our stress test, stress does, it does symbolize the force over area. So it connected with how much water pressure it would be able to withstand. So to continue with our actual prototype, we would want to do a drop test, which would show if the prototype would be durable enough to withstand drops from a certain height, a pressure test in order to make sure that the water from the shower head does not cause damage to the design, as well as cleaning effectiveness. So just how clean the user would be after using the product, which would satisfy our MVP.
Our 3-month plan is more of a future extension, and it's just an estimated time period. But these are just things that we thought would make our product better. So the first one will be, we will make it easier for the user to clean and replace the brush because they can't be using the same brush over that long of a period of time. And also we would add a soap dispenser, as we talked about in our preliminary designs, with the sensor on the shower head so that the user doesn't have to remove the shower handle, put on shampoo, and then take the shower handle back. And we would also give the user ability to control the speed and power of the brush to fit their needs. So if they thought something was too hard, they could lessen the speed and it would be more comfortable for them. And we would also make it fit for different types of shower heads so that we can expand our audience and give it to multiple different users. And one thing we would like to do over the summer is meet with the client and accept feedback for them so we can edit our design. And we would also, this is like a manufacturing type problem, we would find a way to produce the product more easily and more cost efficient.
So our main takeaways from this was, 1, that communication is extremely important, especially during times such as now. Despite taking a virtual detour, it was still possible to continue with project-based learning, especially by collaborating with our peers. Science, as we know, does not always work out. Many times there are multiple obstacles. Nevertheless, the process is still incredibly important. Our team did face many hardships, especially with getting a final working prototype, but we continue to work and will continue to do so until we have a deliverable product which satisfies our client. So these were our references, and if you guys have any questions, we'd be more than happy to answer them.
Great, thank you. Rachel has a question. How will soap stay on this product if water is constantly flowing through it?
So one idea that we had was to have a soap dispenser, as we were talking about, but in regards to the question, whereas if water would be constantly flowing through it, we might just have the client apply soap to their body themselves and then use a brush to go through and brush it out.
Okay. And Pragya asks a question. Are you looking into having a different extension for washing hair, or is it the same brush for both?
That would definitely be a part of our testing with ourselves and feedback from the client. We don't see any reason why currently it shouldn't work it should work pretty well with hair, but once again, we haven't been able to test that yet. So that's definitely what we'll be looking into once we get the final prototype working, and we'll be able to test different parts of the body.
Okay, let's see. Wayne asks a question. Would you think about a way to stop flow in the shower head to allow them to use it to clean?
I think when it comes to that, they would simply have to turn the shower water flow on and off. And that way it would just stop the water flow. I'm not sure if we've thought about constricting the water flow from the prototype itself, because that might overflow the water inside the prototype, which might cause malfunctions. However, that is something that we'll definitely look forward to and think about in the future.
Okay. Question from Roy. Did you consider similar products for material use, such as a dentist's water pick for tooth cleaning?
With the constraints given, or what the client given to us, or what the client gave to us, was mostly just showering. It said originally hygiene, but then later on it specified showering. We definitely can move forward with this. So if we wanted to take this product and apply it to different materials, we don't see why we couldn't, but we definitely would have to get a working prototype first to see if it works on our original requirements.
Okay, so I'm going to ask your group to answer the rest of the questions that are in the chat, and we'll get the last group up, who is Bauhan, Alex, and Ashita. Project titled Paint a Little Picture for Me.
So I'm Ashita.
I'm Bauhan.
And I'm Alex, and we're the group Paint a Little Picture for Me.
So the problem that we are trying to solve is that individuals with spinal cord injury often have limited mobility. This makes it difficult to hold paintbrushes and create art using traditional means. And currently, one of the solutions that Seven Hills is implementing is mouth painting by placing a paintbrush in one's mouth. However, this can become tiring and very uncontrollable. So the goal is then to make a mouth-based device that relieves weight, increases control, while allowing individuals to continue expressing themselves in creative ways.
So there are several devices out on the market that have tried to address this problem. One of them is the mobile painting device, which is an arm that's attached to a wheelchair, and the user can wheel around to create art. So some of the pros of this device is that it's compatible with almost any level of mobility. It creates very bright art, and it's also low cost, but also the user cannot see the art while creating it, and it offers way less control than a traditional brush, and it also requires a lot of space and cleanup. So these are some of the issues that we tried to address with our device. The second device is the glove, which is comfortable and not invasive, but it requires mobility of both hands, and the hand might get tired easily because a paintbrush is put into the glove and the user has to move their hand. So if the paintbrush is heavy or large, then that could cause the user to get tired easily, and it's also difficult to clean. And the last device is the Blick egg-handled paintbrush, which is basically just used like a regular paintbrush, but has an adaptive handle. So this paintbrush can be reused, and it's easy to use and clean, but it's not compatible with all levels of injury, and the handle might also not be comfortable for everyone.
So our level 1 must-have requirements is that the device is the user's preferred method of painting, the device is compatible with paint, the device shall function without the user needing to use their hands, the device shall be able to create art based on what the user wants to create, the device includes a manual, the device is stable and durable for one paint session, which we decided was about 30 minutes, the device shall fit comfortably for different face and body shapes, the device shall pivot at least 10 degrees from horizontal, the user shall be able to move the part of the body necessary to use the device shall not contain sharp or dangerous parts, and it should be from a non-toxic material. Other requirements that are more nice to haves include things like sanitizability and portability.
So for the PDR, we came up with four different designs that could potentially work. The first design utilized facial tracking for a digital paintbrush, and it basically tracked different parts of the face, such as the eyes and the nose. And these movements on the face would translate to movement of a digital paintbrush. And other gestures such as blinking could change other features such as mixing colors. The second design was similar, but it tried to create actual physical art by implementing a robot that would move around a brush to create art on an actual canvas. The third device was a headband wrapped around the user's forehead with Velcro, and it held a paintbrush outwards towards the canvas, and the user could move their head and their face to actually create art. But one of the cons of this design was that the user couldn't see the art that was being created. So the final design was the mouth mount, which is wrapped around the lower part of the face with Velcro and held a paintbrush outwards towards the canvas, and the user could move their face to create art.
After meeting with our client, we decided to pursue the mouth mount. The client was not very interested or familiar with digital art, so we had to choose one of the physical art options. And he was already familiar with mouth painting and asked us to create a device that he could wear around his mouth to help with that. So at Critical Design Review, we had 3 prototypes based on the mouth mount. The first one was extremely blocky and uncomfortable to wear. The second one was less blocky with an increased slope. However, this did not help very much with the comfort. And the third mount had an even greater slope, but comfort still needed to be improved upon. And at the time, we still needed to find a way to address trying to secure a paintbrush to the hole.
So as we continued iterating and building upon our previous prototypes, we started to get closer and closer to devices that actually did what we wanted to do. So as you can see, by the time we hit mount 5, we had a functional Velcro strap, one that wouldn't come undone during the painting session, which was really important. So there's an improved hook and other things like that. And furthermore, the slope kept needing to be increased because even though it was getting more and more comfortable, it still wasn't great. It would still like slide on the face. So mount 5 has increased slope compared to the previous ones, and mount 6 is very similar to mount 5, except it's even more, there's even more slope to it, and it's even more comfortable. And then as we started finishing up with the mounts, we needed a way to actually put the paintbrush into the device, and the way that we had that was utilizing the very large hole within each mount. We created these foam compression pieces. So as you can see, foam 1 is a piece of foam wrapped around, and it's secured by multiple zip ties. And then foam 2 is 2 zip ties, and then foam 3, we just use tape. And what these do is these can be placed inside the hole, and then a paintbrush can be slotted within. And that allows, that continues to allow the user to pivot the paintbrush and have control that way, as well as relieving some of the stress from the paintbrush itself. So as we kept doing this, we had multiple foams and multiple mounts that we really wanted to test and see which one was really the best. So we started to go into design studies for that.
So the first 2 design studies were aimed to measure the amount of control that the user would have with each of the designs. And we only tested 6 of the designs, 3 of which were with mount 5 and then 3 of which were with mount 6. So this design study measured the maximum deflection from the horizontal when the user put the paintbrush inside the device and tried to control it with their mouth. So the control had no resistance and led to the greatest deflection and very little control. Foam 3 performed very well with a high level of control independent of which mount was being used, but mount 6 consistently outperformed mount 5. So that was eventually the mount that we finally went with. And after this study, mount 5 with foams 1 and 2 were eliminated for poor performance. So those were not tested in the other 2 studies.
So after that design study, we also wanted like a way to quantify whether or not these devices were actually improving the user's control over the paintbrush. So we designed an experiment that basically focused on measuring this accuracy. So what we would do is we would have a box, and we would attempt to paint over the entire box and go over the outlines as intended. And when we'd miss spots or lose control of the paintbrushes in certain places, those places where we missed would be measured, summed together, and then that way we could score which paintbrushes and which prototypes we felt we had more control with, quantify like. And as you can see, when we did the control, a ton of the area was missed. 40 millimeters were missed. And I can see with the other mounts, certainly other prototypes helped significantly with the control and reduced those amounts a lot. And then moving into our final design study, we also wanted a way to quantify like the amount of effort and the amount of stress that our device was actually taking off of the user. So this was really hard because we originally wanted to do some type of testing, but there's too much variance and too much bias with it. So we wanted to create like an actual like quantifiable system to do this. So what we came up with was we created another device that we can mount the mount onto. And then we attached a weight to one side of the paintbrush and then measured the amount of force that comes out of the other side that would be theoretically going into the user's mouth that they would have to counteract. So in doing this, when we did it with no foam or we did the control, obviously it would be like a one-to-one for the amount of force that goes in is the amount of force that comes out. But once we added the foam compression pieces with the mounts, those were able to reduce the amount of stress that came out a decent amount, which eventually helped us show that our mount was actually doing something and was actually helping the user with their fatigue.
The design studies also provided some qualitative data, so it was very clear that using the brush without any type of device left the painting out of control and it became a painful process. Mount 6 better fit against the side of the face to be more comfortable, while Foam 2 consistently came in contact with the mouth and Foam 1 was difficult for the user to keep consistent. In conclusion, any of the devices would have helped, however, Mount 6 with Foam 3 did perform the best. So here are the same requirements that we saw earlier, except with the results from the different tests. The only two devices that passed all the level 1 must-have requirements were Mount 6 with Foams 3 and 1. However, due to the better performance, we decided to have Mount 6 Foam 3 be our final device. As for the nice-to-haves, all of the devices failed the same requirements.
So as we said before, due to our 3 design studies, our final prototype that we picked was Mount 6, which was this one. It was the one that we altered and iterated the most to get to this point. So it makes sense that this was the one that we picked. It was also the most comfortable by far. So that was really cool. And then the final foam that we picked was Foam 3. This was by far the most consistent foam in terms of like outward texture. It's the easiest one to set up with the device as well. And it just outperformed the other ones in our design study. So this was the one that we decided to go with. And this is just another image of the full assembly with the paintbrush within it. We also have a quick demonstration of me putting on the device. So this is just how you put the device on.
So for the future, we would like to look into making other art-related devices, such as an adaptive palette or easel, or different methods for brush washing for people with limited mobility. We would also like to look more into the sanitizability of this device, as well as trying to improve the rotation and spin of the paintbrush. And then once everyone is out of quarantine, we would like to, of course, conduct testing at Seven Hills with the people that will be using this device.
And for more information, we have our QR code here and our instructables link so that if you would like to recreate the device or learn more about it, both of these are here for you to use. We would now like to open it up for any questions. And here's our poster.
Okay, so Anaya has asked, did you ever consider using a material other than foam for cushioning? Do you have evidence to suggest that foam is the optimal material for this function?
Other materials were considered initially, but the one that was easiest on hand, given our current circumstances, was insulation foam that I had at my house. Other things that we thought about were things like packing peanuts and possibly even creating like an accordion type of deal to add the compression. Many things were considered, but this was the one that was the easiest for us to do. And that's the one that we went with ultimately.
Okay. Asks, any thought to designing an internal go-between the silicone nub and the joystick that would be what was in the mouth and the brush handle, and the brush handle would end up slipping into this to be maneuvered? So a go-between between the possibly a silicone nub to go in between the mouth and the insulation foam, if I'm correct in interpreting that.
Yeah, like
yeah.
the way you would slip an eraser or something onto the end of the pencil, it would be like on the end of the brush, and that's what would actually be in the device and in the mouth.
Yeah, that could definitely be helpful, because when we were doing a little bit of human testing, when I was trying to mouth paint, definitely an issue was like, especially with heavier paintbrushes, it was very fatiguing to not just my mouth and my jaw muscles, but actually my teeth would start to hurt a little bit. So something softer on the end of the paintbrush could definitely be helpful. We could definitely look to add that in as part of our project.
Okay. This is from Annalisa. Did you try making a design that the device would be curved like a U shape instead of, or rather than, a V shape, so that it could be more comfortable for the user? Or will that be more difficult for the user to hold the paintbrush?
It was definitely considered, but part of it is that we wanted it to work with multiple face shapes. And I'm sure that if we did like some type of curve, it might not completely work either. It was something that we definitely considered, but we found that the V shape was actually really simple and just provided 2 points of contact, one on each cheek, and worked rather well for what we wanted to do. But we could definitely look into that to improve comfort if that was a continuing concern.
Okay. Rachel asks, how would you make this easier to take on and off? It seems dangerous to have it strapped on like this for breathing or choking purposes.
So one concern that we also had was about the client's hair getting stuck into the Velcro. So one of the things that's great about Seven Hills is that there's a lot of assistance. So the client did say that they usually got assistance putting the device on, and they were usually also supervised while using the device. So we didn't feel that it would be that much of a danger because they had other people watching out for them.
Okay. Anvi has asked, is there another method of wearing that might be more comfortable or safer?
Considering how many times we revisited the slope to try and improve the comfort, we feel pretty confident on that part. And as for the safety, like Ashita said, there is usually assistance monitoring the painters.
Okay. Danish asks, is it possible to make the brush or the stick that goes in the mouth smaller to avoid the device going in too far into the mouth and the throat?
So currently the amount of the brush that actually goes into the mouth is no more than ½ an inch. So it's currently a very small amount of the brush is actually going in. We could create like a hard stop or something just to like fully prevent more than what is supposed to be to go in. But the way that it is meant to be done is to put in just a very small amount. So we can definitely put in like hard stop.
Additionally, the art department already utilizes mouth painting with just a paintbrush and no mount. And so the painters have a pretty good amount of control over how much of the paintbrush they have in their mouth already.
Okay. Wayne asks, would you consider putting something soft on the holder where it comes in contact with the face? And what might you use for that?
Yeah, most definitely. That could definitely be something that we use. Even more of the insulation foam might be nice. That's a decently comfortable thing. Something like more silicone, something more rubbery lime material could also work as well. Certainly we could do that.
Okay. And then the last question would be from Will H. Is it possible to, or for the mount to be adjustable so that the slope would accommodate a wider range of your audience?
So as of right now, the mount is not adjustable, but that's definitely something that could be done in the future. But as Alex said, like because we've kept retesting the slope so many times, it's pretty comfortable and it's going to fit almost all face shapes, but it is possible to make it a little bit more adjustable.
Okay, all right. Thank you very much. So this concludes the the third session. If there are any additional questions, then I'm going to ask the current group, Alex, Ashita, and Balhan, to stay on and to check the chat so they can end up answering some of the questions that may not have been answered or would like to be answered coming up. But if we are all finished, I think what we're going to end up doing is going straight into the fourth session. You are all welcome to stay for that fourth session, and I will share the screen so we can end up looking at who's coming up. In the fourth session, we have A Closer Look, project titled A Closer Look by Caroline, Annalisa, and Amrita. Assistive Dining Device for the Visually Impaired by Alec, Arjun, and Vinny. The third presentation is the Frame Drum Mount, an adaptive device to facilitate playing the drums by Anaya, Rumesa, and Garima. And then the last one would be the Automatic Channel Changing Television Remote by Kim, Andrew, and Kayla. So Caroline, Annalisa, and Amrita, are you ready to go?
Yes.
Wonderful, excellent.
All right. Hi, I'm Annalisa.
I'm Caroline.
I'm Amrita, and we're presenting A Closer Look.
So we had the opportunity to work with an individual who has traumatic brain injury, and due to this, they have difficulty reading because of small font size and difficulty tracking words. So we hope to provide them with a device that helped them increase the size of the text and divide the text into smaller sections, which would help make reading easier and improve their reading comprehension.
So here is a list of requirements that we had come up with for our device, and we had given them each a level ranging from 1 to 3, 1 being a requirement that it is important for our device to have, and 3 being something that would be nice to have. And so some of our level 1 requirements would be that the device is low tech, and then as well as the device can increase the font size and chunk the text. We have determined if our 3 designs passed each requirement, and we decided that design 3 had passed has passed the most requirements. So we decided to go ahead with design 3.
Our first design was an app that would magnify the text and divide it into smaller sections, but this was not low tech, so it did not meet the criteria. Our second device was a magnifying table with a light tracker, but the magnifier did not divide text into a smaller section, and it was difficult to turn the page. So we moved forward with our third design, which was the magnifying bar clip, which slides up and down the book and magnifies as it moves.
So after some feedback during our preliminary design report, we decided that we would have a tray so that the device would be more sturdy and easier to use. So the first design that we're looking at is a foldable tray and have a extendable magnifying bar as well as a slot in the tray for the slider. We also had a clip so that the book itself would not shift around while using this design. In the second design, however, we simplified all of these components. We had one slider, which would essentially do the folding of the tray and the slider itself. And the slider can pivot around the rod so that it can be lifted up to allow the user to turn the page. And it can also magnify using the magnifying bar, which is not shown in this CAD design. We also wanted to eliminate the extendability aspect of the magnifying bar, and we decided to replicate the system that we have on one side on the other, which would make the device as a whole simpler to use and simpler to build. So this is a short video about our final prototype that we created. As the user reads, they would move down the magnifying bar, and when they're ready to flip the page, they'd lift it up and repeat the process. And next to this video, you see a picture which shows how much the magnifying bar actually magnifies the text. And we had a 1.5 magnification bar. And our user specifically wanted a bar that would highlight the text or change it to a different color. So we chose a yellow bar that would make it look like the text was highlighted.
So the first design study that was performed was using or testing 8 different sized holes that were 3D printed, and to test for the correct amount of friction between the rod and the slider, because we want the slider to have enough resistance so that it doesn't fall or like it doesn't slide on its own, but have but it still will be able to move freely up and down with minimal effort. And so the user tested each hole and qualitatively rate each hole from most friction to least friction.
For our second design study, we looked at the capacity of the device. So we tested several different size books, ranging from a sheet of paper to a small chapter book. And we were looking at how warped the text became. So as you can see in the top right picture, as the book gets bigger, the bar does not sit flush to the paper, which makes it difficult to read. So we decided that the optimal size was ranging from about 1 piece of paper to the size of an average magazine.
So our third design study was to have 3 different participants use the device for 10 minutes. And then after they used it, they would rate the device overall, and then rate how disturbing flipping the pages was, as they would have to lift up the magnifying bars to flip the pages, and then give any feedback they had about the user experience. So the average overall rating was 8.4, and the average disturbance rating for flipping the pages was 1.7, 1 being not very disturbing and 10 being extremely disturbing. And the sample size is very small. However, this is what we had available to us, and it doesn't represent the community as a whole, but it does show that people would be interested in using the product, and it is an effective product as a whole. Some of the feedback that we got was that different parts of the page magnified differently due to the curvature of the book. So closer to the spine of the book, there is more of a curve, and the magnification there is not the same as the edges of the book, where it is very flat. And we also noticed that the book shifted around while sliding the magnifying bars. And to solve this problem, we had originally thought about having a drawing board clip hold the magazine covers down. However, we were not able to order these parts due to the circumstances.
So in order to construct our device, you would have to 3D print the 6 parts. So 2 of them being the slider pieces, and the other 4 would be the end pieces. And then you would put the magnifying bar through each slider and glue it in place. And you would insert you would also attach the end pieces to either sides of the rod as well, and screw it onto the side of the wooden board and repeat on the other side.
In conclusion, our device, we went forward with the magnifying tray. It's composed of 2 metal rods that attach to opposing sides of the wooden tray using the 3D printed components. And the magnifying bar is attached by the box leg sliding component. And this sliding component allows the magnifying bar to move up and down the page, as well as pivot around the rods so that pages can be turned.
From the feedback that we've gotten so far, some of the future extensions that we would implement is to make the hull higher to allow thicker books to be read, and also to help with the warped text. We would also try creating easily replaceable and adjustable parts so that we could have customizable magnification, as well as allow users to read different types of books ranging from magazines to the novels that we showed.
Thank you for watching. We're now open for questions.
So I have a question. How easy is it to interchange those magnifying bars to increase the magnification?
So currently, the magnifying bar and the slider is a complete system because the magnifying bar would be glued into the slider. So if you would want to change that slider itself, you'd need to take out one of the stoppers and replace the whole magnifying bar and the slider system, which means that you'd have to 3D print another slider as well as the magnifying bar and glue them together. So it is kind of a process, and we haven't made it very customizable yet, but it is something that we're looking into.
What would you need to do to make that more user serviceable by being able to change that magnification around?
Well, I think the main thing that we could do is add in the 3D printed component, make sure that the magnifying bar can slide in easily as well as slide out. And that way we won't need to glue it, and it can be easily interchanged with another magnifying bar of that size.
So almost like, you know, some of those clips on a tripod that keep each leg of the tripod stable, something like that?
Yeah.
Okay. All right. Wayne asks a question, would you think about having your stoppers having multiple holes so you could change the height of your magnifying bar?
We haven't really thought about that, but that would definitely solve the issue of having thicker books. However, since it is closed on both ends, they would still need to remove one of the stoppers to put it, or both. They would need to remove one of the stoppers to increase the height so that they can read the thicker books.
Okay. What has been, okay, I'm sorry, Alma asks a question. Maybe a magnetic end to the magnifying bars would help them snap in and out for better interchangeability. What are your thoughts on that?
Yeah, that's definitely a good idea. I don't think we actually have thought of that. So yeah, that would make it a lot easier for the user to attach and take out each magnifying bar. But we would have to also make sure that each magnifying bar would be the same size.
Okay. All right. So that is awesome. One last question. What has been your most difficult challenge that you've encountered in this project, and how have you surpassed or surmounted that?
I think one of our main challenges was just kind of figuring out how to put the actual device together, because we're all in separate locations. So we had to have a lot of communication about like who was going to be buying these parts and when to meet with each other to put it together, and just the general like organization of it all.
Yeah, I definitely agree with that communication aspect. I think that we also needed to know how to rely on each other's strengths, because not all of us could work on the same things at once because we weren't as Caroline said, in one location together. So we all had to divide up the parts and really trust each other to know that we would get those parts done and come together as a whole to create the product itself.
Okay, so I'm going to ask the three of you to end up sticking around and answering any of the questions that remain in the chat room while the next group, Alec, Arjun, and Vinny, end up getting set up. Their project is assistive dining device for the visually impaired. Thank you.
Hi, I'm Alec.
Hi, I'm Arjun. Hi, I'm Vinny.
So our device was making an assistive dining device to help people with visual impairment and speed reading difficulties.
So the motivation and problem statement for our project was to, most people with visual impairment have struggles throughout life and especially eating. And so we focused on assisting them in being able to locate the food and picking up that food. The other problem that was also part of our project was speed eating, as some people eat food too fast and that can be a choking hazard or just be problematic. And you're aiming to solve that as well. So the exact goal was to create a plate for the blind client that allows them to locate food and reduce the consumption level to a safe level. So the motivation was that this will not only allow the caretakers to allow the clients to be more independent, but also allow them to not sacrifice hygienic eating practices while they're eating food. So our goal was meant for our clients specifically, but our project could be expanded upon for anyone who has a visual impairment, but just wants to be able to eat more independently. So here are a few of our requirements. Level 1 marks the fact that all these requirements are one of our most high priorities. And we generally focused on comparing them to the level of a regular plate in terms of not being able to slide, not tipping, no risk of spilling, and it should be safe to eat with food. Here are our level 2 and level 3 requirements. These are a bit not as high of a priority, but they were still important. We try to keep our plate as cheap as possible while making it safe and portable and being able to be safe from drop testing. And then we also tested a few extra things such as microwave safety. So our first preliminary design was a sensor plate, and this plate would have consisted of temperature sensors and magnetic sensors within the plate and a accompanying spoon. And the way this would have worked is the sensors would have worked together to create almost a coordinate plane, and that way, based on where the user's utensil is, it would help them locate the food. The issue is that this design was not feasible due to how expensive it would have been, and also it would not have been durable. Our second preliminary design was a partition plate, and this had dividers, as you can see the picture, and it would have had small magnets attached to the side, and this would help the user locate food by feeling around the edge of the plate, and it would tell them what type of food is where. The issue is that this was not exactly what our client was looking for, as it did not help with slowing down speed eating. And then our third preliminary design was a high-sided plate with contours and curves, just easier to call a contoured plate. And this would allow the user to scoop food very easily. And in our preliminary design, we also thought about having a shock-absorbing spoon due to the fact that the inconsistent depth of the plate would make it odd to move the spoon around and have some places be higher than others. So our original design did not suit our client's needs specifically, but it provided a great starting point to build upon.
So for our CDR design, we chose to pursue the contoured plate design because it was the closest to what the client was looking for. So the only change that we made from PBR to CDR was adding the cones in the recess. and that would be to help prevent speed eating because the cones provide an obstacle that the user needs to navigate around, which takes up time, therefore slowing the rate of eating. This plate would have Dyson on the bottom of the plate to prevent it from turning or slipping. Also, the spoon would not be shock absorbing. We had concerns about it causing difficulty with picking up the food. So it would just be a custom spoon with like a deep head and a built-up handle. So we decided not to go with the partition plate because it was more focused on identifying the type of food rather than locating and picking up the food. And we decided not to go with the sensor plate because, as Arjun mentioned, it was very expensive and it also wouldn't have been durable if it was dropped or exposed to extreme heat or water. And some of the changes from the PDR design or the cones, the spoon. And we also considered in PDR using a raised edge like a lip to aid with scooping the food out of the plate, but we decided not to go with that for CPR.
So our first design study was intended to understand how effective the spikes and contours were when locating and scooping food. And the way this study was conducted was, as you can see to the right, Alec filled the top of the plate with Cheerios, and he then closed his eyes and used a normal dining spoon to move all of the food from the top to the bottom and then transfer it to a different container. And then we timed that and recorded the transfer rate. So the takeaways were that the spikes were almost too effective at slowing down speed eating. We noticed that the issue was that the spikes were extremely tall and unnatural, and the amount of time it took to navigate around them was excessive, and we wanted to decrease the time they increased that it took to scoop the food. And then the second takeaway was that the contours worked very well, and all the food was moved into the recess. With about 3 or 4 swipes of the spoon, Alec was able to get all of the food from the top to the bottom with his eyes closed. And then the third takeaway was that the scooping was quite difficult as there wasn't a wall to scoop against and guide the food into the spoon. And that made it difficult when there was a little food left, and Alec was trying to get everything into the spoon and then transfer it. So based off of that design study, we designed our second iteration of the contoured plate. So in this iteration, the spikes were made shorter and wider, making them easier to navigate, but they were still an obstacle. So this ties back to how the initial spikes were too effective at limiting speed eating. Here, they still, we had the idea that they would still limit it, but they would make it easier to navigate. And then we also designed a front wall, as you can see, and that would guide the spoon towards a singular point of exit. And what this would do is it would aid in scooping the food, as the wall could be used to guide the food into the spoon, and then it could easily be scooped out of the plate and then into the different container. And then our second design study looked at testing the second iteration. And the takeaways were that the short and wide spikes were much more effective at limiting speed eating while allowing the person to scoop food. And then the front wall was extremely effective at guiding the food into the spoon and then using the singular point of exit to take it out of the plate.
And so this is basically the version that you guys just saw, but we decided to add a spoon. So we left the plate as it was since we deemed that it was efficient and it solved the purpose at hand. And so the spoon right here has a very big head, almost like a soup spoon, in order to take up as much food as possible. And the handle is also built up in order for comfort and to make it easier to use. The other thing that we also added was Dyson to the bottom of the plate in order to make it more stable and to prevent slipping. So the purpose of this design was just to ensure that our spoon worked in correlation to our plate and to make sure that there was no changes need to be made. The takeaways that we got away from this one was the spikes work very well with the new spoon and they almost complemented each other. The shape of the spoon helped take enough food but not too much food. And going back to the point about the spikes being too effective, we found there was a small trade-off between how effective the spikes were. And with the spoon, we found a happy medium where it was effective but not too effective. This is the last design study that we did as sort of a durability test to make sure the plate and the spoon were safe for other things. So the thing that we first tested was a drop test. We dropped it from various heights from 1 to 5 feet. And after dropping it multiple times, there was no visible damage or degrading in the plate. So it seems to be drop proof. And the other thing that we tested was also in the microwave for 30, 60, and 90 seconds. And after all those microwave times, it was also fine with no deformation or anything like that. So as long as the user does not put it on the microwave for too long, it should also be fine.
So here you can see, again, the CAD models of the final design. So it's the contoured plate with the shorter cones in the front wall, which were both shown to be very effective during the design studies, as well as the built-up spoon with the deep head. So here you can see pictures of the actual 3D printed models. These were printed using PETG. And to get to a final product, they would need to be coated in a food-safe epoxy, specifically one called art resin, but due to current circumstances, we were unable to complete that step. So this is kind of the final prototype without the epoxy coating. So here there's like a short video showing how to navigate the spoon. So as you can see, you bring the food down from the top area, and then the spoon kind of needs to tilt to get around the cones. And that causes some time, but it's still able to get the food out of the plate by going towards that singular point of exit caused by the front wall. So here you can see the requirements shown earlier in the slideshow presentation, along with how each prototype compared for that requirement. As you can see, the first prototype, the contoured plate V1, failed the level 1 requirement that it could be used by an individual with limited precision, because the cones were so difficult to navigate that it was just very difficult to use. Contoured plate V2 and the final prototype with the custom spoon performed very similarly, but the spoon just made it a lot easier to use, and it was something that our client had specifically mentioned. Also, it's possible that with the food safe epoxy coating that the device would be dishwasher safe, but we were unable to test that. So some future extensions for this project would include making the design more aesthetically pleasing, whether that's through some physical changes or just materials. We were also thinking of looking into different materials to make it more durable and longer lasting. We could also do more testing with more clients, get their feedback. And we were thinking of potentially creating a fork version of the design, or potentially combining the fork and the spoon into a kind of custom fork.
So a few lessons that we learned were understanding the client specific needs before coming up with our designs. And the reason we felt that this was a good lesson was that we did come up with a partition plate design, but once we understood that our client was also looking for the for scooping and speed eating, we realized that our current design would be a better place to start. So we felt that because we should have understood our client specific needs before making the designs. And then looking into multiple approaches was also a very helpful thing, because we were able to, I guess, pick features from various approaches and use all the ideas that we gathered from all our different approaches to come up with the most optimal design. And then we also used an iterative design process. And this was very helpful, as we're able to single out design flaws, change them, test them, and then continue. And it was much easier to arrive at our final design. And then, of course, collaborating on testing a physical device without being able to meet in person is quite difficult, but we were able to do it, and we feel that despite the circumstances, we were able to arrive at a good final product. So here are our references, just a few different competitors, and we did draw a few ideas from them, which is why we cited them.
Okay, so time for questions. Thank you very much. Doreen asked the question, are you planning on testing the spoon with a blind person? The Seven Hills Day Hab programs may reopen July 1st with a limited number of participants. I would love to see it in person if possible. Note, I am the occupational therapist for the Day Hab programs.
So we were planning, as of course, Alec did have his eyes closed when he was testing. So it kind of simulates having a blind user use the plate, but of course it's not perfect. So in the future, it would be extremely helpful if we're able to conduct a design study where we have a visually impaired individual using the plate, and where we would be able to get really good feedback from them and make any changes if necessary.
So to follow up on that question, Marzook asks, how did you test the fact that it was slow enough or too fast enough for eating by those clients? Was there some quantitative test involved, or was it just qualitative?
We felt that, oh, go ahead, Alec.
We didn't really know how to quantify that because it depends on the individual, but we mostly took it as whether or not it provided a significant obstacle to in comparison to how it would react if there was nothing there. So we kind of it was qualitative, but it was in comparison to a kind of control basis of if there was no cone there, did it cause a significant impact in the speed that I was able to transfer the.
Okay. So how might your design and the system that you ended up designing with the plate or the bowl and the spoon, how might that differ than what has been developed in the past?
So we did look at a few different competitors, and there was one competitor specifically that we found really interesting. It was called the Eatsy plate, and it had pretty much the same concept that we implemented, which was having contours and curves which guide food into a recess, and then you use a elevated wall to scoop the food. The issue was, first of all, the CAD files just were not available online, so we wouldn't. So Seven Hills would not be able to find those files and use that plate. And then also those don't that design did not limit speed eating at all. It probably would have increased speed eating, considering how simple it would have been for the user to guide food into the recess and scoop it out.
Thank you. Wayne asks, for larger production, would you see making a mold for your plate and spoon? This would allow it to be produced by injection molding.
Yes, so that would be a very effective and efficient method of production. It would also allow for the use of hardier plastics, making it more durable, and getting rid of the need for the epoxy coating. But based off of the tools that we had available, we had to 3D print it. But for considering mass production, injection molding would probably be the process to go with.
Okay. And then last question, Andrew asks, does the plate need to be held at an angle in order to eat from it?
So it doesn't necessarily need to be held at an angle. It lies flat on the table. However, it does need to be in the proper orientation, specifically with the recess facing towards the user, there's a small bump on the front edge of the plate to help with that orientation.
Okay, all right. So I'm going to ask the three of you to stick around and keep your eye out on the chat room to see if there are any additional questions that might need to be answered from participants. But we're going to end up going into the next presentation, the drum frame mount, an adaptive device to facilitate playing the drums by Anaya, Rumesa, and Garima. Thank you very much for that presentation. And are you guys ready to go?
Yeah.
Hi, everyone. My name is Rumesa.
Hi, I'm Garima. I'm Anaya.
And today we'll be presenting to you our drum frame mount.
So playing music is an integral part of many people's lives. However, for individuals with limited hand mobility or loose hand grip, it may be hard to play instruments such as the drums, which involves you holding onto the drum and playing it at the same time.
So the goal of our project was to engineer a frame mount to stabilize and position a drum for individuals with limited hand mobility. And our competitors, so our first competitor was the Remo Paddle drum clip, which is currently used by our client. And a good aspect of this is that it's very versatile and you can place the paddle drum in different orientations, but our client did say that it was flimsy. Our second competitor was the drum straps, but these straps are only used for storing and holding the drum rather than playing it, and it requires strapping around the user. And then our third competitor is the Grover drum stand, and but you can only position it from the floor. So it features a clamp that clamps onto the rim of the drum, and then it stands on the floor.
So some of our requirements that we decided were most important largely center around the drum being able to be held in the device without slipping even while the user is banging on it. And also the device should be able to attach the drum to wheelchairs, and also the device should be able to store drums of different sizes, as well as allowing it to move and being cleanable and not using a non-foam type material. As well, some more less important requirements were that it could also attach to tables and that it would be easily reproducible. Also, the users of the device should be able to be knowledgeable about how to attach it easily enough. And we also had the budget constraint of that this device should be made of less than $30 worth of materials. So some of our preliminary designs, one of the first of the designs that we came up with initially is the telescoping adjustable drum holder. So this design kind of consists of a drum holder with multiple concentric circles that get smaller as you go down. This stack of circles can be adjusted to be taller or smaller if needed, and the bottommost solid circle will support the appropriate drum size and can be adjusted to the right size if needed. It also has a clamp on one end that will attach to either tables or wheelchairs.
So our second preliminary design was a wheelchair, and the other would hold on to the rim of the drum to maintain the sound quality. And we looked into G-clamps because they're industrially used, and it's like one of our reliable designs that we actually went into. And also we looked into the miniature table.
Yeah, so we also looked into the miniature table as one of our preliminary designs.
And this would work as a small table that could be added to a wheelchair tray or a table that someone's standing at. However, we decided not to move forward with this because it did not meet our client's requirements.
So we actually went on with the two-way clamp, and we expanded it for 3 prototypes. So the first one is just the 2 clamps, but with a straight rod connection. So this is the most basic functioning prototype. And as you can see to the right, this is the clamp frame, and this is the clamp protector, and this is the screw. And those make up the clamp, and then you have the PVC pipe that connects the 2 clamps, and this is just how we would connect the PVC pipe to the clamp. And our second prototype is very similar, except you have a metal hose neck connection. And so you have 2 3D printed G-clamps, as mentioned before. And the metal hose neck allows for more mobility of the drum to suit the client's needs. And our third one is the slotted ball hinge. And it's just similar as before, except now you have the slotted ball hinge. And this really behaves similar to an arm. And it has locking mechanisms. So it allows for mobility, but it also has locking mechanisms, which make it a better prototype because it allows for stability as well.
So the first thing we really looked at in terms of our build process was how to build our G-clamp. The original version of the G-clamp was used for our proof of concepts during the critical design review. However, it couldn't connect to a PVC pipe because it wasn't designed that way. So we had to modify it by adding a pole at the end of the G-clamp as well as a screw hole so we could connect it to our PVC pipe. So yeah, so this video just shows how the original versus modified versions of the G-clamp looks like.
So another part of our device that we had to iterate a lot was our slotted ball hinge. So the original file that we got from GrabCAD looked as like the one that you can currently see on the screen. So this one had plates on the end that we decided were not compatible with inserting into a PVC pipe. And also when initially printed, parts were fused together and the leg part of the joint that was supposed to go into the slots could not because the slots were too small. So then we moved on to our second version where we removed the plates from the ends of the hinge, but we realized that we still had to modify the cylinders so they could be small enough to fit inside a PVC pipe. So then we had our third version, which was when we split the joint into its 2 separate parts. So we had the ball part where we added a cylinder and a screw hole, and we did the same thing for the socket part. And that way they could both go into the PVC pipe and be screwed in. And finally, we made them into an assembly, and we printed this assembly out using 3D printing, but it ended up getting fused together and was not mobile at all. So we had to reprint it. And as you can see, it's there. So then our final version, we made the joint a little straighter to avoid fusing, and we ended up printing it out. Although we could not implement it in time, it is fully functional and will be implemented in the future.
So we also conducted various design studies on the components of our prototype to make sure they were usable in our final design. The first thing we tested was the metal hose neck to see, because one of our primary concerns when we were considering it as part of the design process was that the metal hose neck would bend or deflect when it was under force from someone hitting the drum or just from the weight of the drum itself. So we decided to test the metal hose neck to see by how many angles it bent when different weights were exerted on it. And as you can see from the graph, the metal hose neck doesn't deflect or bend much until around 650 grams, but after that it shoots pretty high up. So this means that it probably won't be able to support a paddle drum. It'll probably deflect by around 15 degrees or more with a normal paddle drum. So we also conducted 2 design studies on the G-clamp itself. The first one was for testing the grip strength of the G-clamp. And the way we did this was we performed a variety of qualitative testing on the G-clamp to see, to check its grip strength, and then we would award it points. The maximum amount of points that the G-clamp could earn in a trial is 10 points, and we repeated this over different masses and different diameters of containers to see how the G-clamp did. Just a brief highlight of our major findings was that the G-clamp was pretty good at gripping. It wouldn't slip most of the time. However, there was some weakness around the screw itself. Our last design study was on the G-clamp as well. We conducted a design study on the G-clamp to test the strength of the G-clamp and the screw of the G-clamp. So we did this similar to the first G-clamp design study, where we ran some qualitative testing on the strength of the G-clamp, with the maximum amount of points you could get being 9. And then based on that, we tested different diameters and different weights on the G-clamp to test it for strength. Just as some brief highlights, the G-clamp did show signs of deformation and tension at higher masses, which led us to which led our team to decide to make a shift in our design and actually incorporate more sturdy materials in the screw, as we'll discuss later on.
So this is our final prototype and consists of the 2 clamps with the PVC pipe connected. And here are the different ways that you can mount the 2-way clamp prototype. And as you can see in the first picture and the third picture, the reason why we attach it to the chair that way is because we're hoping when we do attach it to a wheelchair, we would attach it to a pole that's on the lower side of the wheelchair frame. And so that would allow the client to access the drum at their own eye level. And so that's the first and third picture. And the second picture shows how you can attach the prototype to the table. And this is a video of how you would mount the drum to the prototype. As you can see, we're tightening the screw onto the drum. And now we're just going to mount it on the table. As you can see, it can support the weight of the circular container. So we noticed, based on our projections, that this prototype would actually outperform the other prototypes, but we'd still have to see with the slotted ball hinge. And this prototype is versatile for various positions in carrying the drum. But we also noticed that the screw breaks easily in the G-clamp under tension. And depending on how you mount the drum to the clamp frame, it may reduce the sound quality. So if you attach it to the rim, which is what we were originally hoping, then it wouldn't affect the sound quality. But if you attached it like this in the picture shown, then it would affect the sound quality.
So this is sort of a chart of how our final prototype meets our final requirements. So for functional requirements, our final prototype is able to hold a drum, but it does cause a little bit of slipping often, and due to the fact that the screw does not hold well against it. We also were able to see that the device can attach to places such as wheelchairs and tables, but we're not completely sure yet if it can attach to all wheelchairs, as we have not had the ability to test. The device is definitely adjustable, but as of now cannot allow the instrument to swing or move. And it is cleanable and made of a non-foam type material. As said before, the device can attach to tables. It's easily reproducible because most of our parts are 3D printable. The user and caretakers will have the ability to know how to attach it because we will be making an instructables. And as for durable materials, some of our device is not as durable as we initially intended, but this will be resolved in the future, and we stayed within our budget of $30.
So in the future, we have an action plan in place, and what we're hoping to do is actually first fortify the G-clamp screw by inserting a metal-based rod inside of it to ensure that it can withstand the force of a paddle drum or someone hitting on the paddle drum, as well as the entire system being clamped on a table or a wheelchair. Another thing we want to do is add rubber stoppers to the end of the G-clamps to ensure no slipping when the clamp is actually on the drum itself. And the last thing we want to do is build the slotted ball hinge into the PVC pipe as we originally intended. With more time, this is actually going to be our next plan of action, so we can test out the slotted ball hinge design in comparison with our original design.
So now we're open to any questions.
Thank you so much for your time.
Thank you. So Joy asked a question. Have you considered using DISM to help with slipping?
Yes, as we mentioned in our future studies, DISM would be a great material to try out to ensure that there's no slippage on the clamp itself. And yeah, we would be looking into using that.
Okay. Kim asked the question about considering changing or optimizing the clamp for the curved shape of the drums that you are working with. And I would also extend that question, the curved shape of the rail on the wheelchair, if that's a part of the design.
Well, we didn't particularly notice. We actually tested on circular containers to sort of mimic the rounded shape of the rim of the drum. And we didn't really notice a problem with the curve shape. The clamp seemed to clamp well onto that, but this could be a future consideration if we notice problems with actual drums.
Yeah, and another thing to point out is that the clamp itself has a clamp protector that allows it to adjust the pressure the clamp exerts on the surface to uneven surfaces, for example, slanted surfaces or even circular surfaces. So I think that's what really helped us help the G-clamp get a better grip on circular surfaces, but with more rigorous testing, we can see if it would be necessary to adjust the shape.
Yeah, we could possibly modify it, maybe make it wider so that it can easily grip onto cylindrical surfaces.
Okay. Wayne asked the question, would you consider to put more than one slotted ball hinge to give you more adjustability to it?
That's an interesting question. We hadn't thought of that originally because we were thinking about first testing the one slotted ball hinge and seeing what would happen.
But it sounds like a great idea. We could probably.
Well, we weren't sure exactly how we would use two, because we're using the slotted ball hinge because we would allow the user to have mobility to adjust the drum at at various angles to their choosing. But we're not sure as to why we would need two.
So then I'll ask and extend that question. What might be some of the advantages that you could think of to have more than one slotted ball hinge? But on the other end of the spectrum, what might be some of the disadvantages?
Well, I at least suspect that it may make it a little bit more complicated, but I do think that any more adjusting joints will the slotted ball hinge will probably increase mobility.
Yeah, it would increase mobility, but it would also put more stress on the clamp that's attaching to the wheelchair or table. So that's a con. So, and it could possibly break the clamp screw, but we are looking into making that stronger. So maybe that's something we have to consider.
Yeah, it'd be a really interesting thing to work on in the future as well.
Okay. And then Arjun asks, would fortifying the G-clamp screw change the flaws you discovered in the design studies with the inability to support a lot of weight?
Graham, I
well-
think you're muted. Well, yes, we do think that it would help because we noticed that putting force on the clamp kind of made the part of the screw that was close to the clamp, the clamp hole, that made it very delicate, and so it was easily breakable. And so if we use a metal rod inside the plastic 3D printed part, then we believe that that would help.
All right, so I'm going to ask the three of you to stick around and keep your eye out on the chat room to see if there are any additional questions that need to be answered. And so the last group is Automatic Channel Changing Television Remote by Kim, Andrew, and Kayla. And if I could just remind all of you, the panelists and attendees, you can write your questions in the chat room and I'll ask them. And they will definitely get addressed. I'll also, while the next group is getting set up, I'll also remind everybody that there is a feedback survey that if you have an opportunity to fill out for session number 4, I'll put that link into the chat as well. And I would appreciate any type of feedback that you have either on the project, the product, or even the process. Okay, Kim, Andrew, and Kayla, are you guys ready?
Yes, we are. Oh, yes. Hello, everyone. I'm Kayla Freeman. I'm Kimberly Stockeye.
And I'm Andrew Yang.
And our project is an automatic channel changing television remote. So a standard television remote can be very difficult to use for some users. It requires somebody to remember, if they have a specific show they want, what channel that show is on, what time that show is on, as well as they have to have the ability to use many very small buttons on the remote. So the goal of this project is to eliminate some of the difficulties associated with using a television remote by having a television remote that only has one button to power the on and off function of the television. And other than that, it will change the channels regarding with as predetermined by a user for what channel and what time they want to watch their specific show, so that they don't have to remember those things.
So displayed here is a completed set of requirements that we set for our device. Some of the most notable of these are that the device communicates with the television in order to automatically change the channels to user-specified channels at preset times, that it has a button which is large enough for our client who is legally blind and suffers from vascular dementia to either see or feel. The button should also provide tactile feedback when pressed. It's also required that this device provides the user with audio feedback when it automatically changes the channel, and that it can be attached to the client's wheelchair or bed rail. Some of the other requirements on this list include the requirements for battery life and durability, as well as the existence of a user interface and or voice control capabilities.
So before we started designing our own product, we looked into 3 main competitors that we thought did somewhat similar features. So 3 we looked at were the Flipper Remote, the Harmony Elite, and the Kava Control Center. So the Flipper Remote was the remote that we were actually given as a competitor that didn't work, but we still looked at it anyways, and we found that even though it was affordable at only $35 and was also easy to use because of its somewhat large buttons, The buttons were not large enough for the user to see and also did not have the capability to automatically change channels, which is a key requirement. Another remote we looked at was a Harmony Elite. So this is a product made by Logitech that supports voice commands and has an intuitive touchscreen interface. However, it is extremely expensive at $350. It doesn't have the ability to change channels automatically, which is a key requirement, and also has small buttons that aren't easily visible to the user. And similar to the Harmony Elite, there's a Kavo Control Center, which also has voice commands, but is expensive at $160 and does not have the ability to change channels automatically. And like the Harmony Elite, it has really small buttons.
So these three are our preliminary designs that were proposed at the beginning of this project. The first of these is what we referred to as the one button design. As the name suggests, this would have one button, which would allow the user to communicate with the TV. However, at the early points of this process, the exact functionality of this button was not yet decided on. The Raspberry Pi would translate the signal from the button to an infrared emitter, which would allow for communication directly with the television. The main priority in this design was simplicity and user friendliness, but unfortunately, this came at the cost of overall availability for functionality. Our second design would be virtual assistant based, using either an Amazon Echo, a Google Home, or a similar system. This design would be controlled by a variety of voice commands that we would make custom for the client. The virtual assistant would take the command that it heard and communicate it using the built-in Bluetooth functionality of the device, either to a commercial Bluetooth receiver or a custom-made Raspberry Pi Bluetooth receiver. Either of these would be connected to an infrared emitter for communicating directly with the television. This design could have many more functions implemented, but it runs the risk of having our specific client having the difficulty of remembering all the voice commands that we made for the device. And that would mean that this device would not be able to complete its goal of changing the channels at the right time. The final design that we had was the 3-button design, which tried to compromise between the simplicity of the first device and the greater functionality of the second device. Technically, this device would be extremely similar to the first, but the 2 additional buttons could allow for extended functionality such as volume control or automatic channel override. So after this, we ultimately decided to work with design 1 because it was determined that user friendliness was much more important than advanced functionality. This final sketch also has a few design changes from its predecessor, including a switch from a Raspberry Pi to an Arduino in order to reduce costs, and also adding additional modules in order to complete the device's functionality and fulfilling the requirements of the device. These additional modules include a piezo buzzer, which would provide the user with the audio alerts when the channel was changed, an independent power source, which means that this device could be run without having it being plugged into an external power source like a computer full time. And finally, some way of keeping track of the time. This could either be a real-time clock, which keeps track of the time itself as a clock, or a Wi-Fi module, which would retrieve the time from the internet and maybe even more information for advanced functionality. Also shown to the side of the slide are a few of our proof of concept models. The top shows a simple button setup, which proved that the Arduino could receive signals from a button press and send out a signal. For the purpose of testing, this was an LED pulse. And the bottom shows a simple buzzer setup, which proved that the Arduino could make a sound that would alert the user that the channel was being changed.
So for our first prototype, we built off of our CDR design and our proof of concepts, and we're able to put together a simple system, which was an Arduino Uno, which was connected to an IR emitter, an IR receiver, and then we found out that this was capable at changing the channels. However, since we didn't have a real-time clock module, it wasn't actually able to change the channels at specific times and only change the channels when it wanted to do so. In addition, this prototype didn't have a button, which meant that the user had no input into when the Arduino was transmitting a signal, and was also not contained in a casing. And so in this case, a casing was necessary to make it more user accessible and less messy.
So the second prototype had the addition of a button because we had a large button arrive that worked with the Arduino. And this button had the capability to turn the TV off and on command. And in addition, this prototype implemented the real-time clock module, which allowed the prototype to change the channel at specific times. In addition, there were still the similar drawbacks to the first prototype as well. For example, it still did not have a casing. And in addition, it is a very power intensive system, as there is no way to turn the Arduino on and off.
So for our third prototype, we built off of what we did for our second prototype. However, instead of using a real-time clock module, we attempted to use a Wi-Fi module, which we hope would be less power intensive. And so what we would use the Wi-Fi module for was we use it so we could connect to the internet and then get the time from the internet that was extremely precise. And so by doing so, we didn't need the real-time clock module running at specific times, and we could have it call the Wi-Fi module only when it was necessary. However, we didn't end up using this because it did not wake the Arduino when the button was pressed, and also the time output was unreliable.
So in addition to the Arduino prototypes, we also had to CAD two different prototypes for the casing itself. So the first casing that we had was based around screws and nuts and bolts. So up top, you will see a nut, and that was specifically made for the button because the button actually has threads on it. However, we do not have the exact dimensions of those threads and their size and how many there are in each inch. And it was, in order to have it accurately fit the design securely, we would have to iterate over this design many, many times, which was not feasible with current circumstances because we could not keep going and retrieving prototypes. In addition, in this casing, we also had screws or holes for screws for both the emitter module, the Arduino, and to hold the case to the lid of the case. So for our second prototype, the key thing was we took out all of these holes, and the only holes in the prototype are for the button itself. It just inserts in and it is secured via Velcro. In addition, we have a hole for the emitter and a stand for the emitter for it to be attached to, as well as a hole on the side so that a cord can be inserted to easily update the Arduino's code.
So in the end, we combined the best of prototype 3 and also CAD prototype 2. And then we ended up creating a casing that would envelop not prototype 3, prototype 2. And then we end up using the casing to envelop the Arduino, which in the end used several components. So first we had the casing, and then we also had the IR emitter and receiver inside. We also had a real-time clock module, which kept accurate time. We had a piezo buzzer, which buzzed when the user pressed the button and also when the channels were being changed. And then we also had the button on top, which was purchased from Adafruit and was able to turn the Arduino on and off based off of user input. So in this video, you can see a brief demonstration of the Arduino changing channels on its own. So because I don't have cable TV at my house, I instead use the Google search function on my TV. And you can hear that when the Arduino is transmitting the signal at the specific time, it prints it to the serial monitor and also beeps. And so in this video demonstration, you can also see how the button works. So you can't exactly see the button, but you can hear the button. And so when the button is clicked, it either turns off or turns on the Arduino. And also you can see the real-time clock reading times.
So in addition, after building our prototypes, we still needed to test them. These tests were, the first test is the emitter distance test. And so this was testing the range of the Arduino and the infrared emitter. So we measured how many times the Arduino successfully communicated with the TV at specific distances, and we found this to be between 4 and 4¼ meters, which is approximately 13 feet. In addition to this, we also tested the angle of the Arduinos to see if it was if it worked at various angles placed around the TV. And so we tested it between 0 and 90 degrees, and it was successful up through 80 degrees. In addition, we have 2 more tests that we have plans to implement over the summer. We are currently unable to run these tests because of material. We do not have all of the materials to implement them, but we are planning to test the battery life and the durability of the Arduino, either by both monitoring how much charge is left on the battery after using the Arduino for a specific amount of time and doing specific actions. And then the chop test will be using dropping the casing in the Arduino and monitoring any damage done to the prototype.
So once again, we have the list of requirements that we set up for the device at the beginning, but here we have also added whether or not the prototype and the final design fulfilled this requirement. A few important notes from this slide are that due to the aforementioned testing limitations, we were not able to decide whether any of the prototypes or the final device fulfilled the drop resistance requirement or the battery life requirement. In addition, only one level 1 or primary requirement was not filled by our final deliverable design. And this was the ability to clamp onto the wheelchair bed rail. This is due to the fact that we never received information such as dimensions for these 2 things, so we cannot accurately design a clamp or other fastening device that would accommodate these. And then finally, the majority of the other requirements which were not met by this device were those which dealt with voice control functionality. These were initially proposed when the virtual assistant design was still a major consideration, but they were not reasonable expectations to beat without having a virtual assistant. So from the testing and requirement analysis, our team concluded that the current product is functional and satisfies all the MVP requirements that are currently possible, that the button is able to control the state of the Arduino, waking it and putting it back to sleep, and the Arduino automatically changes the channel based off of the current time as read by a real-time clock.
So like what Kim said, all the MVP requirements that were set for us at the beginning that we could end up doing have been completed. However, we do have several ideas that we would like to implement in the future. That could be either this summer or next year or for a future project. So one thing we'd like to do, which would be more like another project altogether, would be to create an app that allowed the user to program each show and its times based off of whatever changing case. And then also have the Arduino interact directly with the cable box, which would allow it to know of any changes to the schedule of a show. And also, if we did it this way, we would be able to get more detailed descriptions about each channel and each show that is currently playing on that channel. Another more short-term extension that we'd like to do is we would like to add the holes on the 3D printed casing to allow for the Arduino to be screwed down, because currently what we have is a Velcro solution, which is not exactly the most permanent, is not the permanent solution that we will end up wanting to use.
So throughout this project, we faced many challenges, especially because of outside circumstances that were outside of our control. One of which being that we had to be separated for the course of this project. But we managed to learn a lot throughout this project about how to work together and how to work as a team, and especially about communication, as it was difficult at first for us to describe where each of us was with the prototype and our work with the prototype. For example, what parts of the CAD casing were completed, what parts of the Arduino are working, and what parts are still malfunctioning. And so we learned how to accurately use videos and photos to demonstrate where we were in our progress. And in addition to this, we learned the importance of making a product that is very easily adaptable, as this can be used for many people, both those, and as long as it can be changed for the shows that the user wants, the shows and times. That is all for the presentation. Now we will be taking some questions.
Good, thank you so much. What were some challenges that you think you may have faced that you had problems surmounting, but how did you design your way around it?
So one major problem we had was more of like the situations that we had as a whole, because we were working on an Arduino project, and for that you would need you need the person who's working on the hardware and the software to be the same person, because if you create software, you can't exactly test it if you don't have the hardware on you. So what we did to combat that is we ended up distributing the tasks. So one person would work on the Arduino, while the other people would be working on the 3D printed casing and also on documentation.
In addition to this, there were other smaller problems that we faced. For example, the version of the casing that we printed, the hole for the button was actually a little bit too small for the button to fit through, but we didn't have time to reprint it. So instead we manually shaved it off so that it could still fit.
Roy ends up asking, but what are the dimensions of the device again?
So the dimensions of the device are, I believe, 15 by 15 centimeters.
And then the button itself has a 10-inch diameter, which we determined ought to be large enough for
Sorry.
10 centimeter. Thank you. Did I say inch? I apologize. 4-inch, 10 centimeter diameter. So that will we assume that will be large enough for the client to feel it, especially because it is majorly raised, and it does provide that tactile feedback, because when you push it down, it does spring back up.
Okay. Does the large button also trigger the Arduino to toggle the television on and off, or just end the automatic channel correction? And this question was from Ohm.
So it does both. So when you press the button, what it does is it turns off the TV first, and then it also turns off the Arduino until the next time it's pressed.
And this helps reduce the problems that come with the battery dying. Because we're using a real-time clock module, it luckily comes with its own battery. But if the battery in the real-time clock module is to die, you do have to resync it up with a computer. But by having an off switch, that keeps the battery that powers the Arduino from dying fairly quickly, which makes it easier because the user isn't having to replace it all the time. But it also means that the real-time clock, even though it runs on a separate battery, also isn't dying as frequently, which means there's less maintenance required for the device.
Okay, I think that was going to be my next question. What type of user serviceability is required for this?
So like what Kim said, there is some parts like you have to change the battery every so often. But one thing that we wanted to work on but weren't able to complete because of the time was that we wanted the user or their caretaker to be able to modify the channels on their own. So currently, the only way you can change the channels and the times would be for one of us to plug in our computers to the Arduino and then modify the code. But theoretically, in the future, what we would like to do is to connect the Arduino to some sort of app, which would allow the caretaker or the user to switch the channels to their liking on the fly.
Okay. So I think one last question before I think there will be any final comments. What was, from each of you, what did you find surprising that you learned through this whole process?
So one of the things that I found quite interesting was the fact that we were able to, like, I think a lot of groups have said, working remotely is a very different experience, but our group was able to come together and overcome, like, there was very good, I have to say, very good group chemistry in that we were good at, an Arduino task is something where we did have to divvy it up, as Andrew said. So we did a really good job, I think, of divvying up the task. And I don't think any one person, even if you did this entire like hardware software component, it didn't feel like, I hope anyways, that they were doing all of the work, because everybody was taking equal work, even if it was a very divvied up project. I know a lot of times teachers will warn against divvying up projects like you do this, you do this, you do this. But I feel like in this situation, it worked out extremely well, which was a great way to do this project.
Okay. Anybody else like to respond to that?
Yeah, so based off of what Kim was saying about like divvying up the stuff, because personally I thought since only one person could work on the Arduino itself at one time, I honestly didn't think we were going to be able to complete the project until like a few weeks ago, because there's a lot of moving parts that need to happen before it works. And also, if you have issues with anything, you can't just like call somebody up and be like, oh, can you fix this thing? because they also don't have the prototype with them, so they really can't help you with that much. So it's a lot of working independently within a group environment.
I think I would agree with all of that. Other than that, though, I don't know that I feel like I was necessarily surprised by a lot of things. I feel like we worked in a very orderly fashion in order to accomplish everything. And I think that we weren't hit by many major, like, other than having to work like by ourselves, I don't think that there were any like major surprise problems that we didn't foresee.
Thank you so much. Mr. Barney, are you ready to say
Yeah,
some last words?
well, just once again, I want to congratulate all the students. I mean, this was another great day. You know, we started at 9 o'clock this morning and we're wrapping up today, but I just want to, you know, say what a great job you did again. You know, this is your second presentation in 3 days. This one was very different. But once again, I think, you know, you all rose to the occasion again. I really enjoyed watching these today. I also want to thank everybody who joined us from the community. Your insight, your input, your questions for the students, it's very, very helpful. The feedback that you can give, because for a lot of the students, you know, this isn't the end of these projects. I think they're very invested in this work. And as we've seen in past years, I mean, they want to get for many of the teams that they want to finish these things off and get a deliverable to the people that they're working with. So your feedback is really invaluable. So they're going to keep going with these. Some of these projects, they're iterations that have started in previous years, and they're improvements on what students have worked on in the past, and they'll continue on for groups to come. You know, so you know, I think some of the insightful comments that the students made too about working remotely. I mean, when this COVID crisis started in March, we had Kevin and I had some serious conversations about whether or not we wanted to continue with this project, and we took a leap of faith. And I know he's, you know, the second week of March, when it was the last time we were allowed into the building, we were walking out of the Mass Academy with a couple of 3D printers in our hand, loading them into Kevin's trunk. And he said, I think I'm going to be learning a lot and doing a lot of 3D printing and testing and prototyping from Rhode Island. And so I want to thank him too. I mean, because this was really, you know, it's his first year with a new curriculum, and he's really done a tremendous job keeping the students supported in some of the work that they've had to do. So just really proud of everybody and how this whole project has turned out. They've worked incredibly hard to make it happen, and just another fantastic day for the school and the community. So thank you all for joining us, those of you who had a chance to watch this today, and I just want to thank all the students for their tremendous commitment to making this day a success. So thank you, Kevin.
All right. Well, I have to agree. I think everybody ended up pivoting quite well and adapting to the situation. And I'm happy to hear that many of you have been dedicated to trying to get their products out and have a deliverable device and continue over the summer to end up improving it. But I think everybody did a fantastic job. I'm going to end up leaving the room open. If you'd like to have any comments from the rest of the participants, you can turn your video on and your audio on and speak to that effect. So I'm looking at many of the comments in the chat room, and Roy ends up saying, thanks for reaching out. Great experience. All the students were outstanding. Last few presentations and projects were a bit stronger. Sorry I could not see all of the section 4. Have a great Memorial Day and a long weekend. So you guys all did a tremendous amount of work and awesome projects.
Friday too.
All right. It looks like people are signing off. It is late. Everybody, thank you so much and have a fantastic weekend.
Thank you.
Enjoy
for
your long
coming.
weekend, everybody. Tremendous work.
Okay.
Thank you.
Bye-bye.
Thank you, everybody.
Great job, Kevin.
Thank you. Yeah, I thought thought it went well. 6 hours well spent.
Yeah,
I love that.
Thank you, Elman.
Fantastic. Yeah, no, I think I think this is a great venue, and we need to think about this for next year.